Welcome back, my tired dumplings. Tonight we're going back to a time when winter lasted longer than anyone alive could remember. The glaciers crept south year by year, grinding mountains into dust and pushing forests into narrow bands of survival. Between the ice and the warmer lands to the south lay a zone of possibility. This was where life happened. So get cozy. Feel free to let us know how you're doing down below in the Community Circle comment section. And always know we curate these stories for you to learn something while you snooze. You can look up anything if you're curious. Now please dim your lights, turn on a fan for some ambient noise, and let us journey on inwards. 40,000 years ago, Europe was a different world. Ice sheets stretched across the northern lands, and two kinds of humans walked the same forests, hunted the same valleys, and shared the same cold stars overhead. This is the story of that meeting. The landscape would look strange to you now. Imagine stepping out into a world where the trees are scattered and stunted. Cold winds blow across open grasslands that stretch to the horizon. In summer, wildflowers burst from the tundra in waves of purple and gold. In winter, the ground freezes so hard that even the largest animals leave barely a trace. The air smells different here. It carries the sharp mineral scent of glacial melt and the thick musk of animals you have never seen except in books. Mammoths move across the plains in family groups. Their curved tusks sweep through the snow to reach the dried grasses underneath. Woolly rhinoceros lumber through river valleys, their thick coats matted with ice. Cave lions watch from rocky outcrops, their muscles rippling beneath golden fur. Giant elk with antlers spanning 12 feet cross the meadows at dawn. You hear their calls echoing through the valleys, strange and haunting in the pre-dawn light. The sky itself seems larger here. At night, the stars blaze with an intensity that no modern city dweller has ever witnessed. The Milky Way is not a faint smudge, but a river of light cutting across the darkness. Aurora Borealis dances green and violet across the northern horizon, casting strange shadows on the snow. The moon rises huge and orange over the steppe, illuminating a world that feels both beautiful and unforgiving. Rivers run cold and clear from the melting edges of distant glaciers. In spring, these waterways swell and carve new channels through the landscape. Salmon run upstream in numbers that seem impossible, their silver bodies flashing in the shallows. Bears wade into the current, snatching fish with practiced efficiency. Wolves follow the herds of reindeer and horse, testing for weakness, working in coordinated silence. This is the world where our story begins, not in one place, but across a vast territory spanning from what we now call Spain to the caves of southern France, from the river valleys of Germany to the rocky coasts of Gibraltar. The climate shifts and changes with the centuries. Sometimes the ice retreats and forests creep north. Other times the cold tightens its grip, and the glaciers advance again, forcing everything living to adapt or move or disappear. In the middle of all this change, humans make their homes. But not one kind of human. Two separate lineages, each shaped by hundreds of thousands of years of evolution in different parts of the world, now share this challenging landscape. They have different bodies, different faces, different ways of thinking about the world around them, yet they are both undeniably human. The first group has been here for a very long time. Their ancestors walked these lands for over 200,000 years before the second group arrived. They know every cave, every seasonal migration route, every place where flint can be found and shaped into tools. They have weathered ice ages that would have destroyed less adaptable species. They have learned to read the landscape like a language, to predict where game will be and when plants will fruit and how to survive winters that can kill in a single night. These are the Neanderthals. The name comes from a valley in Germany where their bones were first recognised as belonging to an ancient human relative. But that valley was just one small place in a vast territory. Neanderthals lived across Europe and Western Asia for millennia, adapting to climates both harsh and mild, developing technologies that worked, raising children who learned to survive in a world that demanded constant vigilance and skill. Picture a Neanderthal standing on a cliff overlooking a river valley at sunset. The figure is stockier than a modern human, built for power and endurance rather than the long-distance efficiency that would come to characterise later populations. The body is barrel-chested with thick bones and powerful muscles designed to generate and conserve heat. The face is distinctive, with a prominent brow ridge, a large nose adapted for warming frigid air before it reaches the lungs, and a jaw that projects slightly forward. The hair is thick and probably reddish-brown, based on genetic evidence we would not discover for thousands of years. This person is not a brute or a primitive caricature. The eyes are intelligent, observant, taking in details of the landscape that you might miss. A group of reindeer moves across the opposite hillside. The wind direction is noted. The season, the condition of the animals, the best approach for tomorrow's hunt. All of this information processes quickly, filed away in a brain that is actually slightly larger on average than those of modern humans. Behind this solitary watcher, deeper in the valley, others are making camp for the night. A fire has been started using methods passed down through countless generations. Sparks from striking flint against iron pyrite have caught in a bundle of dried fungus and grass. The fire is fed carefully, efficiently. Nothing is wasted in this world. The flames push back the darkness and the cold. They make this one small space feel like home. Someone is working on a hide, scraping away fat and tissue with a stone tool shaped precisely for this purpose. Another person naps fresh flint, the sharp crack of stone on stone ringing out in the evening air. A third tends the fire and prepares food. There is a rhythm to this work, a practiced ease that speaks to thousands of years of accumulated knowledge. Children play near the fire, but not too close. They learn by watching, by doing, by the gentle corrections of those older and more experienced. There is no written language, no recorded history in the way you would recognize it. But there is teaching, nonetheless. How to read tracks in the snow, which plants are safe to eat and which will make you sick. How to approach dangerous game without getting killed. Where to find the best stone for tool making. How to cure hides so they stay supple through the winter. The knowledge is vast and vital and passed on through observation and practice. This is a sophisticated culture, though it leaves fewer traces than the civilizations that would come later. Neanderthals made complex tools that required careful planning and significant skill. They controlled fire, built shelters, created compound adhesives by heating birch bark at precise temperatures. They cared for their injured and sick, as evidenced by individuals who survived wounds and disabilities that would have been fatal without help from others. They buried their dead with what appears to be ceremony and care. Recent evidence suggests they created art, though the record is frustratingly sparse. Shells with traces of pigment, carved bones, cave paintings in Spain that may predate the arrival of modern humans. The picture is incomplete, but it hints at inner lives richer than the old stereotypes suggested. They spoke. We cannot know exactly what their language sounded like, but anatomical evidence suggests they had the physical capacity for complex speech. The hyoid bone, which supports the tongue and larynx, is present and shaped much like that of modern humans. Their ear anatomy was suited for hearing the range of sounds used in human language. They communicated, told stories, shared knowledge, warned of danger, probably laughed and argued and comforted one another in words we will never hear. For 200,000 years, Neanderthals were the humans of Europe. They saw climate swing wildly from warm to cold and back again. They watched species go extinct and new ones arrive. They adapted, survived, endured. Their population probably never grew very large by modern standards. Estimates suggest perhaps tens of thousands at any given time, spread across a huge territory. Small bands moving with the seasons, occasionally meeting other groups for trade or to find mates or simply for the comfort of seeing other human faces. And then, around 50,000 years ago, something changed. New people began arriving from the east and south. These newcomers looked different, moved differently, made different kinds of tools. They came in small groups at first, testing the territory, learning its rhythms. They were not invaders in the way later migrations would be. There were no armies, no organised conquest, just people moving into new lands, following game and opportunity, settling in places that seemed promising. These were the early modern humans, Homo sapiens, our direct ancestors. They had evolved in Africa over the previous 200,000 years, developing their own distinctive anatomy and culture. Now they were expanding out of their ancestral homeland, moving into the Middle East, Asia, and eventually Europe. They were taller and more lightly built than Neanderthals, with higher foreheads and more prominent chins. Their bodies were designed for endurance and efficiency in warmer climates, though they proved remarkably adaptable to the cold. The stage was set for an encounter unlike any other in human history. Two human lineages, separated for over 500,000 years, were about to share the same landscapes, the same resources, perhaps even the same campsites and caves. What happened next would shape the future of our species in ways that are still being discovered and debated today. The Ice Age world was vast and often empty. Resources were scattered and seasonal. There was room, in theory, for both groups. But territory that could support human life was limited, constrained by climate and the distribution of game and fresh water. Inevitably, these two peoples would cross paths. They would see each other across valleys, encounter each other at waterholes and crossing points, perhaps compete for the same caves and the same hunting grounds. How did they react? Did they fight? Trade? Ignore each other? Something more? The archaeological record is tantalizingly incomplete, but the evidence we do have suggests a more complex story than simple conflict or simple coexistence. It hints at interaction, at choices made and relationships formed in ways both expected and surprising. But before we explore what happened when these two groups met, we should understand who the Neanderthals really were. Not the crude stereotypes of old textbooks, but the people themselves. What their lives were actually like, day by day, season by season, in a world of ice and stone and survival. Morning in a Neanderthal camp begins before the sun clears the horizon. The fire from the night before has burned down to embers, but someone has been tending it through the darkness, adding fuel at intervals to keep the coals alive. Fire is too valuable to let die. Creating it from scratch takes time and effort, and in wet weather it can be nearly impossible. Better to maintain what you have. The first person to rise rebuilds the flames, coaxing them back to life with dry grass and small sticks. Smoke rises straight up in the still morning air. The temperature hovers just above freezing. Your breath forms clouds that hang in the air for a moment before dissipating. Around the fire, others begin to stir, pulling closer to the warmth, blinking away sleep. Breakfast is simple: dried meat from yesterday's kill, perhaps some early berries if the season is right, water from a nearby stream. The food is eaten without ceremony but with complete attention. Nothing is taken for granted here. A full belly is a gift, and you have learned to appreciate it when it comes. The camp is located in a rock shelter, a natural overhang that provides protection from wind and rain. The back wall is blackened from countless fires. The floor is littered with the debris of daily life, though not randomly. Stone flakes from tool making are concentrated in one area, animal bones in another. There is organisation here, patterns that repeat across Neanderthal sites throughout Europe. Today there will be a hunt. Several adults have been tracking a small herd of red deer for the past 2 days. The animals are moving toward a valley that narrows between two rocky slopes, the kind of terrain that gives hunters an advantage. The plan has been discussed and refined. Everyone knows their role. Hunting for Neanderthals is not the romantic adventure depicted in old paintings. It is calculated risk, careful stalking, and moments of explosive violence. The weapons are simple but effective. Wooden spears with stone points, hardened over fire for durability. The spears are not thrown from a distance but used for close-range thrusting. This requires getting dangerously near to animals that can kill you with a kick or a gored antler. The hunting party moves out as the sun rises higher. They leave behind the very young and very old, those who would slow the pursuit or are too valuable to risk. Neanderthal groups were probably small, maybe 20 to 30 individuals at most. Losing even one person could threaten the whole group's survival. The country they move through is neither forest nor open plain, but something in between. Scattered pine and birch trees grow along the river bottoms. The higher ground is covered in tough grasses and low shrubs. In the distance, the white peaks of mountains mark the edge of the ice, glaciers visible even from here, though they're still many days' travel away. The hunters move quietly, reading signs invisible to untrained eyes. A broken branch at a certain height indicates where a deer passed through yesterday. Tracks in soft mud show which direction they were heading and how fast they were moving. Droppings reveal how recently the animals were here and what they have been eating. This is a deep literacy of landscape accumulated over generations, as precise and meaningful as any written language. By midday they have closed the distance. The deer are ahead, grazing in a meadow bordered by rocks on two sides. The wind is blowing from the animals toward the hunters, carrying their scent away. Good. The hunters spread out, moving into position with patience that comes from understanding. There is only one chance to get this right. The attack, when it comes, is swift and coordinated. Several spears thrust almost simultaneously into the flank of an older female who is separated slightly from the herd. She staggers, tries to run, but the wounds are deep. The other deer scatter in panic, bounding away across the meadow and disappearing into the trees. The injured animal makes it perhaps 50 metres before collapsing. The hunters approach carefully. Wounded animals can still be dangerous, but this one is clearly dying, her breathing laboured and shallow. Someone delivers a final thrust to end the suffering quickly. There is no waste of energy, no unnecessary cruelty. This is food, survival, respect for the animal that makes your continued existence possible. The butchering begins immediately. Stone tools slice through hide and muscle with practiced efficiency. The best cuts of meat are removed first, then the organs, the bones with marrow, the useful tendons and sinew. The hide is carefully removed in one piece, valuable for clothing or shelter. Nothing is discarded thoughtlessly. Even bones will be cracked open for marrow or shaped into tools. What cannot be carried is cached, buried in a cold spot where it might last a day or two before scavengers find it. The group loads themselves with as much as they can bear. The journey back to camp takes longer now, heavy with success. This one deer might feed the group for several days, allowing time for other activities like tool making, hide processing, or simply rest. Back at camp, the meat is divided according to patterns we can only guess at. Likely those who participated in the hunt receive larger shares, but the young and old are not left out. Survival in small groups depends on taking care of everyone, not just the strongest. A child today might be a hunter tomorrow. An elder carries knowledge too valuable to lose. Some of the meat is eaten fresh, cooked over the fire until the outside is charred and the inside tender. The fat sizzles and pops, filling the rock shelter with rich smells that make your mouth water. Other portions are cut thin and hung to dry, preserving them for future need. Nothing here is abundant enough to waste. As evening settles in, the pace slows. Someone works on repairing a spear that was damaged in the hunt, carefully attaching a new stone point with cordage made from plant fibres and sealed with birch tar adhesive. The process is intricate, requiring multiple steps and precise timing. The tar must be heated to exactly the right temperature, or it will not work. This is chemistry, albeit learned through trial and error over countless generations. Another person scrapes the deer hide, working it back and forth over a smooth stone to remove every trace of fat and tissue. Later it will be cured and softened, transformed from a stiff bloody skin into supple leather. This takes days of work, but the result is worth it. Good clothing means the difference between comfort and misery in winter. Children watch, and occasionally help, learning skills they will need to master by the time they reach adulthood. There is no formal schooling, but education happens constantly through observation and participation. A child learns to knap flint by watching an adult, then trying with guidance and correction. They learn to identify plants by following foragers and testing their knowledge. They learn to move quietly through the forest by accompanying hunters and being taught what not to do. Neanderthal childhood was probably shorter than modern childhood. Children had to become capable contributors relatively quickly, but there was still time for play, for exploration, for developing bonds with others in the group. Toys have been found at Neanderthal sites, simple carved objects that suggest leisure and imagination existed even in this demanding world. The group's territory is large, perhaps several hundred square kilometres. They do not settle permanently in one place, but move throughout the year, following seasonal resources. In summer, they might camp in open meadows near good hunting. In winter, they retreat to protected rock shelters and caves. They know this land intimately, every source of fresh water, every outcropping of useful stone, every pass through the mountains, every place where certain plants grow. Other groups exist in neighbouring territories, but contact is probably infrequent. A few times a year, different bands might meet at neutral gathering places. These meetings serve important functions. They allow young people to find mates outside their immediate family, preventing inbreeding. They enable trade of tools, raw materials and information. They reinforce social bonds and cultural knowledge. At these gatherings there might be feasting, storytelling, demonstrations of skill. A particularly talented toolmaker might trade their products for access to high-quality flint from another group's territory. A successful hunter might gain status through displays of prowess or generosity. Young people might form bonds that lead to joining another group. The total Neanderthal population across Europe and Western Asia at any given time was probably modest. Estimates range from a few thousand to perhaps 70,000 individuals, though the numbers likely fluctuated with climate and resource availability. These are small populations by modern standards, vulnerable to random catastrophes and genetic drift. But what they lacked in numbers, they compensated for in durability. Neanderthals thrived for over 200,000 years in environments that swung from temperate to glacial and back again. They survived volcanic eruptions, ice ages, and the extinction of prey species. They were not primitive or doomed by biological inadequacy. They were highly successful humans, adapted to their world and capable of remarkable ingenuity. Their tools, while simpler in some ways than those that would later be made by modern humans, were far from crude. The Mousterian tradition, named after a site in France, represents a sophisticated approach to stone tool manufacture. A single carefully prepared stone core could yield dozens of sharp flakes, each shaped for specific purposes. Scrapers for processing hides, points for spears, blades for butchering. The makers understood the properties of different types of stone and exploited them expertly. Recent discoveries have expanded our understanding of Neanderthal capabilities even further. They created pigments by grinding and heating minerals, though we are still uncertain exactly how these were used. They crafted jewellery from eagle talons and shells, suggesting symbolic thought and personal adornment. They used medicinal plants, identified through residue on their teeth, indicating knowledge of healing and pain relief. Perhaps most remarkably, they cared for the vulnerable. Skeletons have been found showing evidence of severe injuries or disabilities that healed over time, proving the individual survived long after they would have died without help. A partially paralysed person, someone with a withered arm, an individual missing most of their teeth, unable to process raw food independently. These people lived because others chose to keep them alive, to share food and provide protection. This is compassion. This is community. This is what makes us human, in the deepest sense of that word. Neanderthals buried their dead, though the practice was probably not universal. Some graves show signs of deliberate arrangement, the body positioned carefully, sometimes accompanied by objects or even flowers. The meaning of these burials is debated. Were they expressions of grief, religious belief, or simply a practical way to dispose of remains and discourage scavengers? We may never know for certain, but the care taken in some cases suggests something beyond mere utility. Their world was hard, but it was not without beauty or meaning. They experienced sunrises and storms, the return of spring after brutal winters, the satisfaction of a successful hunt, the warmth of fire on a cold night. They loved their children, mourned their dead, celebrated their successes. They were people, in all the complexity that word implies. And into this world, around 50,000 years ago, came new people who would change everything. The story of modern humans begins far from the ice and mountains of Ice Age Europe. It begins in Africa, in landscapes of grasslands and scattered trees, in river valleys and coastal plains. This is where our species evolved, where we developed the anatomy and behaviours that define Homo sapiens. By 200,000 years ago, early modern humans were living in eastern and southern Africa. They looked much like people do today. Tall and lightly built, with high foreheads and prominent chins, less robustly built than their Neanderthal cousins to the north. Their bodies were adapted for endurance in warm climates, efficient at shedding heat rather than conserving it. For thousands of generations they remained in Africa. The continent was large and diverse enough to support growing populations. Resources were relatively abundant compared to the northern latitudes. There was no immediate pressure to leave. But humans are curious, restless, always looking beyond the next horizon. Around 100,000 years ago, some groups began moving north. The first attempts to expand out of Africa may have faltered, turning back or dying out. But eventually some succeeded in establishing populations in the Middle East. From there, the expansion accelerated. Groups spread east into Asia, south into the islands of Southeast Asia, and eventually north into Europe. The journey took thousands of years. It was not a purposeful migration in the modern sense, not a decision to travel from one specific place to another. Instead, it was a gradual expansion of range, each generation moving slightly farther than the last, following game and opportunity, settling in promising areas, and occasionally sending out explorers who would become the founders of new populations farther afield. Imagine being part of one of those early groups, moving into territory where your people have never been. You have left behind the landscapes your ancestors knew for countless generations. Everything here is new. Different plants, different animals, different weather patterns. You must learn it all from scratch, adapting techniques developed in warmer climates to work in this colder, stranger place. The route north from Africa passed through the Levant, the crossroads where Asia, Africa and Europe meet. This region was milder than the frozen north, a transitional zone where modern humans first encountered traces of other human groups. Neanderthals had been here too, their tools and campsites evidence of their presence. For a time, both groups probably shared this territory, though the evidence for direct interaction is frustratingly limited. From the Middle East, some groups turned east toward Asia, others continued north into what is now Turkey and the Caucasus, and some eventually pushed west into Europe itself. This was the most challenging route, leading directly into Neanderthal heartland during an ice age. Why go? Perhaps population pressure from behind drove them forward. Perhaps curiosity and the human impulse to explore. Perhaps they were following herds of animals moving with seasonal patterns. Or maybe there was no grand reason, just small choices made year by year, camp by camp, that collectively resulted in a massive geographic expansion. By around 45,000 years ago, modern humans were arriving in Europe in significant numbers. They entered from the southeast, following river valleys and coastal routes. The climate at this time was cold, but not at its worst. The ice sheets had temporarily retreated, creating a window of opportunity for settlement. These early Europeans brought technologies that differed from Neanderthal traditions. They made smaller, more specialised stone tools, including delicate blades and points that required significant skill to produce. They crafted tools from bone and antler, materials that Neanderthals used, but not as extensively. They created beads and pendants from shells and teeth, marking the beginning of a tradition of personal adornment that would become increasingly elaborate over time. Perhaps most significantly, they brought a different approach to resource use and social organisation. While Neanderthals tended to stay within relatively restricted territories, modern humans ranged more widely, establishing trade networks that moved materials like shells and high-quality stone over distances of hundreds of kilometres. This suggests larger social networks, more contact between distant groups, and a different relationship with territory and resources. The first modern humans in Europe faced the same challenges that Neanderthals had long since mastered: surviving the cold, finding food in a landscape where resources were seasonal and unpredictable, avoiding predators that were faster, stronger, and better armed than any human. They had to learn quickly or die. But they had one advantage. They could learn not just from their own experience, but from anyone they encountered. If they met Neanderthals, observed their techniques, saw what worked and what did not, that knowledge could be absorbed and adapted. Innovation could flow between groups, accelerating the pace of cultural evolution. Picture a small band of modern humans in their first European winter. They have never experienced cold like this. The African savanna, even at its coolest, never prepared them for temperatures that can freeze exposed skin in minutes. They huddle in a cave they found abandoned, trying to keep a fire burning with wet wood. The wind howls outside, driving snow through the entrance. This is not survival. This is barely endurance. Then perhaps they encounter Neanderthals. Maybe they see smoke from a nearby fire and cautiously approach. Maybe they find a campsite and examine the remains, learning from the arrangement and tools. Maybe there is a face-to-face meeting, tense and uncertain, two groups of humans trying to decide if the others represent threat or opportunity. What happens next changes everything. The archaeological record shows something remarkable. At several sites in Europe, we find evidence of both Neanderthals and modern humans using the same locations, sometimes separated by years, sometimes apparently at the same time. The tools of both groups appear in the same layers of sediment. The remains of their fires are intermingled. They were here together. One of the most telling sites is in southern France, in the Rhône Valley. Multiple caves and rock shelters show occupation by both groups over a period of several thousand years. The stratigraphy is complex, layers upon layers of habitations separated by periods of abandonment when the climate became too harsh, even for these hardy people. But what is clear is that this was shared territory, used by both populations at different times and possibly simultaneously. In some cases, Neanderthal tools show influences from modern human techniques. Stone points become more refined. New styles emerge that blend characteristics of both traditions. This suggests knowledge transfer, learning, cultural exchange. If the two groups never interacted, how could such changes occur? Other sites tell different stories, places where only Neanderthal artifacts are found, with no trace of modern humans. Regions where modern humans seem to have established themselves without any Neanderthal presence. The picture is not uniform across Europe. Different regions, different outcomes. Some places saw contact and mixing, others remained isolated. The island of Gibraltar, at the southern tip of Spain, appears to have been one of the last Neanderthal refuges. The climate there remained relatively mild, even during the worst of the Ice Age. Resources from both land and sea were available. Neanderthals lived there until perhaps 28,000 years ago, thousands of years after they had disappeared from most of Europe. Did they know they were among the last? Did they have any concept of their species dwindling toward extinction? In Croatia, at a cave called Vindiga, both Neanderthal and modern human remains have been found in deposits dated to roughly the same time period. The dating is not precise enough to prove they were there simultaneously, but the overlap is suggestive. This was a border zone, a place where two worlds met. The Swabian Jura in southern Germany has yielded some of the earliest modern human art in Europe. Carved ivory figurines depicting animals and strange human-animal hybrids. Flutes made from bird bones, the oldest known musical instruments. These objects date to around 40,000 years ago, just when modern humans were establishing themselves in the region. They represent a cultural flowering, a burst of creativity and symbolic expression. Neanderthals were still present in this region at that time. Did they see these carvings, hear the music? Did the presence of new neighbours with new ways of thinking inspire them, threaten them, or simply puzzle them? We know from later evidence that the two groups did more than just share space. They interbred. The genetic data is unambiguous on this point. All non-African people today carry roughly 1 to 2% Neanderthal DNA in their genomes. This means that at some point Neanderthals and modern humans had children together, and those children survived and reproduced, passing on a mixture of both ancestries to future generations. When did this happen? Where? How often? The genetics suggest most of the interbreeding occurred relatively early, probably in the Middle East before modern humans had fully spread into Europe. But there may have been later encounters as well, smaller events that left less clear genetic signatures. What were these encounters like? Were they peaceful, coercive, consensual? The bones and genes cannot tell us about individual experiences or emotions. We can only infer from the patterns and try to imagine the reality behind the data. Perhaps a young modern human woman, separated from her group during a hunting accident, is found by a Neanderthal band. She's injured, unable to travel. They take her in, care for her, and over time she becomes part of their community. She has children with a Neanderthal man, and those children grow up between two worlds, carrying genes from both lineages. Or perhaps a Neanderthal youth, curious and bold, seeks out the new people camped in a neighbouring valley. Trade begins, then friendship, then something more intimate. The details matter, but they are lost to time. What we know is that it happened. The evidence exists in every cell of your body if your ancestors came from outside of Africa. You carry Neanderthal genes. They contributed to your immune system, your skin tone, your susceptibility to certain diseases. They are part of what makes you human. This was not replacement. This was not conquest and genocide, though competition and conflict surely occurred. This was a more complex process of interaction, exchange, and ultimately absorption. Over thousands of years, Neanderthals as a distinct population disappeared, but they did not vanish completely. They live on in us, a ghost population visible only through the lens of genetics. The frontier between Neanderthal and modern human populations was not a line on a map, but a shifting mosaic of territories, a patchwork of occupied and empty lands that changed with the seasons and the years. In some valleys, Neanderthals hunted and gathered as they had for millennia. In others, modern humans established camps and began learning the rhythms of European life. And in between, in the boundary zones, both groups moved and met and made choices about how to respond to each other. The first encounters were probably cautious. Neither group would have known what to make of the other. Clearly human, clearly intelligent, but different. The body language would be similar enough to read basic intentions: aggression, fear, curiosity, friendliness. These are universal among social primates. But the details of communication might have been difficult. Did they share enough language to speak? Probably not at first. Gestures, demonstrations, shared activities might have bridged the gap. Trade could have occurred without much language, displaying an object, pointing to something desired in exchange, nodding or shaking the head. This is how humans have traded across language barriers throughout history. There is no reason to think it could not have worked in the Ice Age as well. What did they trade? Raw materials, certainly. High-quality flint was not evenly distributed across the landscape. Groups with access to good stone sources could trade surplus material for other valuable items. Hides, prepared and tanned, were always useful. Tools, perhaps, though most groups could make their own. Rare items like shells from distant coasts, ochre for pigments, medicinal plants known only in certain regions. Imagine a neutral meeting ground, a river crossing where paths converge. Two groups arrive from different directions, perhaps by prior arrangement, perhaps by chance. There is tension at first. Hands rest on weapons, just in case, but no one attacks. Slowly the groups approach each other. Items are laid on the ground, flint blades from one side, shells from the other. Gestures indicate what is being offered and what is wanted in return. After some negotiation, the exchange is made. Both groups retreat, watching each other warily but without violence. The encounter ends peacefully. This might happen once a year or less often. Most of the time, the groups would never see each other, living out their lives in separate territories, with only occasional indirect evidence of the other's existence. A distant smoke column, tracks leading away from a water source, the remains of a fire that was not made by anyone in your group. But over time, familiarity might breed something other than contempt. If encounters were generally peaceful, if trade proved beneficial, the barrier between groups might soften. Perhaps a young person from one group, exiled or simply adventurous, seeks acceptance with the other. Perhaps during a harsh winter, one group allows another to shelter in their territory in exchange for help with hunting or defence against predators. The archaeological evidence for direct interaction is sparse but tantalising. At the cave of Arcy-Secure in France, Neanderthal remains were found alongside sophisticated ornaments made from ivory and bone, items that closely resemble those made by modern humans elsewhere. Did Neanderthals create these independently, inspired by what they saw? Did they trade for them? The deposits are disturbed, making precise interpretation difficult, but the association is suggestive. At the Saint-Césaire site, also in France, a Neanderthal skeleton was found in association with tools of the Shuttle-Peronian tradition, a technology that blends Neanderthal and modern human characteristics. This has led to debates about whether Neanderthals were capable of innovating these tools independently or learned the techniques from modern humans. The answer probably varies by location and group. Some researchers argue that the presence of similar tool types in both Neanderthal and modern human sites indicates parallel development rather than cultural contact. Smart people in similar environments solving similar problems might arrive at similar solutions independently. Others point to the timing and distribution of these hybrid technologies as evidence of diffusion and learning between groups. The truth probably lies somewhere in the middle. Some innovations were independent, others were borrowed and adapted. Culture is always a mix of invention and imitation, and there is no reason to think Ice Age humans were any different. One of the most intriguing pieces of evidence comes from genetic analysis of Neanderthal remains. The patterns of DNA variation suggest that Neanderthal populations were small and somewhat isolated from each other, leading to low genetic diversity. This made them vulnerable to inbreeding and accumulation of harmful mutations. When modern humans arrived with their larger population sizes and more extensive social networks, the genetic influx from interbreeding might have been beneficial in the short term, bringing fresh genetic diversity into isolated Neanderthal groups. But it also might have contributed to their eventual disappearance. Small populations absorbing genes from a larger, more numerous group can eventually be swamped. The distinct Neanderthal genetic signature gets diluted over generations until it is no longer recognizable as a separate lineage. This is not extinction through violence, but through assimilation. Climate change also played a role. Around 40,000 years ago, the climate began another shift toward colder, drier conditions. Resources became scarcer. Territories that had supported small populations became marginal or uninhabitable. Competition for the remaining good lands increased. modern humans may have had advantages in this competition. Their more extensive social networks allowed them to share information about resources over large areas. Their technologies included innovations like sewing needles made from bone, enabling better cold weather clothing. They used a wider variety of tools for a wider range of tasks, possibly making them more efficient at resource extraction. But these advantages were not overwhelming. Neanderthals were still formidable survivors, still capable of thriving in harsh conditions. The process of displacement took thousands of years, not decades or centuries. This was not a blitzkrieg, but a slow, grinding down of populations already under stress. In some regions, Neanderthals seem to have disappeared quickly after modern humans arrived. In others, they persisted for millennia, holding on to territories that modern humans found less appealing or more difficult to penetrate. The pattern is complex, varying by region and local conditions. Disease might have played a role. When populations that have been separated for hundreds of thousands of years come into contact, there is potential for disease transmission. Modern humans might have carried pathogens to which they were resistant, but which devastated Neanderthals, or vice versa. The archaeological record cannot capture diseases that leave no trace on bones, so we can only speculate about this possibility. What we know for certain is that by around 39,000 years ago, Neanderthals had vanished from most of Europe. Only a few isolated populations remained, hanging on in refuges at the edges of the continent. Gibraltar, the Italian peninsula, isolated mountain valleys. One by one, these last populations faded away. The last known Neanderthal remains date to around 28,000 years ago, though some researchers argue the extinction occurred earlier and the later dates are contaminated. Either way, by 25,000 years ago at the latest, Neanderthals were gone as a living population. But not completely gone. Their genes persisted in the modern human populations that had absorbed them. Their knowledge might have too techniques and strategies passed on through those hybrid children and their descendants. The boundary between Neanderthals and modern humans was always porous. The encounter was not a clash of civilizations, but a mingling, a complex interaction that defies simple narratives of winners and losers. The landscape of Ice Age Europe was not evenly divided between Neanderthals and modern humans. It was a shifting patchwork of territories where both groups hunted, gathered, and made their homes. Understanding how they shared this space requires looking at the archaeological evidence with care and patience. Caves and rock shelters were prime real estate. They offered protection from wind and predators, natural shelter that did not require construction. Good caves were reused over and over, sometimes for thousands of years. At many sites we find layers of occupation by both groups, separated by periods when the cave was abandoned and then reoccupied. At Gorham's Cave in Gibraltar, excavations have revealed a deep stratigraphy spanning tens of thousands of years. Neanderthals used this site repeatedly, leaving behind tools, hearths and food remains. The deposits show they were eating seafood like mussels and limpets, hunting birds, and taking advantage of both land and marine resources. This demonstrates sophisticated knowledge of the local environment and the ability to exploit multiple food sources. Modern humans also used caves extensively. At sites like Abri-Patour in France, we find evidence of repeated occupation over millennia. The deposits contain tools, art objects, and remains of meals. The stratigraphy allows researchers to track changes in technology and subsistence strategies over time. When both groups use the same cave at different times, we can compare their approaches. Sometimes the differences are stark. Modern humans leave behind more diverse tool types, more personal ornaments, more evidence of long-distance trade. Neanderthals leave simpler assemblages, fewer decorative items, more emphasis on heavy-duty tools for processing game and hides. But sometimes the differences are subtle or absent. Both groups controlled fire expertly. Both hunted similar animals using similar strategies. Both processed hides and made them into clothing and shelter. The basic challenges of survival in this environment demanded similar solutions regardless of who was doing the surviving. Stone tool technology offers one of the best windows into possible cultural exchange. Tools are abundant in the archaeological record. They preserve well, and their forms can be compared across sites and through time to track changes and innovations. The Mousterian tradition associated with Neanderthals is characterized by flakes struck from prepared cores. The napper would carefully shape a stone core and then strike it to produce flakes of predetermined size and shape. These flakes were then retouched into various tool types. scrapers, points, knives. The technique is efficient and produces high-quality tools. Modern humans brought with them the Upper Paleolithic tradition, characterised by blade production. Blades are long, narrow flakes struck in sequence from a specially prepared core. This technique produces more cutting edge per unit of stone, an advantage when good quality flint is scarce. Blades can be further modified into a wide array of specialised tools: barons for engraving, backed knives for cutting, microliths that can be hafted into composite tools. In the transition period, when both groups were present in Europe, we see intermediate traditions that blend characteristics of both. The shuttle Peronian, mentioned earlier, includes both Mousterian-style flakes and blade production. The Eleusinian tradition in Italy shows similar mixing of techniques. Were Neanderthals learning from modern humans, inventing independently? The debates continue, but the presence of these hybrid technologies in regions and times when both groups were present suggests at least the possibility of cultural transmission. Symbolic behaviour is another area where comparisons are revealing. Modern humans produced abundant art from early on: cave paintings, carved figurines, engraved bones, beads and pendants. These objects are found across Europe wherever modern humans lived. Neanderthal symbolic behaviour is more controversial. There are hints: perforated shells that might have been worn as ornaments, scratched bones that might be decorative, cave paintings in Spain that might predate modern human arrival. But the evidence is always debatable, often unclear. Recently, researchers have argued more forcefully for Neanderthal symbolic capacity. The Spanish cave paintings, if the dates hold up, would prove that Neanderthals created art independently, without learning from modern humans. Pigments found at Neanderthal sites show they were processing ochre and other materials, though what they did with them remains uncertain. The question matters because symbolic thought, the ability to represent meaning through abstract forms, is often considered a hallmark of modern human cognition. If Neanderthals possessed this capacity, it challenges old ideas about what made us unique. If they lacked it, it might help explain why they ultimately disappeared while we survived. But perhaps the question is poorly framed. Humans exist on a continuum, not divided into symbolically capable and symbolically incapable. Neanderthals clearly had inner lives, thoughts, emotions. Whether they expressed these through art as frequently or elaborately as modern humans is a separate question from whether they were capable of such expression. Hunting strategies offer another point of comparison. Both groups hunted large game: reindeer, horses, bison, mammoths. The approaches were probably similar: stalking, ambush, communal drives where animals were herded toward natural traps or killed in groups. But there are subtle differences. Modern humans seem to have hunted a wider variety of prey, including smaller, fast-moving animals like rabbits and birds. This might reflect better projectile technology, the ability to throw spears from a distance rather than relying on thrusting spears. Modern humans also exploited aquatic resources more extensively: fish, shellfish, waterfowl. Neanderthals ate these foods too, but less consistently. These differences in diet might have given modern humans an advantage during times of scarcity. Being able to fall back on alternative food sources when large game was unavailable could mean the difference between survival and starvation. Social organisation is harder to infer from archaeology, but there are clues. The distribution of materials at modern human sites suggests larger social networks. Shells from the Mediterranean show up hundreds of kilometres inland. High-quality flint from specific sources is found across large regions. This indicates trade, exchange and communication across distances that would have required interactions between many different groups. Neanderthal sites show less evidence of long-distance material movement. Resources tend to be local, acquired within a day's travel of the campsite. This does not mean they lacked social networks, but those networks might have been smaller or less extensive. Larger social networks have survival advantages. They buffer against local resource failures. If one region has a poor hunting season, connections to neighbouring groups can provide alternatives. Information about where game is plentiful can be shared. Innovations spread faster through larger networks. But larger networks also require more complex social management. Keeping track of who owes what to whom, maintaining relationships with people you might only see occasionally, negotiating access to resources and territories. Modern humans seem to have been adept at this kind of social complexity. Perhaps this was one of the critical differences. not intelligence in some abstract sense, but social intelligence, the ability to build and maintain relationships across large groups, to cooperate with distant neighbours, to create cultural institutions that allowed for trust and exchange without constant face-to-face contact. Language likely played a role. Both groups could speak, but the complexity and nuance of their language might have differed. More complex language allows for more detailed sharing of information, for teaching and storytelling, for social bonding and negotiation. If modern humans had a slight edge in linguistic ability, that could translate into significant advantages in social organisation and cultural transmission. But we should be cautious about overstating these differences. Neanderthals were not simple or primitive. They survived for far longer as a distinct lineage than modern humans have existed so far. They endured ice ages and climate shifts that would have destroyed less capable populations. They were smart, resourceful, and resilient. The fact that they disappeared while we survived does not mean they were inferior. It might mean they were unlucky. Smaller populations are more vulnerable to random chance. A bad winter, a disease outbreak, a volcanic eruption in the wrong place at the wrong time. Any of these could push a stressed population over the edge, or it might mean they were outcompeted by a group with specific advantages in a particular set of circumstances. Change the circumstances, and the outcome might have been different. What is clear is that for several thousand years, Neanderthals and modern humans shared Europe. They used the same resources, faced the same challenges, and possibly learned from each other. The archaeological record shows a complex pattern of interaction, not a simple story of displacement or conflict. And beneath that complexity lies a fact that was only discovered recently, one that changes how we understand this entire period. Neanderthals and modern humans did not just share space, they shared genes. They interbred, creating hybrid offspring who carried the legacy of both lineages into the future. The revelation that modern humans carry Neanderthal DNA was one of the great scientific surprises of the early 21st century. For decades, researchers had debated whether Neanderthals and modern humans interbred. Some argued that the anatomical differences between the groups were too great. Others pointed to the potential for gene flow wherever two compatible species overlapped. The debate could not be settled by morphology alone. Bones can only tell you so much. What was needed was genetic evidence, direct comparison of DNA from Neanderthal remains and modern humans. But extracting DNA from ancient bones is incredibly difficult. DNA degrades over time, breaking into smaller and smaller fragments. Contamination from modern sources is a constant problem. For years it seemed impossible. Then, in the early 2000s, a team led by Svante Pääbo at the Max Planck Institute in Germany began making progress. They developed techniques for extracting and sequencing tiny amounts of degraded DNA from Neanderthal bones. It was painstaking work, fraught with technical challenges and false starts. But slowly, the Neanderthal genome began to emerge. The first complete sequence was published in 2010. Researchers compared it to genomes from modern humans around the world. The results were unambiguous. Non-African populations carried between 1 and 2% Neanderthal DNA. African populations, whose ancestors never left the continent, and thus never encountered Neanderthals, carried essentially none. This meant that interbreeding had occurred, most likely in the Middle East around 50 to 60,000 years ago, before modern humans had fully dispersed into Europe and Asia. The descendants of those hybrid offspring carried Neanderthal genes with them as they spread across the globe. Further analysis revealed which specific genes had been inherited. Some Neanderthal variants are found in genes related to skin and hair, suggesting they helped modern humans adapt to the colder climates and different UV levels of Eurasia. Others affect the immune system, providing resistance to local pathogens that the newly arrived modern humans would have encountered. Interestingly, some regions of the modern human genome are almost completely devoid of Neanderthal DNA. This suggests that certain Neanderthal variants were harmful when present in a modern human genetic background, and were selected against over time. Other regions show higher than average Neanderthal ancestry, indicating those variants were beneficial and spread through the population. The presence of Neanderthal DNA in living people today fundamentally changes how we think about human evolution. We are not a single lineage that replaced all others. We are a blended species, carrying genetic contributions from multiple archaic human groups. Neanderthals are not the only contributors. Denisovans, another archaic human group known primarily from DNA, extracted from a few bones found in Siberia, also interbred with modern humans. People in Southeast Asia and Oceania carry significant Denisovan ancestry. Other, as yet unnamed archaic groups probably contributed as well. The human family tree is not a simple branching diagram, but a braided stream, lineages separating and then reconnecting. This blending has practical consequences. Some Neanderthal genes influence your susceptibility to diseases like diabetes and Crohn's disease. Others affect your height, sleep patterns, and even mood. The variants inherited from Neanderthals are part of normal human variation today, neither universally good nor universally bad, but context-dependent. One of the most medically relevant findings involves the immune system. A cluster of Neanderthal genes on chromosome 3 is associated with a stronger inflammatory response to infections. This might have been advantageous during the Ice Age when exposure to novel pathogens was common, but in modern environments that same strong inflammatory response contributes to severe outcomes from diseases like COVID-19. Other Neanderthal variants affect skin tone and hair colour. Red hair and fair skin, common in northern European populations, may have been influenced by Neanderthal genes. This makes sense given that Neanderthals lived in high-latitude environments with low sunlight for hundreds of thousands of years, likely evolving lighter pigmentation to synthesize vitamin D more efficiently. The fact that we can identify specific Neanderthal genes and track their effects is remarkable. It turns abstract questions about interbreeding into concrete, testable hypotheses about human biology. It also personalizes the connection. If you are of non-African descent, you carry Neanderthal DNA. They are part of your ancestry, part of what makes you who you are. But how did this interbreeding occur? The genetic patterns suggest it was not an ongoing process throughout the period of overlap. Instead, most of the gene flow happened relatively early, perhaps in a few key events or periods of more extensive contact. After that initial mixing, the population seemed to have remained largely separate, with minimal additional gene flow. This pattern is consistent with a scenario where small groups of modern humans, freshly arrived in the Middle East, encountered and interbred with local Neanderthals. The descendants of those encounters then expanded into Asia and Europe, carrying Neanderthal genes with them. Later arrivals from Africa did not contribute as much to the modern gene pool, and thus did not dilute the Neanderthal ancestry already present. There is also evidence of gene flow in the other direction. At least one Neanderthal individual from the Altai Mountains in Siberia shows traces of modern human DNA, suggesting that a modern human ancestor contributed to Neanderthal populations as well. This was probably a rare event, but it demonstrates that gene flow was not entirely one way. The social implications of interbreeding are difficult to infer. Were these consensual relationships, forced encounters, isolated events, or part of broader social mixing? The genes cannot answer these questions. We can only imagine the individual stories behind the data. Perhaps some encounters were violent, a grim reality of prehistoric life where strength often determined outcomes. But others might have been based on mutual attraction, curiosity, or strategic alliance. Individuals choosing to join another group, forming relationships across the boundary that separated their peoples. In small populations, every successful reproductive event matters. A hybrid individual who survived to adulthood and had children of their own would pass on both Neanderthal and modern human ancestry. Over generations, those genes would spread through the population, eventually reaching frequencies where they would persist even after Neanderthals themselves disappeared. The genetic data also sheds light on Neanderthal population dynamics. The low genetic diversity in Neanderthal genomes suggests their populations were small and often isolated. Inbreeding was probably common, leading to accumulation of harmful recessive mutations. This made Neanderthals vulnerable to population crashes and less able to recover from setbacks. Modern humans, in contrast, had larger and more connected populations. Their genetic diversity was higher, providing more raw material for natural selection to work with. When modern humans arrived in Europe, they likely outnumbered Neanderthals significantly, and their numbers continued to grow while Neanderthal populations declined. But decline does not mean complete extinction. The genes persisted. In a very real sense, Neanderthals are still here, just not as a separate population. They have been absorbed into the modern human gene pool, their legacy visible in the DNA of billions of people. Recent advances have allowed researchers to sequence DNA from even more ancient Neanderthal remains, pushing the timeline back. We now have partial genomes from Neanderthals who lived over 100,000 years ago. These ancient genomes show that Neanderthal populations changed over time, just as all populations do. They were not static or unchanging, but dynamic, adapting to shifting climates and environments. Some researchers have even attempted to identify specific Neanderthal genes related to cognitive function. This is controversial and technically challenging, but early results suggest that some Neanderthal variants and genes related to brain development might have subtle effects on modern human cognition. What those effects are, and whether they are beneficial, neutral or harmful, remains unclear. What is clear is that the genetic legacy of Neanderthals is woven into the fabric of modern humanity. Every time you get a vaccine and your immune system responds, Neanderthal genes might be playing a role. Every time you step outside and your skin responds to sunlight, ancient adaptations to Ice Age Europe might be influencing that response. This is evolution in action, not as an abstract process, but as a living reality. We are the product of countless encounters, exchanges and minglings. Our ancestors did not exist in isolation, but interacted with other human groups, learning from them, competing with them, and sometimes creating children with them. The story of Neanderthals and modern humans is not a story of replacement, but of integration. Two lineages, separated for 500,000 years, came back together. One continued as a distinct population, the other did not. But the boundary between them was never absolute, and the legacy of that boundary crossing is still with us today. The sun is setting over the Ice Age landscape one last time. 40,000 years have passed since the first modern humans arrived in Europe, and the world has changed beyond recognition. The ice has advanced and retreated multiple times. Entire species have gone extinct. Forests have grown and died and grown again, and somewhere in all that change, the Neanderthals disappeared. Not in a single catastrophic event, but gradually, population by population, until no pure Neanderthal groups remained. The last individual died alone or among their family, unaware that they were the final representative of a lineage stretching back hundreds of thousands of years. What would they have thought if they knew? Did they have any concept of their own uniqueness, their separateness from the other humans sharing their world? Or did they simply see themselves as people, doing their best to survive in a hard world, unaware that history would remember them as a footnote to someone else's story? We will never know their thoughts, but we know their legacy, in the genes of billions of people, in the tools they left behind, in the knowledge that humans are more diverse and more interconnected than we once believed. The Neanderthal story challenges simple narratives about human evolution. We are not the inevitable result of linear progress. We are not the sole survivors because we were superior in every way. We are the product of contingency, chance, and complexity. We survived in part because we absorbed others, because we were willing to interbreed and learn and adapt. Standing here at the end of this story, looking back across 40 millennia, certain truths emerge. The first is that we are all Africans ultimately. Our species evolved there, and even those populations that left and encountered Neanderthals carried African ancestry with them. The second is that we are all hybrids. No modern human is purely one lineage or another. We carry genes from Neanderthals, Denisovans, and probably other archaic groups we have not yet identified. The third truth is that the past is closer than we think. 40,000 years sounds like an immense span of time, but it's only about 2,000 generations. Your Neanderthal ancestors are not impossibly distant. They are part of your family tree, separated from you by less time than separates you from the earliest farmers or the first cities. What lessons can we draw from this? Perhaps simply this. Difference is not destiny. Neanderthals and modern humans were different in many ways, but not so different that they could not recognize each other as human, could not communicate or trade or form relationships. The boundary between us was permeable, not absolute. In our modern world, we obsess over differences. Nationality, ethnicity, language, religion. We divide ourselves into groups and then imagine those divisions are fundamental and unchangeable. But the story of Neanderthals and modern humans suggests that even groups separated by hundreds of thousands of years of independent evolution can come together, can share knowledge and genes and future. We are the inheritors of that ancient mixing. We carry Neanderthal genes not as a curiosity but as a living part of who we are. They influence our health, our appearance, our responses to the environment. They are not other, they are us. The archaeological sites where Neanderthals once lived are now tourist destinations, museums, protected monuments. The caves where they sheltered from Ice Age storms now have walkways and lights, and placards explaining what was found there. The bones carefully excavated and studied, the tools catalogued and displayed. It is easy to see these remains as artifacts, dusty relics of a distant past. But they were lives, people who felt cold and hunger and joy, who loved their children and mourned their dead, who watched the seasons change and hoped for better days, who were, in the most fundamental sense, human. Their disappearance as a distinct population is a loss, a reduction in human diversity that cannot be undone. But their persistence in our genes is a gift, a contribution that continues to shape humanity. We are richer for their existence, more complex and interesting because they were part of our story. Science continues to uncover new details. Every year brings fresh discoveries, new sites excavated, new techniques applied to old bones. The picture becomes clearer and more nuanced. We learn that Neanderthals were artists, that they cared for the disabled, that they adapted to diverse environments from the Mediterranean to the Arctic. We learn that our interactions with them were more extensive and more complex than previously thought. But some mysteries remain. We still do not fully understand why Neanderthals disappeared when they did. Climate stress, competition, disease, absorption into modern human populations, all played roles, but the relative importance of each is still debated. We do not know what their language sounded like, what stories they told, what they believed about the world. These gaps in our knowledge are frustrating but also humbling. The past is not fully knowable. We do our best with the evidence we have, but there are limits to what bones and stones can tell us. The inner lives of Neanderthals, their hopes and fears and dreams, are lost to time. What we can do is honour their memory by telling their story as honestly as we can. Not as brutish primitives overcome by superior invaders, not as noble savages living in harmony with nature, but as people, complex and capable, doing their best in a challenging world. And we can recognise that their story is our story. When you look in the mirror, you might see echoes of Neanderthal ancestry in your features. When you fight off an infection, Neanderthal genes might be helping your immune system respond. When you stand in the cold and your body adapts, ancient evolutionary innovations forged in Ice Age Europe might be at work. You are connected to them. Not metaphorically, but literally. The same molecules that made up their bodies were passed down through countless generations and now make up yours. You are the continuation of their story, the living proof that they existed and mattered. As you drift off to sleep tonight, my tired potatoes, think about those ancient humans standing under the same stars you see, facing challenges you can barely imagine. They survived long enough to contribute to your existence. They were resilient, adaptable, human in all the ways that matter. And remember that human evolution is not finished. We are still changing, still adapting, still mixing genes across populations. The boundaries we draw between groups are temporary, always shifting. We are one species, spread across the globe, carrying the legacy of everyone who came before. The story of Neanderthals and modern humans is a story about contact and mixing, about the permeability of boundaries, about the complex ways that evolution actually works. It is a story that invites humility about our own place in history. We survived, yes. But that survival was not inevitable, and it came with costs and compromises and debts to those who came before. So tonight, as you close your eyes and let the day's worries fade, spare a thought for those ancient people of the Ice Age, for the Neanderthals who walked these lands for 200,000 years, for the first modern humans who ventured north into unknown territory, for all those who met and mingled and created the lineage that led to you. Their world is gone, the ice has melted, the mammoths are extinct, the caves are empty, but they live on in you, in the genes you carry and the story you continue. You are their legacy, their contribution to the future, and that is a remarkable thing to be. Sleep well, knowing you are connected to a story that spans hundreds of thousands of years and thousands of generations. You are part of something vast and ancient and ongoing. You are the inheritors of Neanderthal and modern human, of African and Eurasian, of everyone who survived long enough to contribute to the chain of life that leads to this moment. If you enjoyed this journey through Ice Age Europe, please follow us for more bedtime stories about the people who came before us. Tomorrow we will explore another chapter of our shared past, another story of survival and adaptation in a world very different from our own. Until then, rest well. "20,000 years ago, during the height of the last ice age, vast grasslands stretched across continents where forests and cities would later rise. These were the mammoth steppes, cold and windswept plains where survival meant understanding every plant, every stone, and every shift in the weather. Today, you will spend one full day living as your ancestors did, moving through the rhythms of Ice Age life from dawn until the stars appear. You wake before sunrise in a world wrapped in blue twilight. The air inside the shelter tastes sharp and clean, carrying the faint scent of smoke from last night's fire. Your breath forms small clouds that drift upward toward the curved ceiling of mammoth hide stretched over a framework of bones and branches. The ground beneath you feels firm, layered with dried grasses and the soft pelts you've carefully arranged for warmth. Outside, the wind moves across the steppe with a sound like distant conversation. You lie still for a moment, listening to the particular quality of that wind. It comes from the north today, steady rather than gusting, which means the weather will hold. This matters more than almost anything else in your world. The hide door covering the entrance glows faintly as dawn approaches. You can see the dark shapes of other shelters nearby, round structures that look like small hills against the pale grass. Smoke rises from one of them, a thin grey line that tells you someone else has already revived their fire. The sight brings a small measure of comfort. You are not alone on this vast plain. You push aside your sleeping furs and sit up slowly. Your body knows the cold, expects it, and has learned to move in ways that preserve warmth. The deerskin tunic you wore to sleep is already layered over your caribou hide leggings. Everything you own serves multiple purposes. Nothing is wasted in this place. The fire pit at the centre of the shelter holds only grey ash and a few dark fragments of charred wood. You spent the last of yesterday's fuel keeping warm through the night. This means your first task is already decided for you. The day begins with fire, as most days do. You gather a small bundle of dried grass from the supply you keep near the entrance. The grass crackles softly in your hands, releasing a dusty smell that reminds you of a late summer. You arrange it carefully in the fire pit, building a small nest with a hollow centre. Beside this you place thin twigs of willow, each no thicker than a finger, crossed at angles that allow air to flow beneath them. From a leather pouch hanging on the wall you take 2 stones. One is a piece of flint, grey and glassy, with edges you've shaped yourself. The other is a chunk of iron pyrite, heavy and golden brown. These stones have created fire for you hundreds of times. You know exactly how to hold them, where to strike, and what angle produces the best spark. You position the flint above the grass nest and strike it sharply with the pyrite. The first strike produces nothing. The second sends a small orange spark into the air, bright but too brief to catch. The third strike is different. The spark lands directly in the centre of the grass nest and begins to glow. You lean close, so close your face feels the tiny warmth, and breathe gently onto the ember. The grass catches with a whisper of flame. Yellow light fills the shelter, dancing across the curved walls. You feed the infant fire with more grass, then add the thin willow twigs one at a time. The flames grow taller, stronger, beginning to crackle with real authority. You feel your shoulders relax slightly. Fire means warmth, safety, the ability to cook food and keep predators at a distance. Fire is the difference between surviving and merely enduring. As the fire establishes itself, you add thicker branches, pieces of dry pine and birch you gathered days ago and stored in a pile near the wall. The pine releases a sweet resinous smell as it burns. The birch bark catches quickly, curling and blackening, adding its own sharp scent to the warming air. You arrange the larger pieces carefully, creating spaces for air to flow, ensuring the fire will burn steadily while you prepare for the day ahead. Light now fills the shelter completely. You can see every detail of your small home. The walls are made from mammoth hide, thick and waterproof, sewn together with sinew thread. The framework beneath consists of mammoth ribs and leg bones, collected from carcasses found on the steppe, arranged to create a dome shape that sheds wind and rain. At the highest point, a small opening allows smoke to escape. The floor is packed earth, covered with layers of dried grass and animal hides that provide insulation from the frozen ground below. Along the walls, you've arranged your possessions with care. Baskets woven from willow bark hold dried berries, roots, and strips of preserved meat. Stone tools hang from bone pegs, each one shaped for specific tasks. Leather bags contain materials for making thread, sewing needles carved from bone, and scraps of hide waiting to be worked. A row of clay pots, each formed by hand and fired in coals, holds water, fat, and precious ochre pigment. Everything has its place. Organisation is another form of survival. You stand and move to the entrance, pushing aside the heavy hide door. Cold air rushes in, fresh and bracing, carrying the smells of grass and distance. The sun is rising now, turning the eastern sky from grey to pale gold. The steppe stretches away in every direction, rolling grassland that seems to have no end. In the distance, you can see a small herd of horses moving slowly across the plain, dark shapes against the dawn light. Farther still, barely visible, a group of mammoths feeds on the tough grass, their curved tusks catching the early sun. This is your world. Vast, cold, beautiful in its own harsh way. The Ice Age steppe provides everything you need to live, but it requires constant attention, constant work and respect for the power of nature in its most raw form. Today, like every day, you will gather what the land offers, craft what you need, and maintain the knowledge that keeps you alive. The wind touches your face, cold, but not bitter. The sky holds no threat of storms. It is a good day to work, to move across the land, to collect the materials that make survival possible. You turn back to the shelter, add 2 more branches to the fire and prepare yourself for the tasks ahead. The sun climbs higher as you set out from the shelter, walking east across the steppe with a large basket woven from grass and willow bark. The basket hangs from a leather strap across your shoulder, bumping gently against your hip with each step. In your other hand you carry a digging stick, a sturdy length of hardwood sharpened to a point and fire-hardened at the tip. This simple tool will help you unearth roots and pry stones from the soil. The grass underfoot is coarse and silvery, adapted to cold and drought. It grows in dense tufts separated by patches of bare earth. As you walk, small birds rise from the grass ahead of you, tiny brown shapes that dart away with sharp, chirping calls. The sound is cheerful, a reminder that life thrives here despite the cold. Your first goal is a grove of willow trees that grows along a small stream about 2,000 paces from your shelter. The willows are precious, providing flexible branches for weaving, inner bark for cordage, and twigs that burn hot and clean. You visited this grove many times, always taking only what you need, never stripping a single tree completely. The willows grow back quickly if treated with respect. As you walk, you scan the ground for useful stones. The steppe is littered with rocks of all sizes, carried here by ancient glaciers and deposited across the grassland. Most are ordinary granite or basalt, but occasionally you find flint, chert, or the golden brown pyrite that makes fire. Every stone has potential uses. Some can be shaped into cutting tools, others work well as hammerstones or grinding surfaces. The largest can be arranged to create hearths or support structures. You spot a piece of flint half buried in the soil. It's roughly the size of your palm, grey, with bands of lighter colour running through it. You kneel and work it free with your digging stick, brushing away the dirt to examine it more closely. The flint has good texture, fine-grained and glassy. It will flake cleanly when struck. You place it carefully in your basket. 100 paces farther, you find a fist-sized chunk of quartzite, hard and pink-tinted. This stone is too tough to shape into cutting tools, but it makes an excellent hammerstone for knapping flint. You add it to your collection. The stream appears ahead, a bright line of water cutting through the grass. Willows grow along both banks, their narrow leaves rustling in the breeze. The trees are still small, none taller than twice your height, but their branches are numerous and flexible. You approach the nearest tree and select several young shoots growing from the base. These shoots are about as thick as your thumb and perfectly straight. You take out a flint blade and cut them close to the ground, making clean cuts that won't damage the tree. The willow branches smell green and alive, even in this cold climate. You trim away the small side twigs and add the cleaned branches to your basket. These will be soaked in water to make them even more pliable, then woven into new baskets, or used to repair the framework of your shelter. Near the water's edge, you notice a stand of cattails growing in the shallow margin of the stream. The cattails are in seed now, their brown cylindrical heads full of fluffy material that can be used for tinder, stuffed into clothing for insulation, or woven into mats. You wade into the cold water, feeling it seep through your hide boots, and gather several cattail heads. The fluff inside is dry despite the plant's wet location. You wrap the heads in a piece of leather to keep them safe. The stream itself provides another resource. Along its banks you find smooth stones worn round by water. These water-polished rocks are useful for grinding pigments, processing hides, and smoothing wooden tool handles. You select 3 stones of different sizes, each fitting comfortably in your hand, and add them to your growing collection. As you work, a family of ground squirrels watches from the far bank. They sit upright on their haunches, whiskers twitching, clearly curious about your activities. One of them makes a high-pitched chirping sound, possibly a warning to the others. You smile at their caution. These small creatures are also gathering food, storing seeds and roots in underground burrows to survive the winter ahead. In a way, you're doing the same thing, though your methods are more complex. You follow the stream northward, looking for a specific plant you know grows in this area. After searching for perhaps 500 paces, you find what you're seeking. A patch of wild onions grows near a bend in the water, their tubular leaves rising from the soil. You kneel and use your digging stick to carefully extract several bulbs. The onions are small, each no larger than a walnut, but they are pungent and flavourful. They will add taste to tonight's meal and provide nutrients your body needs. The soil here is darker and richer than the dry ground of the open steppe. You dig deeper, searching for other edible roots. Your stick strikes something firm. You work carefully around it and unearth a burdock root, long and pale brown. The root is the length of your forearm and as thick as 2 fingers. Burdock can be roasted in coals or boiled in water. It has a slightly sweet taste and fills the belly. You brush the soil from the root and add it to your basket. The sun is higher now, warm on your face despite the cool air. You estimate the morning is half over. Your basket is beginning to feel heavy, which means you've gathered well. But there is one more thing you want to find before returning to the shelter. You leave the stream and walk toward a rocky outcrop visible in the distance. This outcrop rises from the steppe like a small island of stone, its weathered surface covered with lichen. You know from experience that certain kinds of flint can be found near such rock formations, exposed by erosion and easy to spot against the pale lichen. The walk takes longer than expected. The outcrop is farther than it appeared. This is the way of the steppe, where distances are hard to judge on the flat land. But the walking is pleasant, and you enjoy the rhythm of your footsteps, the whisper of grass, the vast openness of the sky overhead. When you finally reach the outcrop, you begin searching the base of the rocks. Lichen crunches under your feet, releasing a dry, powdery smell. You move slowly, examining every shadow, every crevice. Then you see it. A nodule of black flint, roughly the size of a goose egg, lying against the base of a large boulder. The flint is nearly perfect, with no visible cracks or flaws. This is a prize worth carrying. You pick up the nodule carefully, feeling its weight, admiring its smooth surface. This piece of stone represents future tools. In your hands, with patience and skill, it will become scrapers, blades, points for spears. The transformation from raw stone to functional tool is a kind of magic you understand deeply. With this final find, your basket is full. The weight pulls pleasantly on your shoulder as you turn back toward home. The return journey feels shorter, perhaps because you walk with purpose, carrying the fruits of your morning's work. As you near your shelter, you see smoke rising from several fires. Other people are awake and active now, beginning their own daily tasks. A child runs between the shelters, laughing at some private game. The sound is bright and unexpected in this austere landscape. It reminds you that humans bring more than just survival to this place. They bring joy, creativity, and the determination to thrive even in difficult conditions. You duck through the entrance of your shelter, glad for the warmth inside. The fire has burned down to glowing coals. You add fresh wood, and the flames rise again, welcoming and familiar. You empty your basket carefully, arranging each item in its proper place. The stones go in one corner. The willow branches lean against the wall. The cattail heads rest in a dry basket. The roots and onions are placed near the food storage area. You stand back and survey your morning's work. These materials represent more than objects. They represent possibility, preparation, and the continuation of life on the steppe. Tomorrow, or the next day, you will transform these raw materials into things you need. But for now, it is enough to have gathered them, to know they are here, ready when you need them. The midday sun fills your shelter with light that angles through the smoke hole and glows orange through the mammoth hide walls. You settle yourself on a flat rock near the fire, arranging your stoneworking tools around you. The large nodule of black flint sits before you like a challenge and a promise. Toolmaking requires patience, focus, and an understanding of how stone breaks. You have spent years learning these skills, beginning as a child who watched the adults work, progressing through countless mistakes and small successes until the knowledge lived in your hands as much as your mind. Today, you will create several tools that your household needs. You begin by examining the flint nodule from every angle, turning it slowly in your hands, feeling its weight and balance. The surface is smooth, covered with a pale, chalky cortex that must be removed to reach the workable stone beneath. You look for the grain of the flint, the subtle ways that indicate how it will fracture when struck. This is not random. Stone has an internal structure, and working with that structure rather than against it is the key to successful knapping. You select your hammerstone, the piece of quartzite you found earlier. It fits your hand perfectly, heavy enough to deliver force but small enough to control precisely. You hold the flint firmly in your left hand, supporting it on your leather-covered thigh. The leather will protect your leg from sharp edges and flying flakes. The first strike is always important. You aim for a spot near the edge of the nodule and bring the hammerstone down with controlled force. The impact makes a sharp crack. A large flake splits away from the nodule, exposing the glossy black interior of the flint. The flake itself is useless, but it has opened up the stone, giving you access to the workable material inside. You continue striking, working your way around the nodule, removing the cortex in large rough flakes. Each strike requires judgment. Too hard and the stone might shatter. Too soft and nothing happens. The right force, applied at the right angle, produces clean, predictable breaks. The rhythm develops naturally. Strike, turn the stone, strike again. Flakes pile up around your feet, sharp and glittering. After perhaps 20 strikes, you've reduced the nodule to a smaller core of pure black flint, roughly oval in shape. This core is your platform for creating usable tools. Now the real work begins. You set aside the heavy hammerstone and pick up a softer striker made from a piece of antler. Antler is gentler than quartzite, allowing for more controlled flaking. You will use this to remove thin, sharp flakes from the core, each one a potential cutting tool. You position the antler striker carefully and strike a blow near the edge of the core. A long curved flake peels away cleanly. The flake is about as long as your hand and sharp along both edges. You examine it closely. The edge is keen enough to slice hide or meat with minimal pressure. This flake will become a scraper for processing animal skins. You continue working the core, removing flakes of various sizes. Some are long and narrow, good for cutting. Others are broader and thicker, suitable for scraping or chopping. Each flake that comes away is examined and set aside for later use or discarded if it has flaws. The pile of potential tools grows steadily. The work is meditative. Your hands move with practiced certainty. Your mind enters a focused state where only the stone exists, its possibilities and limitations, the precise angle of each strike, the subtle feedback that tells you when the fracture is going well or poorly. Outside, the wind continues across the steppe. Inside, there is only the quiet percussion of stone against stone. After removing perhaps 15 usable flakes, you select one for further shaping. This flake is about the length of your palm, narrow and gently curved. It will become a knife blade, but first it needs refinement. The edges are sharp but irregular. You need to create a straight, consistent cutting edge. You switch to an even softer tool, a piece of hardwood carved into a point. This pressure flaker allows you to remove tiny flakes from the edge of the larger flake, shaping it precisely. You hold the blade to be in your left hand, wrapped in leather for protection, and press the wooden point against the edge. With controlled pressure and a slight twisting motion, a tiny flake pops off. The edge is now slightly straighter. You work your way along the edge, removing microscopic flakes, each one improving the line and sharpness. This process is called pressure flaking, and it transforms a rough piece of stone into a finished tool. The work is slow and exacting. Your eyes are drawn close to the stone, watching each tiny fracture. Your fingers feel the edge becoming keener, more refined. After perhaps 30 careful pressure flakes, the blade is ready. You test it by drawing the edge across a scrap of leather. The stone cuts through the hide with almost no resistance, leaving a clean straight line. You've created a knife worthy of the most delicate work. You set the finished blade aside and select another flake from your pile. This one is broader and thicker, good for scraping rather than cutting. You shape it differently, creating a rounded working edge rather than a sharp point. This scraper will be used to clean fat and tissue from animal hides, an essential step in making leather. The scraping edge needs to be durable rather than hair sharp, so you leave it slightly thicker, less acute. The afternoon passes in this focused work. The pile of finished tools grows, a knife blade, 2 scrapers of different sizes, a pointed awl for piercing holes in leather, and a small graver for carving designs into bone. Each tool is shaped for its specific purpose. Each one represents a problem solved, a need met. As you work, you think about the generations before you who learned this craft, who developed these techniques through experiment and observation, and who passed the knowledge forward. Toolmaking is not instinct. It is learned behaviour, cultural knowledge that must be taught and practiced. The fact that you can sit here and create these precise implements from raw stone is the result of thousands of years of accumulated understanding. This thought brings a sense of connection to those ancient teachers, a feeling that you are part of something larger than yourself. The fire burns low. You add more wood and blow gently on the coals. Flames rise again, casting dancing shadows on the shelter walls. The light catches on the pile of stone flakes scattered around you, making them glitter like scattered stars. You gather the finished tools and arrange them carefully on a piece of hide. Tomorrow you will haft some of them into wooden handles, binding the stone to wood with sinew and pine pitch. Others will be used as they are, held directly in the hand, but for now they are complete, ready to serve their purposes. The remaining core of flint is smaller now, but still useful. It will provide material for future tools. You wrap it in leather and place it with your other stone reserves. Nothing is wasted. Even the smallest flakes can be used for cutting tasks or as scrapers for detailed work. You sweep the sharp debris into a pile and carry it outside, disposing of it away from the areas where people walk. Stone flakes are dangerously sharp, capable of cutting through hide boots or slicing skin. Proper disposal is a matter of safety. Back inside, you sit by the fire and clean your hands, brushing away the stone dust and tiny particles. Your fingers are marked with small cuts from the day's work, tiny lines of red against your skin. These are the marks of a craftsperson, badges earned through concentration and skill. They will heal quickly and leave no scars. The shelter feels warm and secure. Outside, the day is moving toward evening, but you have more work ahead before darkness falls. Fire is the heart of survival in this cold land. Without it, nights would be unbearable. Food would remain raw and hard to digest, and predators would venture much closer to your dwelling. Maintaining fire is not simply a task. It is a responsibility that runs through every day like a thread through fabric. Your fire has burned steadily since dawn, fed with wood throughout the day. But fire requires more than fuel. It needs attention, understanding, and respect. A neglected fire dies quickly. A poorly managed fire consumes too much wood or produces choking smoke. A well-tended fire burns clean and hot, using fuel efficiently, providing warmth and cooking heat exactly when needed. You kneel beside the fire pit and study the current state of the flames. The wood has burned down to a bed of glowing coals mixed with ash. This is actually ideal for many purposes. Coals provide steady, sustained heat without the dramatic flames that consume fuel rapidly. You will cook on these coals later, but first, you need to ensure you have enough firewood for the coming night. The wood pile near the wall is diminished. You count perhaps 10 branches remaining, enough for a few hours but not enough to last until morning. Gathering firewood is a constant necessity, one that cannot be postponed or forgotten. You take up a leather carrying sling and head outside. The sun is lowering toward the western horizon, painting the sky in shades of amber and pale rose. The temperature is dropping as evening approaches. You can feel the change in the air, a subtle shift that your body reads automatically. Your destination is a stand of dead trees about 1,000 paces to the south. These trees died years ago, killed by fire or disease, and now they stand as weathered skeletons, their wood dried perfectly for burning. Dead standing wood is far superior to branches gathered from the ground. Groundwood absorbs moisture from the soil and burns poorly, producing more smoke than heat. Standing dead wood is dry all the way through, burning hot and clean. As you walk, you notice how the angle of light transforms the step. The grass that appeared silver at dawn now glows golden. Shadows stretch long and dramatic across the land. The distant mountains, invisible at midday, are now visible as blue silhouettes against the sky. This is the time of day when the harsh landscape reveals unexpected beauty. The dead trees stand in a small grove, 6 tall trunks reduced to bare poles with scattered dead branches. Some of the branches have already fallen, littering the ground around the trees. Others still cling to the trunks, dried and brittle. You select the branches that are elevated off the ground, but loose enough to break free with moderate force. You reach up and grab a branch about as thick as your wrist. It's light, much lighter than living wood, evidence of how thoroughly it has dried. You pull down and the branch breaks free with a satisfying crack. The wood is pale grey, worn smooth by years of weather. You break the branch into manageable lengths by bracing it against your knee and applying pressure. Each piece is about the length of your arm, sized to fit easily into your fire pit. You continue gathering, working methodically through the available deadwood. Some branches are too rotted, crumbling to powder in your hands. You leave these. Others are solid and sound despite their age. These go into your carrying sling. The work is physical but not difficult. Your body is accustomed to such labour. A sound makes you pause. Somewhere in the distance are mammoth trumpets, the call carrying across the empty space. You look toward the sound and see a herd moving slowly westward, dark shapes against the golden grass. The mammoths are enormous even at this distance, their curved tusks visible as graceful arcs. They are travelling to their feeding grounds, following routes they have used for generations. You watch them for a moment, feeling a mixture of awe and familiarity. Mammoths are part of the fabric of this world. They provide ivory for tools, hides for shelter, meat for food. But they are also dangerous, massive creatures that can crush a human without even noticing. Respect and caution are the appropriate responses to such animals. The mammoths move on, disappearing beyond a low rise. You return to your wood gathering. When the carrying sling is full, you shoulder the load and start back toward your shelter. The wood is bulky but not heavy. It rustles and shifts as you walk, settling into the sling. Back at your dwelling, you stack the new firewood carefully near the entrance, arranging it so air can circulate around each piece. Proper storage keeps wood dry and ready to burn. Damp wood produces smoke and wastes effort. You return to the fire pit and consider the current state of the coals. They have begun to fade, the bright orange dulling to red. This is the time to add fresh fuel. You select 3 pieces of the newly gathered wood and place them on the coals in a careful arrangement. The pieces are positioned to allow airflow beneath them, creating channels for oxygen to reach the burning coals. Within moments, thin wisps of smoke rise from the wood. The smoke thickens, turning white and substantial. Then, with a soft whoosh, flames appear. The dried wood catches quickly, burning with clean yellow flames that grow rapidly in size and intensity. Heat radiates outward, warming your face and hands. Fire is more than combustion, it is transformation. Wood becomes heat, light, smoke, and ash. The process is both practical and somehow magical, a taming of one of nature's most powerful forces. Every time you light a fire or coax flames from coals, you are participating in knowledge that humans discovered tens of thousands of years ago. The techniques you use were learned by trial and error by people whose names are lost to time, but whose discoveries made civilization possible. You add 2 more pieces of wood, building the fire to a size that will produce lasting coals. The shelter fills with warmth and the pleasant smell of burning pine. Light dances on the curved walls, creating an atmosphere that feels safe and enclosed despite the vast cold world outside. As the fire stabilizes, you prepare for an important task. Creating fire from nothing, without the benefit of existing coals, is a skill you practice regularly. If your fire ever goes completely out and no one nearby can share their coals, you must be able to create flame using only materials found on the steppe. You gather the necessary items: a flat piece of wood, dry and sound, which will serve as the fireboard, a straight stick of slightly harder wood, which will be the drill, a curved piece of bone with a smooth depression carved in one end, which will hold the top of the drill, a bow made from a flexible branch with a leather thong stretched between the ends, and a small pile of dried grass and tinder, ready to catch the first ember. The technique is called bow drill firemaking. It uses friction to create heat, and heat to create an ember. The process requires technique, endurance, and favourable conditions. Even with experience, success is not guaranteed. You carve a small notch in the edge of the fireboard, creating a collection point for the hot wood dust that the friction will produce. You place the fireboard on the ground and brace it with your foot. The drill stands upright on the fireboard, its top end fitted into the socket carved in the bone. The bowstring is wrapped once around the drill shaft. You position yourself carefully, one knee on the ground, the other foot bracing the fireboard. You press down gently on the bone socket with your left hand while moving the bow back and forth with your right. The drill begins to spin, rotating first one direction, then the other. Smoke appears almost immediately where the drill point touches the fireboard. This is good. Smoke means friction, and friction means heat. You increase your speed, moving the bow faster, pressing down harder. More smoke rises, thicker now, with a sharp smell of burning wood. Your arm begins to feel the effort. The bow drill method demands sustained physical work. You cannot stop or slow down once the process has begun. The heat must build continuously until it reaches the point where wood dust becomes ember. Sweat forms on your forehead despite the cool air. Your arm aches, but the smoke is pouring from the friction point now, dense and consistent. You can feel the heat building, just a little longer. You make one final strong effort, moving the bow as fast as possible, pressing down hard. Then you stop, carefully lifting away the drill. In the notch of the fireboard, you see a tiny pile of dark brown wood dust, smoking vigorously. And at the centre of that dust, a pinpoint of orange, an ember. You carefully tip the ember onto a piece of bark and transfer it to the waiting nest of dried grass. You bring the nest close to your face and blow gently. The ember glows brighter. The grass begins to smoke. You blow again, more strongly. Suddenly the grass bursts into flame. You have created fire from nothing but wood, friction, and knowledge. The triumph is quiet but real. Even though you have a perfectly good fire burning in the pit, even though you used flint and pyrite to start it this morning, the ability to create flame with the bow drill is essential knowledge. It is a backup system, a guarantee that you will never be helpless as long as you have access to wood and grass. You let the grass fire burn out naturally, watching the flames consume the fuel in seconds. The demonstration is complete. Your skill is confirmed. Tomorrow or a year from now, if you need this technique, your hands will remember. The main fire burns steadily, filling the shelter with warmth. Evening is settling over the steppe outside. Soon it will be time to prepare food. But the fire is ready, burning clean and hot, exactly as it should. Your shelter has protected you through many seasons, but like all things made by human hands, it requires constant maintenance. The mammoth hide walls are durable, but wind and weather take their toll. The framework of bones and branches can shift or loosen. Small gaps can appear where cold air seeps through. A shelter neglected becomes a shelter failed. Before the day ends, you make a circuit around the outside of your dwelling, examining every section carefully. The hide walls are held in place by a combination of bone stakes driven into the ground and leather thongs tied to the framework beneath. You test each stake, pushing against it to ensure it remains firm. Most are solid, but two have worked slightly loose. You drive them deeper into the earth using a heavy stone as a hammer. One section of hide near the entrance shows signs of wear. The material has developed a small tear where it rubs against a bone support. You examine the damage closely. The tear is not large, perhaps the length of your finger, but it will grow if not repaired. Water could seep through. Cold air could penetrate. You return inside and retrieve your sewing kit. The kit consists of several bone needles of different sizes, each one carefully carved and polished, with an eye drilled through one end. You also take a length of sinew thread, pulled from the dried tendons of a deer you processed weeks ago. The sinew is strong and flexible, perfect for sewing heavy hide. Back outside, you thread the needle with sinew. The light is fading now, but enough remains to work by. You begin stitching the tear closed, using a technique passed down through generations. The stitches are small and tight, pulled firmly but not so tight that they cut through the hide. Each stitch overlaps the previous one slightly, creating a waterproof seam. The work is precise and satisfying. Your fingers know the motion without thinking. Push the needle through the thick hide, pull it out the other side, loop the thread, repeat. The rhythm is meditative, similar to the rhythm of napping stone. Both activities require focus, patience, and respect for materials. As you work, you think about the mammoth whose hide forms your walls. The animal died years before you were born, killed by hunters from a neighbouring group. The hide was traded for tools and dried meat. It has served as shelter ever since, protecting multiple families from rain, snow and wind. The mammoth's body transformed into houses, tools, fuel and food. Nothing of that great animal was wasted. This is the way of the steppe. Everything serves a purpose. The repair complete, you tie off the sinew thread and trim it close to the hide. The tear is now invisible unless you know where to look. The wall is whole again, ready for whatever weather comes next. You circle the shelter once more, this time from the inside. The framework overhead is a lattice of mammoth bones interwoven with willow branches, all lashed together with sinew and strips of hide. You check each connection point, tugging gently to test the bindings. Most are solid, but one shows signs of fraying. The sinew has begun to split, weakened by exposure to smoke and moisture. You untie the damaged binding and replace it with fresh sinew from your supplies. The new binding is wound tightly, crossing and recrossing to create maximum strength. You tie it off with a knot that will not slip or loosen. The framework is secure again. The floor of the shelter also needs attention. The layer of dried grass that provides insulation from the frozen ground has compressed over time, losing its effectiveness. You gather fresh grass from a pile you've kept dry near the entrance and spread it evenly across the floor, especially in the sleeping area. The new grass is springy and resilient, creating a softer, warmer surface. You arrange your sleeping furs over the fresh grass, testing the comfort. Much better. The smoke hole at the peak of the shelter requires regular adjustment depending on wind direction and fire intensity. Today the wind comes from the north, so you shift the position of the hide flap that partially covers the opening, angling it to allow smoke to escape while preventing rain or snow from entering. Getting this balance right is an art learned through experience. A good shelter is more than just walls and a roof. It is a system of interconnected elements, each one affecting the others. The fire produces smoke that must escape through the smoke hole. The smoke hole must be positioned to prevent rain entry. The hide walls must be tight enough to keep out wind but must allow some air circulation to prevent the build-up of moisture. The framework must be strong enough to support the weight of the hides and resist wind pressure. Every element must work in harmony. You step back and survey your dwelling with critical eyes. The walls are sound, the framework is secure, the floor is fresh, the smoke hole is properly adjusted, the entrance hide hangs smoothly, creating a good seal when closed. The shelter is ready for the night ahead, and for many nights to come. Shelter building is knowledge that must be learned and practiced. The skills involved are numerous and complex. Choosing the right location, one with good drainage and protection from prevailing winds, gathering and preparing materials, designing a structure that will shed rain and resist wind, constructing a framework strong enough to support the weight of heavy hides, sewing the hides together into panels large enough to cover the frame, maintaining everything over time. No one learns all this overnight. The knowledge is passed down from experienced builders to novices, taught through demonstration and corrected through patient feedback. You learned these skills as a child, watching adults work, helping with simple tasks, gradually taking on more responsibility as your abilities grew. Now you maintain your own shelter with confidence, knowing that you can repair almost any problem that arises. As darkness falls completely, you return inside and seal the entrance hide behind you. The fire burns brightly, casting warm light throughout the space. Your shelter feels solid and secure, a small island of warmth and safety in the vast cold night outside. The wind can blow, the temperature can drop. Inside you're protected by knowledge, materials and the work of your own hands. Evening is the time for cooking, when the day's work is done and the fire burns steady and hot. Tonight's meal will be simple but nourishing, made from the materials you've gathered and the food you've preserved from earlier hunts and harvests. You begin by selecting a cut of dried meat from your stores. The meat is from a reindeer killed a week ago, cut into thin strips and hung near the fire to dry. Drying preserves meat by removing the moisture that bacteria need to grow. The strips are now hard and dark, reduced to about a third of their original weight. They will keep for months without spoiling. You take 3 strips and place them on a flat stone near the fire. Using your newly sharpened flint knife, you cut the dried meat into smaller pieces, each about the size of your thumb. The meat is tough, requiring pressure to cut through. This toughness is a sign of proper drying. Next, you retrieve the wild onions and burdock root you gathered this morning. The onions need only their outer layers removed before use. You peel them carefully, revealing the white bulbs inside. They smell strong and sharp, a scent that makes your mouth water. The burdock root requires more preparation. You scrape away the outer skin with a scraper, exposing the pale flesh beneath, then cut the root into thin rounds. You have a clay cooking pot, one you made yourself from river clay several seasons ago. The pot is round and simple, with thick walls and a wide mouth. It has no handles, but it sits stable when placed directly on hot coals. You pour water into the pot from a water skin. The water comes from the stream where you gathered willows, cold and clean. Cooking in water is one of humanity's great innovations. Before pots and fire, food could only be eaten raw or roasted directly over flames. Water cooking allows for gentler heat, better flavour, and the ability to combine many ingredients into a single dish. The invention of pottery changed everything. You place the pot carefully on the bed of coals at the edge of the fire pit. The clay immediately begins to warm. You add the pieces of dried meat to the water. As the water heats, the meat will rehydrate and soften, releasing its flavour into the liquid. Steam begins to rise from the pot's surface. While the meat cooks, you prepare other additions. You take a handful of dried berries from a basket, small purple fruits gathered last summer and sun-dried on flat rocks. These berries add sweetness and nutrition to the stew. You also grind a small amount of wild garlic using a grinding stone, creating a paste that will add flavour and help with digestion. The water in the pot is heating rapidly now, beginning to simmer. Small bubbles rise to the surface and burst. You add the onions, burdock berries and garlic paste. The ingredients settle into the bubbling water. The smell that rises with the steam is rich and complex, a combination of meat, onion and wild herbs. Cooking is partly science and partly intuition. You know from experience how long different ingredients need to become tender. Onions cook quickly. Burdock takes longer. Dried meat needs time to fully rehydrate. You judge by smell, by the appearance of the bubbling water, and by tasting small amounts as the cooking progresses. You add a pinch of salt, a precious substance traded from people who live near the distant sea. Salt enhances flavour and helps preserve food. You use it sparingly, making your limited supply last as long as possible. The stew bubbles gently, the liquid reducing slowly, concentrating the flavours. You stir occasionally with a wooden spoon carved from birch. Stirring prevents ingredients from sticking to the bottom of the pot and burning. While the meal cooks, you prepare flatbread using a technique you learned from a traveller who passed through several years ago. You take a small amount of ground seed flour, made from grass seeds you collected and ground between stones. You mix the flour with water to form a thick dough, adding just enough liquid to make it workable. The dough is dense and sticky, heavy in your hands. You shape the dough into a flat round, about as wide as your hand and as thick as your finger. You place this directly on a hot stone positioned near the fire. The stone has been heating for the past hour and is now hot enough to cook on. The flatbread sizzles when it touches the stone, releasing a toasted grain smell. The bread cooks quickly on one side, developing brown spots and a firm texture. You flip it with your fingers, working quickly to avoid burning yourself. The other side cooks just as fast. The finished bread is crispy on the outside and chewy inside, perfect for soaking up stew. The stew has been cooking for perhaps half an hour. The meat has softened and expanded, absorbing water and becoming tender again. The burdock is cooked through, slightly translucent. The onions have nearly dissolved, their flavour permeating the liquid. You taste a spoonful. The flavour is deep and satisfying, savoury with a hint of sweetness from the berries. You remove the pot from the coals using a scrap of leather to protect your hands from the heat. The clay is nearly hot enough to burn through the leather. You place the pot on a flat stone and let it cool slightly. This meal represents the convergence of many skills and much knowledge. Hunting to obtain meat, preserving the meat through drying, gathering wild plants and knowing which are edible, making pottery from clay, creating and maintaining fire, understanding cooking times and flavour combinations. Each element is essential. Remove any one and the meal becomes impossible or at least much less satisfying. You scoop stew into a wooden bowl, another item you carved yourself during a long winter. The bowl is smooth from use, worn to fit comfortably in your hand. You tear pieces from the flatbread and use them to soak up the rich liquid. The first bite is almost too hot, but you are patient. You eat slowly, savouring each mouthful. The food is fuel for your body, providing the energy and nutrients you need to continue surviving on the steppe. But it is also more than that. It is comfort, pleasure, and a reminder that life can be good even in harsh conditions. The flavours connect you to the land, to the plants and animals that sustain you, and to the accumulated knowledge that transforms raw ingredients into nourishment. As you eat, the fire crackles softly. Outside, night has fallen completely. The stars are emerging, thousands upon thousands of them scattered across the black sky. The temperature continues to drop, but inside your shelter, with food in your belly and warmth from the fire, you are content. This is what survival looks like when done well, not merely enduring, but living with competence, creativity, and gratitude. After the meal, as the fire burns low and comfortable, you prepare for one final task of the day. This task has no immediate practical value. It produces no food, creates no tools, and improves no shelter. Yet, it may be the most important work you do. You are going to practice passing on knowledge. In a world without writing, knowledge lives only in minds and hands. Everything you know about survival, every technique for making tools, lighting fires, finding food, and building shelter, exists because someone taught you. And that person was taught by someone else, reaching back through countless generations. The chain of knowledge is unbroken only as long as each generation successfully teaches the next. Tonight you will practice teaching even though no student is present. You do this regularly, speaking the knowledge aloud, reinforcing your own understanding, and preparing for the day when you will have young people to instruct. Speaking knowledge aloud helps you organise it, identify gaps, and find clearer ways to explain complex ideas. You settle by the fire and begin to speak, your voice quiet but steady in the enclosed space. You describe the process of making fire with flint and pyrite. Your hands move as you talk, demonstrating the grip, the angle of strike, the importance of having dry tinder ready. You explain how to recognise good flint by its glassy texture and conchoidal fracture. You describe the feeling of a successful strike, that particular sharp crack that means the spark will come. You move on to tool making. You explain how to read the grain of stone, how to predict where a flake will separate, how much force to apply for different materials. You demonstrate the difference between hard hammer percussion and soft hammer percussion. You describe the patience required for pressure flaking, the importance of taking time to examine the stone from every angle before striking. The words flow easily. You have thought about these processes so many times, performed them so often, that explanation feels natural. But you also notice places where your explanation stumbles, concepts that are difficult to put into words. These are the things that must be taught through demonstration, through the student attempting the task themselves under supervision, through repeated practice until the hands learn what the mind struggles to express. You talk about shelter construction. You explain how to select a building site with good drainage and protection from wind. You describe the process of creating a framework strong enough to support heavy hides. You detail the technique for sewing hides together with waterproof seams. You explain how to maintain proper ventilation while keeping out cold air. Some of this knowledge is seasonal. Building a shelter in spring requires different considerations than building in autumn. You explain these differences, describing how summer shelters can be lighter and more open, while winter structures must be heavily insulated and windproof. You discuss food gathering and preparation. You name the edible plants of the steppe, and describe where to find them at different times of year. You explain which parts of each plant are edible, and which must be avoided. You describe cooking techniques and food preservation methods. You talk about the importance of varying the diet, of eating different foods to obtain all the nutrients the body needs. The knowledge seems endless when you begin to list it all. Plant identification, animal tracking, weather prediction, tool making, fire building, shelter construction, food preparation, hide processing, cordage making, basket weaving, and countless other skills. Each skill has depth, nuance, and subtlety. Each requires practice to master. You pause and add more wood to the fire. The flames rise again, bright and warm. You think about the different ways knowledge can be taught. Some things are best learned through story, memorable narratives that embed practical information in an entertaining framework. Other things require direct demonstration and hands-on practice. Still other knowledge is passed through gentle correction, observing a student's work and offering suggestions for improvement. The most important thing, you realise, is patience. Learning takes time. Students make mistakes, forget steps, become frustrated. A good teacher expects this, accommodates it, and finds ways to make the learning process engaging rather than tedious. You speak about the values that underpin survival skills. Respect for materials, recognizing that everything on the step is finite and must be used wisely. Attention to detail, understanding that small errors in toolmaking or shelter construction can lead to failure. Persistence, the willingness to attempt difficult tasks repeatedly until skill develops. Observation, the habit of watching nature carefully, learning from the world itself. These values are as important as specific techniques. A person can know every step of firemaking but still fail if they lack patience. A person can understand shelter design but create a weak structure if they work carelessly. Skills and values must be taught together, woven into the same lessons. You also think about the knowledge that cannot be taught directly, the wisdom that comes only from experience. How to judge weather by the quality of light and the behaviour of animals. How to estimate distances on the open steppe. How to pace yourself physically to work all day without exhaustion. These things develop through years of living on the land. They can be pointed out, but they cannot be transferred directly. The fire has burned down to coals again. You let it settle naturally, knowing you will build it up once more before sleep. The shelter is warm and comfortable. Outside, the night is quiet except for the whisper of wind through grass. You have spent perhaps an hour speaking knowledge aloud, organising your thoughts, preparing yourself to be a teacher. The exercise has been valuable. You feel more confident about your ability to pass on what you know. When the time comes to teach actual students, you will be ready. But there is one more aspect of knowledge transfer to consider. Not all knowledge is practical. Some knowledge exists for its own sake. Stories about the stars, explanations for natural phenomena, traditions and customs that bind people together. This cultural knowledge is just as important as survival skills. It gives meaning to existence, connects individuals to their community and history. You look up at the smoke hole, visible as a small circle of darkness against the darker shelter ceiling. Through that opening, you can see a few bright stars. You know stories about those stars, tales passed down from grandparents and great-grandparents. Stories about hunters who became constellations, about animals that live in the sky, about the path souls take after death. These stories are not practical, but they matter. They comfort, inspire, and create shared understanding among people. They are part of what makes humans human, this need to explain, to narrate, to find ways and meaning in the chaos of existence. You resolve to remember the stories as carefully as you remember the technical skills. Both kinds of knowledge must be preserved and transmitted. Both shape the character of the people who live on the steppe. The day is ending. You have worked hard, accomplished much, and prepared yourself for the future. You are tired in a good way, the kind of tiredness that comes from purposeful activity. Tomorrow will bring new tasks, new challenges, but tonight you rest with the satisfaction of a day well spent. The final task before sleep is to prepare the fire for the night. A fire that burns too hot will consume all your fuel before morning. A fire that dies completely will leave you shivering in the cold. The goal is to create a bed of coals that will provide warmth throughout the night without requiring constant attention. You select several large pieces of hardwood from your fuel supply. Hardwood burns slowly and produces long-lasting coals. You arrange these pieces carefully in the fire pit, positioning them close together to conserve heat. The wood catches from the existing coals, flames rising briefly before settling into steady combustion. Once the new wood is burning well, you partially cover the fire pit with a flat stone, reducing the airflow. This slows the combustion rate dramatically. The fire will burn for hours now, providing warmth without wasting fuel. You arrange your sleeping furs in the warmest part of the shelter, closest to the fire but not so close that a stray spark could cause problems. The furs are heavy and soft, layered to create insulation both beneath and above your body. You've learned through many cold nights exactly how to arrange them for maximum warmth. Before lying down, you make one final check of the shelter. The entrance hide is secure, the smoke hole is properly adjusted, your tools and food supplies are organised and safe. Everything is in order. You settle into your sleeping furs and feel your body relax. The physical work of the day has left you pleasantly tired. Your muscles are warm and loose from activity. The fire's heat radiates across your skin. You pull the top layer of furs up to your chin and allow yourself to simply be still. Thoughts drift through your mind like clouds across the sky. You review the day's accomplishments, materials gathered, tools created, fire maintained, shelter repaired, food prepared, knowledge practiced, each task completed successfully, each one contributing to your continued survival. But beyond mere survival, you recognize something else: pride in your skills, satisfaction in your self-sufficiency, connection to the land and the generations that came before you. You're living in one of Earth's harshest environments, yet you are not merely enduring. You're competent, creative, and capable of finding beauty in this austere landscape. The Ice Age steppe is a hard place to live. It offers no margin for error, no forgiveness for carelessness. Yet it is also a place of stark beauty, of vast skies and endless grasslands, of resilience and adaptation. The same glaciers that make this climate so challenging have also created these grasslands, provided the stones you use for tools, and supported the herds of animals that sustain you. You think about the mammoth whose bones form your shelter framework, the willow trees that provided materials for baskets and fire, the reindeer whose meat you ate tonight, the stream that offers water and attracts game, the flint that becomes tools in your skilled hands. Everything is connected. Everything is part of a larger web of relationships between humans, animals, plants, and the land itself. This understanding brings a sense of belonging. You're not separate from nature. You're part of it. Another species making its way through the world using the abilities evolution has given you. Your intelligence, your hands, your capacity for learning and innovation are your equivalents of the mammoth's size, the reindeer's speed, or the wolf's teeth. These are your adaptations for survival. The fire crackles softly, a comforting sound that has accompanied humans for hundreds of thousands of years. How many of your ancestors fell asleep to this same sound, in shelters not so different from yours, living lives governed by the same rhythms of gathering, making, maintaining, and resting? The continuity is profound. You're doing what humans have done since before recorded time, surviving through knowledge, skill, and community. Tomorrow will come with its own demands. There will be new tasks to complete, new challenges to face. Perhaps you will hunt, tracking game across the steppe. Perhaps you will process hides, scraping and softening them into leather. Perhaps you will repair tools, weave baskets, or gather more food. Whatever needs doing, you will do it because this is your life, the life your ancestors prepared you for through their teaching and their example. But tomorrow is not here yet. Tonight is for rest, for allowing your body to repair itself after a day of labour, for letting your mind drift peacefully towards sleep. You feel your breathing slow and deepen. Your eyes grow heavy. The warmth of the fire and the comfort of the furs create a cocoon of safety and peace. Outside, the stars wheel slowly across the sky. The wind continues its endless conversation with the grass. Somewhere in the distance, a wolf howls, the sound carrying across the empty land. It is a lonely sound, but also strangely beautiful. Another voice in the wilderness, another life finding its way through the night. Your thoughts grow less distinct, blending into images and fragments. Stoneflakes glittering in firelight, the smell of cooking stew, the weight of the carrying sling full of firewood, the satisfaction of a shelter well maintained. These impressions swirl and fade as consciousness releases its grip. Sleep comes gently, naturally, as it should after a day of purposeful work. Your breathing falls into the deep, regular rhythm of rest. The fire burns on, its coals glowing softly in the darkness. The shelter holds its warmth. The night continues outside, vast and cold and filled with its own life. You sleep deeply, dreamlessly, your body and mind recovering their strength. Tomorrow you will wake with the dawn, add wood to the fire and begin the cycle again. Gathering, making, maintaining, teaching, resting. These are the rhythms of survival, the ways that have sustained humans through the harshest ages. For now, you rest. Safe, warm, and competent. A small point of human warmth and intelligence in the great cold night of the Ice Age steppe. Tomorrow will bring new tasks, but tonight you have done well. You have lived skillfully, gathering what you need, creating what you must, maintaining what you have, and preparing to pass it all forward. This is enough. This is everything. The fire glows, the shelter stands, you sleep, and the long night passes peacefully. One more day of survival complete, one more night of rest earned, one more morning waiting to arrive with its familiar challenges and rewards. You're sitting outside a cave entrance in what will one day be called France. But that name won't exist for another 30,000 years. The year is approximately 35,000 BCE, and you've just finished a meal of roasted ibex. The fire crackles beside you, sending occasional sparks upward into the darkness, and as your eyes follow those brief orange embers, they continue travelling until they meet something far more permanent. Stars. Not just a handful of stars, but thousands upon thousands of them, spread across the sky in a brilliance that would make any modern city dweller weep with disbelief. There's no light pollution here, no glow of distant towns or passing cars. The Milky Way stretches overhead like a river of cream poured across black stone, so bright you could almost read by it if reading were something you knew how to do. But you don't need reading. Your mind is already doing something far more fundamental. It's finding patterns. This isn't a conscious decision. Your brain, like every human brain that will follow yours through the millennia, is a pattern recognition machine. It's what keeps you alive. That rustle in the grass might be wind, or it might be a cave lion. That particular arrangement of broken branches might mean another human passed this way, or it might mean nothing at all. Your survival depends on sorting signal from noise, and you've gotten remarkably good at it. So when you look at the stars, your brain does what it does best. It connects dots. That cluster over there looks somewhat like the ibex you hunted earlier. See how those stars form the curve of horns? And that group to the east resembles the bear you saw last spring, though you'd never get close enough to one to confirm the details. You don't have names for these patterns yet, at least not names that will survive, but you recognize them. Night after night they're there, in the same positions relative to each other. This is remarkable, actually. Almost everything else in your world changes. The seasons shift. Animals migrate. Rivers flood and recede. Trees grow and fall. Even the moon transforms its face across each month, swelling from a sliver to a bright circle and back again. But these stars, these particular arrangements, they are constant. Or mostly constant anyway. You've noticed they do move across the sky each night, wheeling from east to west, but they maintain their relationships to each other. The ibex stars stay ibex-shaped. The bear stars remain bear-like. You don't know it yet, but you've just made one of the most important discoveries in human history. You've found something reliable in an unreliable world. Over the following nights and months you notice more. Those same star patterns appear in the east each evening and travel westward, eventually disappearing below the western horizon. If you stay awake long enough, and sometimes you do, whether by choice or because something has spooked the group and everyone's remaining alert, you see new patterns rise in the east to replace them. It's like watching a very slow parade, except this parade repeats itself with extraordinary precision. You begin to anticipate. You know that when certain stars appear just above the eastern horizon at dusk, the weather will soon turn colder. You've seen this correlation enough times that it's no longer a coincidence. When other stars dominate the night sky, the herds will be moving through the valley, and hunting will be good. This knowledge gets shared. Around fires, under those same stars, you and others discuss these observations. The sharing isn't formal education as future civilizations will understand it. There are no schools, no books, and no formal teachers, but knowledge passes anyway, through conversation and demonstration, through the simple act of pointing upward and helping others see what you see. A young member of your group, perhaps 10 or 11 years old, sits beside you one night. You point out the patterns you know, tracing invisible lines between stars with your finger. The child's eyes follow your hand, and you can see the moment of recognition, that same spark of understanding that lit your own mind years ago. The patterns aren't random. They mean something. They can be learned. Neither of you realizes it, but you're creating something that will outlast both your lives, both your descendants, and both your entire lineages stretching forward 10,000 years. You're creating tradition. You're building the foundation of astronomy. The stars wheel overhead, indifferent to your newfound attention. They've been there for billions of years before you, and they'll remain for billions more after you're gone. But in this moment, in the simple act of watching and wondering, you've joined a project that your species will continue for as long as it exists. You've started asking the question that will echo through every civilization that follows. What are those lights, and what do they mean? It's approximately 15,000 BCE now, and you're standing in what will eventually be known as Germany, watching the moon rise over a landscape of ice and scattered pine. The glaciers have been retreating for generations, but winter still brings a cold that can kill the unwary. You've survived 23 of these winters, which makes you remarkably old by the standards of your time, and you've learned something that younger people often miss. The sky keeps time. Not just any time, the perfect time. You discovered this gradually, the way most important things are discovered. One year, you noticed that the moon went through exactly 12 complete cycles, from new to full and back to new again before the seasons completed their circuit. Well, almost 12. It was actually a bit more than 12, but close enough that you could use it as a rough calendar. When the moon had cycled through its phases 12 times, you could expect the warm season to arrive soon. When it cycled through another 12, the cold would return. This was useful, but the moon alone wasn't quite reliable enough. Some years, counting 12 moons brought you to the season change right on schedule. Other years, you'd be off by several weeks. It was frustrating, like trying to catch fish with a net that had inconsistent holes. But then you paid attention to the stars, specifically to which stars were visible just before dawn. You noticed that certain stars would appear on the eastern horizon just before the sun rose, and this appearance correlated even better with the seasons than the moon did. When you could see a particular bright star rising just before daybreak, you knew with certainty that the herds would arrive within days. When another star made its first pre-dawn appearance, you could prepare for the cold. You didn't know the physics behind this. You didn't know that Earth orbits the Sun, or that the stars' apparent positions shift gradually throughout the year because of this orbital motion. You didn't need to know the mechanism. You just needed to know it worked, and it did, with a reliability that bordered on the miraculous. Other patterns emerged as you watched. The moon's position against the background stars changed nightly, moving eastward through the same star patterns that the sun seemed to travel through during the year. The moon completed its journey through these patterns in about 29 days, one complete cycle from new moon to new moon. This realization helped you understand why the 12 lunar months didn't quite match up with the seasonal year. The moon and the sun were travelling along the same path through the stars, but at different speeds. You began marking these observations. On bones and antlers, you carved notches, not random decorations, but deliberate counts. 29 notches for a lunar month, 12 sets of these for a year, with additional marks to track the discrepancy. These weren't idle doodlings passed around a fire. They were data. They were records. They were humanity's first spreadsheets, carved into whatever material was hard enough to last. The precision of these records is startling. Modern archaeologists examining Ice Age artifacts have found counting systems that tracked lunar phases with remarkable accuracy. You weren't primitive in your thinking. You were sophisticated observers using the tools available to you. The fact that you lacked telescopes or mathematical notation didn't make you less intelligent. It made you more impressive, actually, because you figured out so much with so little. This timekeeping had immediate practical value. Knowing when seasons would change meant knowing when to move camp, when to hunt specific animals, and when to gather particular plants. A group that could predict these changes had significant advantages over a group that reacted to them as they occurred. You could prepare, you could plan, you could survive when others might not. But something else was happening too, something harder to quantify. By tracking time, you were developing a new relationship with the future. Instead of living entirely in the present moment, reacting to whatever each day brought, you were beginning to anticipate. You were building mental models of how the world worked, models that extended beyond immediate sensory experience. You were, in a real sense, beginning to think abstractly. The night sky became your most reliable reference. The ground beneath your feet changed with floods and fires and the slow grinding of glaciers. The plants and animals around you migrated and evolved. Even the climate shifted across generations. But those stars, those patterns in the sky, remained constant enough to build your life around. They were the one fixed reference in a fluid world. You didn't worship the stars exactly, though that would come later for other cultures. Your relationship with them was more practical than spiritual at this point. They were tools. They were the most accurate calendar you had, the most reliable clock and the best map for predicting the future. They were quite literally your guide to survival. As you stand there watching the moon rise, you feel a satisfaction that transcends mere utility. There's something deeply pleasing about understanding how the sky works, about being able to predict what will appear where and when. You've turned mystery into knowledge and chaos into pattern. You've looked at the universe and found it comprehensible. The stars continue their ancient dance, and you continue your watch, adding another night's observations to a lifetime of accumulated knowledge. You don't know that people will still be doing this same thing 15,000 years from now, using tools you can't imagine to ask questions you'd never think to pose. But you'd probably appreciate the continuity. You've started something after all. You've begun the long project of mapping the heavens, and that project has barely begun. You're standing on a ziggurat in ancient Babylon, and the year is approximately 1700 BCE. The structure beneath your feet rises in massive tiers above the Euphrates River valley, each level smaller than the one below, creating a stepped pyramid that serves as both temple and observatory. The air's warm, it's almost always warm here, and the sounds of the city have faded with the sunset. Now there's just you, the night, and your duty. You are a priest astronomer, which in this civilization means you're one of the most powerful people in the kingdom. Kings consult you before making important decisions. Farmers depend on your calculations to know when to plant. The entire empire runs according to calendars you and your colleagues maintain. This isn't symbolic power. This is real authority derived from real knowledge, and that knowledge comes from the sky. Your people have been watching the heavens systematically for centuries, keeping records that span generations. These aren't casual observations noted when someone happens to remember. This is rigorous, continuous monitoring, with each night sky carefully recorded on clay tablets that fill entire libraries. You've inherited these records, and you add to them nightly, continuing a scientific tradition that will outlast your civilization itself. Tonight, you're tracking Venus. The evening star, you call it, though you've noticed it also appears as the morning star at different times of year. What you don't yet realize is that these are the same object, a planet closer to the sun than Earth, though the concept of planets as worlds rather than wandering stars is still centuries away. What you do know is that Venus follows a complex pattern through the sky, appearing and disappearing with a regularity you've learned to predict. This predictability is everything in a world where so much is uncertain, where crops might fail, where diseases strike without warning, where enemies could attack at any time. The sky offers constancy. The fact that you can predict celestial events gives you a kind of power over chaos itself. When you announce that Venus will disappear from the evening sky in 5 days and reappear as the morning star in 83 days, and then it happens exactly as you've said, you're demonstrating mastery over the cosmos itself. Or at least that's how it appears to those who don't understand your methods. But you understand your methods and they're not magic, they're mathematics. Your civilization has developed sophisticated arithmetic, including a base 60 counting system that will eventually give the world 60-second minutes and 60-minute hours. You use this mathematics to track celestial cycles, calculating the relationships between different astronomical periods with impressive precision. The moon has been especially well studied. Your predecessors discovered the Saros cycle, a period of approximately 18 years and 11 days, after which eclipses repeat in almost identical patterns. This means that if you record every eclipse for 18 years, you can predict eclipses for the next 18 years and the 18 after that. It's not perfect, small variations accumulate over time, but it's remarkably accurate, and it makes you appear almost prophetic to those who don't know the mathematics behind your predictions. You've also been tracking the 5 visible planets, though you don't call them that yet. Mercury, Venus, Mars, Jupiter and Saturn wander among the fixed stars, each following its own complex path. Mercury never strays far from the Sun, appearing briefly after sunset or before sunrise. Venus makes its more dramatic appearances, becoming the brightest object in the sky besides the Sun and Moon. Mars occasionally seems to move backward, a phenomenon called retrograde motion that will puzzle astronomers for centuries. Jupiter and Saturn move more slowly, taking years to complete their journeys through the stars. These observations have practical applications. Your calendar, based on lunar months but adjusted to keep pace with the solar year, requires constant monitoring to remain accurate. You add extra months when necessary, a practice called intercalation, to prevent the calendar from drifting away from the seasons. This ensures that religious festivals occur at the appropriate times of year, that farmers plant at the optimal moment, and that the entire civilization stays synchronized with natural cycles. But there's more than practicality at work here. You've begun to see patterns within patterns, relationships between celestial events that suggest the universe operates according to comprehensible rules. When you calculate that Mars will appear in a certain position relative to certain stars on a certain date, and then it happens, you're not just predicting the future, you're glimpsing the underlying order of creation itself. Your culture has woven the sky into every aspect of life. The zodiac, those 12 patterns of stars through which the sun appears to travel during the year, has become a framework for understanding time and fate. Each month belongs to a different zodiac sign, and the position of planets within these signs is believed to influence earthly events. This is the beginning of astrology, which will later diverge from astronomy, but which, in your time, is inseparable from it. Both are attempts to find meaning in the sky, to understand how celestial patterns relate to terrestrial existence. You don't see a conflict between the spiritual and the mathematical. For you, calculating the precise moment of a lunar eclipse and believing that eclipse carries divine significance are complementary activities. The mathematics proves the divine order. The predictability of the heavens demonstrates that the universe is not chaotic, but rather follows laws established by the gods. Your calculations are, in a sense, a way of reading the gods' intentions. As the night deepens, you record your observations on a fresh clay tablet, pressing wedge-shaped marks into the soft surface with your reed stylus. Centuries from now, archaeologists will unearth tablets like this and marvel at their accuracy. They'll recognize genuine astronomical data recorded with scientific precision. They'll see that your civilization understood far more about celestial mechanics than history often credits you with knowing. But for now, you're simply doing your job. You're watching, recording, calculating, and slowly building a body of knowledge that will influence every civilization that follows. When Greek astronomers later develop their models of the cosmos, they'll build on Babylonian observations. When Islamic scholars preserve and expand astronomical knowledge during Europe's Dark Ages, they'll reference Babylonian mathematics. When modern astronomy finally emerges, it will carry forward traditions that began on ziggurats like the one beneath your feet. The stars wheel overhead, the same stars that Ice Age hunters watched, but you're seeing them differently now. You're measuring them, calculating their movements, and finding mathematical relationships in their patterns. You've transformed them from mysterious lights into data points in an increasingly sophisticated understanding of the cosmos. You've turned wonder into science, though you don't use that word yet. Above you the Milky Way glows, and somewhere within it, though you'll never know this, the light of your own sun is just one star among billions. But on this night, in this moment, you're doing the work that will eventually reveal even that humbling truth. You're watching, recording, and thinking activities that will prove to be among humanity's most powerful tools for understanding the universe. You're standing on the deck of a Polynesian voyaging canoe, and the year is approximately 800 CE. The nearest land is 3 days behind you, and the nearest land ahead is perhaps 5 days away, though you won't know for certain until you see it. Around you the Pacific Ocean extends to every horizon, an expanse of water so vast that all the world's land could fit within it with room to spare, and you have no instruments, no compass, no sextant, and no GPS. You have something better. You have the stars, and you know how to read them. Your canoe is magnificent, 60 feet of a hull carved from breadfruit trees, with 2 hulls joined by a platform that provides stability in rough seas. The sail is woven from pandanus leaves, and it catches the trade winds that will carry you across hundreds of miles of open ocean. You're travelling with 30 other people, carrying plants and animals to establish on a new island, assuming you find it. This isn't exploration for exploration's sake. This is colonization, migration, the deliberate expansion of your people across a vast ocean. And you're navigating by methods that would seem impossible to many other cultures. You have no written charts. You've never written down any directions or drawn any maps. Everything you know about navigation, every technique, every star path, every wave pattern, exists in your memory and in the memories of the navigators who taught you. This knowledge was passed down orally, demonstrated at sea, and practiced until it became intuitive. What looks like magic to outsiders is actually a sophisticated science based on careful observation of natural phenomena. The stars are your primary tools. Before departing, you memorize star paths, specific stars that rise and set at consistent points on the horizon, creating paths across the sky that correspond to directions across the ocean. When you want to sail toward your destination island, you identify the appropriate star path and keep your canoe aligned with it. As each star rises in the east, travels across the sky, and sets in the west, you use it to maintain your course. When one star becomes too high to use effectively, you switch to the next star in the sequence. This continues all night, every night, for as many nights as the journey requires. During the day you have the sun, which rises and sets at predictable points depending on the season. You also have the swells, long-period waves generated by distant storms that travel across the ocean in consistent directions. You can feel these swells through the hull and sense their direction even when surface waves obscure them. By combining sun position with swell direction, you maintain your course during daylight hours, but the stars provide the most reliable guidance. You know dozens of stars by name, understand their rising and setting points, and can estimate your latitude by observing which stars pass directly overhead. The North Star, Polaris, is too far north to be useful in most of the Pacific, but other stars serve similar functions. The Southern Cross points south. Arcturus, which you call Hokulea, passes nearly overhead at Hawaii's latitude. When Hokulea is directly above you, You know you're at the correct latitude to find those islands. You've also memorized reference islands, small atolls and islands that lie between your starting point and destination. Even if you don't plan to stop at these references, knowing their positions helps you navigate. If you spot one of them, you can adjust your course accordingly. If you don't spot one you expected to see, you know you've drifted and can calculate the correction needed. The sophistication of this system is staggering. You're essentially maintaining dead reckoning across hundreds or thousands of miles of featureless ocean, updating your position constantly based on every available cue. You watch for clouds that form over distant islands, invisible below the horizon but revealed by the clouds they generate. You observe seabirds and know which species fly far from land and which stay close to shore. You note the colour of the water, the type of floating debris, and the temperature changes that indicate different currents. On clear nights, the navigation is almost relaxing. The stars are bright and obvious. The moon provides additional light and you can see the horizon clearly. But tonight clouds obscure much of the sky. This would panic a less experienced navigator, but you've sailed through worse conditions. You find gaps in the clouds, catch glimpses of familiar stars, and use those brief views to maintain your course. When stars aren't visible at all, you rely on the swells, on the wind's direction, and on subtle signs that others might miss entirely. Your people have been making journeys like this for over 1,000 years, spreading across the Pacific in waves of migration that populated islands from Hawaii to New Zealand to Easter Island. This represents one of humanity's greatest navigational achievements, settling thousands of islands scattered across the world's largest ocean, using nothing but observation, memory, and skill. Cultures with metal tools and written languages couldn't match what your people accomplished with wooden canoes and oral knowledge. The key was the stars' reliability. On an ocean without landmarks, where currents can push you off course and winds can shift unpredictably, the stars remained constant. They appeared in the same positions, followed the same paths, and maintained their same relationships to each other. This celestial constancy provided the reference frame you needed to navigate terrestrial uncertainty. Your navigation is astronomy in its most practical form. You don't care about the physical nature of stars. Whether they're distant suns or lights on a celestial sphere makes no difference to your work. What matters is their positions, their movements, and their usefulness as guides. You've developed an applied science of astronomy focused entirely on what works rather than why it works. Your theories about the cosmos might strike later astronomers as primitive, but your practical knowledge of celestial navigation is extraordinarily sophisticated. As dawn approaches, you spot something on the horizon, a cloud with a greenish tint at its base, reflecting vegetation on an island below. It's the reference atoll you expected to see, right where it should be. Your navigation has been accurate. You adjust your course slightly, compensating for the current that pushed you marginally east during the night, and continue toward your destination. Around you, people are waking, preparing food and tending to the plants and animals you're transporting. Children play on the platform between the hulls, too young to understand the precision required to find a tiny island in an enormous ocean. They'll learn, though. Some of them will become navigators themselves, memorizing the same star paths you know, learning to read the same subtle signs, and continuing traditions that stretch back through more generations than anyone can count. The sun rises and the stars fade. Your nighttime navigation tools disappear, but you've already noted your position and set your daytime course. In a few days, if your calculations remain accurate, you'll sight your destination. A new island to settle, a new home for your people, found by following lights in the sky across an ocean that covers nearly a third of the planet. The stars didn't care about your journey. They would have shone just as brightly whether you were there to see them or not. But by learning to read them, by understanding their movements with enough precision to stake your life on that understanding, You've transformed them from merely beautiful lights into the most reliable tools humanity has ever found for exploring the world. You've proven that careful observation and rigorous mental training can overcome seemingly impossible challenges. You've shown that the sky is more than something to wonder at. It's something to use, to rely on, and to trust with your survival. And in doing so, you've continued the project begun by those Ice Age observers. The long, patient work of understanding what those lights are and what they can tell us about the world we inhabit. You're standing in the Library of Alexandria, and the year is approximately 200 BCE. The room around you contains hundreds of thousands of scrolls, the accumulated knowledge of the ancient world gathered from every culture the Hellenistic Empire has touched. But right now, you're not interested in poetry or philosophy. You're focused on a particular scroll that contains astronomical observations from Babylon, and you're trying to reconcile those observations with a new geometric model of the cosmos. You are, in the terminology of your time, a mathematician and natural philosopher, though later ages will call you an astronomer. Your name might be remembered. Perhaps you're Aristarchus or Eratosthenes or Hipparchus. Or it might be forgotten, lost among the thousands of scholars who worked in Alexandria during its golden age. But whether or not your individual name survives, the work you're doing will change humanity's relationship with the sky forever. You're not just observing the heavens anymore, you're measuring them. This represents a fundamental shift in approach. Earlier civilizations watched the sky and recorded what they saw, identifying patterns and using those patterns for practical purposes. You're doing something different. You're asking quantitative questions and demanding numerical answers. Not just where does the sun appear to move, but how large is the sun? Not just do the stars move, but how far away are they? Your culture has advantages that earlier observers lacked. Greek mathematics has developed geometric tools powerful enough to model celestial mechanics. Your understanding of circles, angles, and ratios allows you to make calculations that would have been impossible for the Babylonians despite their sophisticated arithmetic. You also have access to centuries of Babylonian observations, giving you data spanning longer periods than any single lifetime could provide. Consider Eratosthenes' famous calculation of Earth's circumference, performed right here in Alexandria roughly 50 years ago. He noticed that at noon, on the summer solstice, the sun was directly overhead in Serene, casting no shadow, while in Alexandria it cast a shadow corresponding to an angle of approximately 7 degrees. By measuring the distance between these cities and using basic geometry, he calculated Earth's circumference with remarkable accuracy. This wasn't just clever, it was revolutionary. He'd measured the size of the entire planet using nothing but shadows, angles, and reasoning. You're attempting something similarly audacious, calculating the distance to the moon. You know that during a lunar eclipse, Earth's shadow falls on the moon, and by carefully measuring the shadow's size relative to the moon's diameter, you can determine the ratio of distances. The mathematics is tricky. You need precise observations of eclipses, careful measurements of angles, and sophisticated geometric reasoning. But it's doable, and when you finish, you'll have a number. The moon is approximately 60 Earth radii away. This is astonishing accuracy for observations made with naked eyes and simple measuring tools. You have no telescopes, no precision instruments, just calibrated sticks and circles divided into degrees. Yet you're determining cosmic distances, measuring the unmeasurable, pulling numbers from what had been pure mystery. Other scholars in Alexandria are tackling different questions. Aristarchus has proposed something radical. Perhaps Earth orbits the Sun rather than the reverse. His geometric arguments are compelling. If Earth circles the Sun, it explains certain observations about planetary motions more elegantly than the traditional model. But his idea faces resistance. If Earth moves, shouldn't we feel it? Shouldn't the stars shift position as Earth travels around its orbit? The lack of observable stellar parallax, the apparent shift in star positions caused by Earth's motion, seems to argue against a moving Earth. What Aristarchus doesn't know is that he's right, but the stars are far more distant than anyone imagines. The parallax exists, but it's too small to detect without telescopes. His correct theory will be largely forgotten, buried under the weight of common sense that insists the solid ground beneath our feet must be stationary. Truth sometimes loses to intuition, at least temporarily. You're also working on cataloguing stars with unprecedented precision. Your predecessor Hipparchus created a star catalogue that listed roughly 1,000 stars, noting their positions and relative brightnesses. You're expanding this work, adding more stars, refining the measurements, and developing a magnitude system to classify brightness. This might seem like mere bookkeeping, but it's crucial. To understand how the heavens change, you first need to know their normal state. Only with precise catalogues can you detect phenomena like novae, new stars that appear where none existed before, or track subtle changes in planetary positions. The geometric models you're developing represent humanity's first serious attempts at explaining celestial mechanics. You describe the cosmos as a series of nested spheres, each carrying different celestial objects all rotating around Earth at the centre. It's wrong in most details, but the approach is sound. Create a mathematical model, test it against observations, and refine it when discrepancies appear. This is science, even if the specific conclusions will later be overturned. You're particularly interested in planetary motion. The 5 visible planets, Mercury, Venus, Mars, Jupiter, and Saturn, wander among the stars in ways that simple circular motion can't explain. Mars occasionally appears to stop, move backward, then resume its normal direction. How can this be if planets move on simple circles? Your solution involves epicycles, small circles whose centres travel along larger circles. A planet moves along its epicycle while the epicycle's centre moves along a larger circle around Earth. With the right combination of circles moving at the right speeds, you can match observed planetary motions quite well. The model is complicated, requiring multiple epicycles for some planets, but it works. It predicts where planets will appear in the sky months or years in advance. This model will dominate astronomy for over 1,000 years, not because people are stubborn or ignorant, but because it's genuinely useful. It predicts celestial phenomena accurately enough for navigation, calendar making, and other practical purposes. The fact that it's based on incorrect assumptions about Earth's centrality doesn't matter for prediction. A wrong model that works is more useful than no model at all, but something else is happening in your work that transcends any specific model or measurement. You're establishing the principle that the universe operates according to mathematical laws discoverable through reason and observation. The heavens aren't merely mysterious or divine, they're comprehensible. They follow rules. Those rules can be written down, calculated, and predicted. This idea, more than any particular discovery, is your culture's greatest contribution to astronomy. As evening falls and you finally leave the library, you walk out into the Mediterranean night. The stars are emerging, the same stars that Ice Age hunters watched, that Babylonian priests tracked, and that Polynesian navigators followed. But you see them differently now. You don't just observe them, you measure them. You don't merely note their patterns, you create mathematical models to explain those patterns. You've transformed them from objects of wonder into objects of study. The transformation isn't complete, of course. Many of your measurements are rough, many of your models are wrong, and many questions remain unanswerable with your current tools. But you've established something crucial. The project of understanding the cosmos through mathematics and systematic observation. You've shown that human reason can grapple with celestial phenomena, that the apparently unreachable can be measured, and that mysteries can become mathematics. Somewhere in your calculations and models, buried in geometric diagrams and numerical tables, lie the seeds of revelations that won't flower for centuries. Your work on stellar positions will eventually prove Earth moves. Your geometric techniques will help demonstrate the vast scale of the cosmos. Your insistence that observation must match theory will become the foundation of the scientific method. But tonight, you're simply satisfied to have added a few more measurements to humanity's growing understanding of the heavens. The stars shine on, indifferent to your calculations, but you've measured their positions with unprecedented precision. You've turned skyward mystery into earthly mathematics. You've continued the long journey from wonder to understanding, and that journey is far from over. You're on a rooftop in Padua, Italy, and the year is 1609. In your hands you hold an instrument that will change human understanding of the cosmos more profoundly than anything since the invention of mathematics itself. It's a tube roughly 3 feet long, fitted with carefully ground lenses at each end, capable of magnifying distant objects approximately 20 times. You call it a telescope, from Greek roots meaning far-seeing, and tonight you're about to turn it toward the sky for perhaps the 100th time, each session revealing something new that contradicts centuries of accepted truth. The device itself is barely a year old, at least in its current form. Dutch spectacle makers discovered that certain combinations of lenses could magnify distant objects, and when you heard about this, you immediately recognized its potential. You've spent months grinding lenses, testing configurations, and improving the design until you achieved magnifications far beyond what the Dutch achieved. Where they saw a novelty, you saw a revolution. Your colleagues at the University of Padua were initially skeptical. Some refused to even look through the device, insisting that anything seen through glass lenses must be an artifact or illusion rather than reality. Others looked but dismissed what they saw, unable to reconcile observations with their understanding of how the cosmos should work. But you've persisted, and your observations have become increasingly difficult to dismiss. Tonight, you're focusing on Jupiter. You've been watching this planet for weeks now, and what you've discovered is staggering. Jupiter has moons, at least 4 of them, visible as tiny points of light arranged in a line extending from the planet's bright disk. Night by night, you've watched these moons change position, orbiting Jupiter exactly as the moon orbits Earth. This is revolutionary because it proves that not everything in the heavens orbits Earth. Here is a celestial body with its own satellites, a miniature planetary system that demolishes the Earth-centered cosmos accepted since ancient times. You've been keeping detailed records, sketching Jupiter's moons in different positions each night, and calculating their orbital periods. The innermost moon completes its orbit in roughly 42 hours. The outermost takes about 16 days. The precision of their movements is beautiful. They're following the same mathematical laws that govern the moon's orbit around Earth, suggesting universal principles rather than special cases. But Jupiter's moons aren't your only discovery. The moon, Earth's moon, has been equally revelatory. Through your telescope, the smooth, perfect sphere described by ancient philosophers transforms into a rough, mountainous world. You see craters, valleys, and towering peaks that cast long shadows across lunar plains. You've even measured the height of some mountains by calculating shadow lengths, finding peaks that rival Earth's highest summits. The moon isn't a perfect celestial object made of quintessence, as Aristotle claimed. It's a world as physical and irregular as Earth itself. Venus has provided more evidence against Earth-centered models. Through your telescope, you've observed that Venus goes through phases like the moon, sometimes appearing as a crescent, sometimes as a gibbous shape, and sometimes nearly full. This only makes sense if Venus orbits the Sun, passing between us and the Sun when it appears as a crescent and moving beyond the Sun when it appears full. In an Earth-centered system where Venus orbits between Earth and the Sun, it should only ever appear as a crescent. The phases of Venus are direct evidence for a sun-centered solar system. You've also been observing the sun itself using projection methods to avoid damaging your eyes. The sun, supposedly the most perfect celestial object, is marked with spots, dark blemishes that appear, change shape, and disappear over days or weeks. By tracking these spots, you've determined that the sun rotates, completing one revolution approximately every 27 days. This rotation, combined with the imperfect nature of sunspots, further demolishes the idea of celestial perfection. The Milky Way has revealed its secret. To the naked eye, it appears as a hazy band of light across the sky. Through your telescope, it resolves into thousands upon thousands of individual stars, too distant and numerous to see separately without magnification. This suggests the universe contains far more stars than anyone imagined. Not the few thousand visible to the naked eye, but potentially millions or billions, extending far beyond what earlier astronomers thought possible. Each of these observations contradicts established doctrine. The Church's cosmology, based on Aristotle and Ptolemy, places Earth at the centre of a small, ordered universe with perfect celestial bodies moving on perfect circles. Your observations suggest a vastly larger universe with imperfect celestial bodies where Earth is not central. You're not trying to challenge religious authority, you're simply reporting what you see, but the implications are impossible to ignore. The resistance you face isn't entirely unreasonable. Your telescope is new technology, and its reliability isn't yet proven. How can anyone be certain that what appears in the telescope truly represents reality, rather than optical illusions created by lenses? Your response is pragmatic. The telescope accurately shows distant terrestrial objects, ships that are below the horizon, and buildings in distant cities. If it works reliably for earthly observations, why should celestial observations be different? You're also making your findings public, publishing your observations in language accessible to educated readers, not just in Latin for scholars. Your book, Sideris Nuncius, the Starry Messenger, spreads your discoveries across Europe within months. Other observers with telescopes confirm your findings. Jupiter's moons can be seen by anyone with adequate magnification. The phases of Venus are independently verified, and the moon's mountains are photographed with increasing detail as telescope. Technology improves. The cumulative weight of these observations forces a revolution in thought. The cosmos is not small, ordered, and geocentric. It's vast, perhaps infinite, with Earth as just one planet among several orbiting an ordinary star. This insight is simultaneously humbling and exhilarating. Humanity has been demoted from the centre of creation, but in exchange we've discovered a far grander universe than anyone imagined. As you pack up your telescope for the night, you reflect on how one simple device, a tube with lenses, has demolished millennia of accepted truth. The ancient Greeks would have given anything for this technology. They had the mathematical sophistication to understand what you're seeing, but they lacked the tools to see it. The observations that would have resolved their debates about Earth's motion were always there in the sky, invisible only because human eyes couldn't detect them without help. This raises a humbling question. What else is in the sky that you can't see even with your telescope? Your instrument magnifies 20 times, which is impressive, but surely this isn't the limit of what's possible. Future observers with better telescopes will undoubtedly see things you're missing. How much larger is the universe than what you can see? How many more discoveries await merely better technology? You don't know it yet, but your telescope represents the first of many technological leaps that will progressively reveal the cosmos's true nature. Better lenses, then reflecting telescopes, then photography, then spectroscopy, then radio astronomy, then space-based telescopes free from atmospheric distortion. Each advancement will reveal new phenomena, answer old questions, and raise new mysteries. Your 17-inch telescope is primitive compared to what's coming, but it's sophisticated enough to begin the revolution. The stars shine overhead, now known to be distant suns rather than lights on a celestial sphere. The planets, visible as bright points to the naked eye, are revealed through your telescope as worlds. Jupiter with its cloud bands and moons, Saturn with its mysterious elongated shape. You can't quite resolve the rings with your current telescope, but you know something odd extends from the planet's sides, and Mars with hints of surface features. You've lived through one of history's great turning points, the moment when humanity first saw the cosmos as it truly is, rather than as we imagined it must be. The implications will take generations to fully understand, but the basic fact is clear. We are far smaller, and the universe far larger, than anyone dreamed. And that's wonderful, because it means there's so much more to discover, so many more mysteries waiting in the dark between the stars. You're working in a Cambridge office, and the year is approximately 1726. Papers cover your desk, calculations, diagrams, and observations from astronomers across Europe. You're attempting something that many colleagues consider impossible. You're trying to calculate the distance to a comet using nothing but geometric principles and observations from multiple locations. If you succeed, you'll prove that comets are distant celestial objects rather than atmospheric phenomena, and you'll demonstrate that mathematics can measure even the seemingly unmeasurable. Your name is Edmund Halley, and you've dedicated much of your career to understanding celestial mechanics. You've been fascinated by comets, those mysterious objects that appear unpredictably, blaze across the sky for weeks or months, then vanish. Aristotle believed they were atmospheric disturbances, weather phenomena rather than celestial objects. This view persisted for centuries, but you're convinced Aristotle was wrong. The evidence is in the geometry. You have observations of comets from different locations on Earth, measured carefully by skilled astronomers. If comets were atmospheric phenomena relatively close to Earth, observers at different locations should see them at noticeably different positions against the background stars. This is parallax, the same principle that makes nearby objects appear to shift when you close one eye and open the other. But cometary parallax, when measurable at all, is tiny, suggesting these objects are extremely distant. Moreover, you've been studying historical records of comet sightings, comparing their paths across the sky, their appearance, and their behaviour, and you've noticed something remarkable. Comets that appeared in 1531, 1607, and 1682 followed nearly identical paths. They appeared in similar regions of the sky, moved in similar directions, and brightened and faded in similar patterns. What if these weren't three different comets, but the same comet, returning periodically? The mathematics support this hypothesis. Using Newton's laws of motion and gravitation, which your friend Isaac published 40 years ago, you can calculate orbital paths for objects moving through the solar system. When you apply these calculations to the 1682 comet, assuming it's in a highly elliptical orbit around the Sun, you get an orbital period of roughly 75 to 76 years. Count back 76 years from 1682, and you reach 1607. Count back another 76 years, and you reach 1531. The timing matches the historical sightings almost perfectly. This means you can make a prediction. If your hypothesis is correct, this comet should return around 1758 or 1759. You'll be long dead by then. You're already in your 70s. But the comet will either appear as predicted, confirming your calculations, or it won't, proving you wrong. Either way, the prediction is testable, which makes it scientific rather than mere speculation. What you're doing represents a new kind of astronomy. Earlier observers watched the sky and recorded what they saw. They identified patterns and made predictions based on those patterns, but their predictions were essentially extrapolations, assuming the future will resemble the past. You're doing something different. You're using physical laws, mathematical models, and theoretical understanding to predict phenomena that haven't been observed yet. You're not just recording the universe, you're calculating it. Newton's work made this possible. His laws of motion and universal gravitation provided for the first time a unified framework for understanding both celestial and terrestrial mechanics. The same force that pulls an apple downward pulls the moon toward Earth, and Earth toward the sun. The same mathematical laws that describe projectile motion on Earth describe planetary orbits in the heavens. This unification is profound. It means the universe operates according to comprehensible universal principles rather than separate rules for different domains. You've applied these principles to various problems. You calculated the path of the 1682 comet, determining its orbital elements with unprecedented precision. You've worked on improving tables of planetary positions, incorporating perturbations, the subtle gravitational influences that planets exert on each other, causing small deviations from perfect elliptical orbits. You've studied the moon's motion, wrestling with the three-body problem, the mathematical challenge of precisely calculating how three gravitationally interacting objects move. The moon problem is particularly vexing. The moon's orbit is influenced not just by Earth, but also by the sun, and the combined gravitational effects create orbital irregularities that are devilishly difficult to calculate. Newton himself struggled with lunar motion, and the problem won't be fully solved for another century. But you've made progress, improving predictions enough that navigators can use your lunar tables to determine longitude at sea, a practical application of celestial mechanics that saves lives and enables exploration. You've also been thinking about stellar distances. The stars are clearly far more distant than planets. They show no measurable parallax even from observations made 6 months apart, when Earth is on opposite sides of its orbit around the Sun. This means stellar distances must be enormous compared to solar system scales. But how enormous? Can these distances be measured at all? You suspect they can, eventually, though not with current instruments. If telescopes become powerful enough and measurements precise enough, stellar parallax should become detectable. The math is straightforward. Measure a star's position in summer, measure it again in winter when Earth has moved to the opposite side of its orbit, and calculate the distance based on the apparent shift. The challenge is that even the nearest stars are so distant that their parallax is measured in fractions of an arc-second. Angles so small they require instruments far more precise than what's currently available. But you're confident that future astronomers will make these measurements. Technology improves, telescopes become more powerful, measurement techniques become more refined. What's impossible today becomes routine tomorrow. The stars' distances will eventually be known, and when that happens, humanity will finally understand the true scale of the cosmos. As you review your calculations one more time, checking for errors, you consider how far astronomy has come in just a few generations. When you were born, telescopes were relatively new, the heliocentric model was still controversial, and the physical laws governing celestial motion were unknown. Now, less than a century later, you're calculating comet orbits, predicting future appearances, and treating the heavens as a domain subject to the same mathematical laws that govern earthly phenomena. The transformation isn't complete. Many mysteries remain. The nature of stars is unknown. Are they distant suns, and if so, how far away and how large? The structure of the Milky Way is unclear. Is it a flat disk, a sphere, or something else entirely? The possibility of other galaxies hasn't even been seriously considered. Most astronomers assume all visible stars belong to one unified system, but the methodology is now established. You observe, you measure, you calculate, you predict, and you test. When predictions fail, you refine your models. When new phenomena are discovered, you incorporate them into your framework. This is science, and it's proving extraordinarily powerful for understanding nature. Your comet prediction, in particular, feels like a gamble against mortality itself. You're wagering that mathematics and physics can project forward decades into the future, that the universe is lawful enough, and that your understanding is complete enough to make predictions across timescales longer than human lifetimes. If you're right, and the comet returns when predicted, it will be one of science's great triumphs, a demonstration that human reason can grasp cosmic patterns and use them to predict the unpredictable. You won't live to see it, but you're content with that. You've done the work, you've made the calculations. The comet will either confirm your hypothesis or it won't, but either outcome advances knowledge. And that ultimately is what drives you. Not personal glory or the satisfaction of being proven right, but the simple desire to understand how the universe works. The stars shine outside your window, distant and mysterious, but less mysterious than they were. Each generation peels back another layer of cosmic mystery, armed with better tools, better mathematics, and better understanding. Your generation has accomplished remarkable things, but you're certain future generations will accomplish more. The universe is vast, complex, and wonderful, and humanity has barely begun to explore it. You're standing outside the dome of the Mount Wilson Observatory in California, and the year is 1924. The sun set hours ago, and now the Milky Way stretches overhead in magnificent detail, visible despite the growing light pollution from Los Angeles in the valley below. Inside the dome behind you sits the Hooker telescope, 100 inches of reflecting mirror, the largest telescope in the world, capable of gathering more light and seeing fainter objects than any instrument in human history. And tonight, you've used it to make a discovery that will fundamentally change humanity's understanding of its place in the cosmos. Your name is Edwin Hubble, and you've been photographing spiral nebula. Those fuzzy, spiral-shaped objects scattered across the sky. Astronomers have debated their nature for years. Are they gas clouds within our own galaxy, or are they distant galaxies themselves, separate island universes beyond the Milky Way? The debate has been fierce with respected scientists on both sides, but you think you've finally settled it. You've been focusing on Andromeda, the largest and brightest of the spiral nebulae. Using the Hooker telescope's light-gathering power, you've been taking long-exposure photographs, images that accumulate light over hours, revealing details invisible to direct observation. And in these photographs, you've identified individual stars within Andromeda, not just the bright blue-white stars that mark spiral arms, but specific types of variable stars called Cepheids. Cepheids are crucial because their brightness varies predictably, pulsing brighter and dimmer over periods ranging from days to months. More importantly, there's a direct relationship between a Cepheid's period and its intrinsic brightness. Longer period Cepheids are inherently brighter than short period ones. This relationship was discovered by Henrietta Leavitt, working with Cepheids in the Magellanic Clouds, and it provides a method for measuring cosmic distances. Here's the beautiful logic. If you know a Cepheid's intrinsic brightness and can measure its apparent brightness, you can calculate its distance. It's like seeing a light bulb and determining how far away it is by how dim it appears. If you know it's a 100-watt bulb, you can tell whether it's 10 feet away or 100 feet away by its apparent brightness. The Cepheids you found in Andromeda have periods indicating they're extremely luminous stars, yet they appear very faint in your photographs. The only way to reconcile these facts is if Andromeda is extraordinarily distant, not thousands or tens of thousands of light years away, but nearly 1 million light years. This places it far beyond any reasonable estimate of the Milky Way's size. Andromeda isn't a gas cloud within our galaxy. It's a galaxy itself comparable in size to the Milky Way, containing hundreds of billions of stars. If Andromeda is a galaxy, then likely all spiral nebulae are galaxies. This means the universe contains not one galaxy, but countless millions of them, scattered through space at distances that dwarf the distances between stars within any single galaxy. The universe is vastly, almost incomprehensibly larger than anyone imagined. But you've made another discovery, even more startling. You've been measuring the spectra of galaxies, analysing the light they emit to determine which wavelengths are present. What you've found is that nearly every galaxy shows a redshift, meaning their light is shifted toward longer, redder wavelengths compared to what it should be. And the more distant the galaxy, the greater the redshift. This redshift has a clear interpretation. These galaxies are moving away from us. The shift in wavelength is a Doppler effect, the same phenomenon that makes a train whistle's pitch drop as it passes you. When a light source moves away, its light is stretched to longer wavelengths, redshifted. When it approaches, the light is compressed to shorter wavelengths, blue-shifted. Moreover, you've noticed a relationship. The farther away a galaxy is, the faster it's receding. Double the distance, and the recession velocity doubles as well. This relationship, what will become known as Hubble's law, has profound implications. If all distant galaxies are moving away from us, and their recession velocity increases with distance, the universe itself must be expanding. This is difficult to grasp. You're not saying galaxies are moving through space away from us as if we're at the centre of an explosion. You're saying space itself is expanding, carrying galaxies along with it. It's like dots on an inflating balloon. As the balloon expands, all dots move away from each other, but no dot is at the centre of the expansion. Every observer in any galaxy would see all other galaxies receding, with more distant ones receding faster. This expansion suggests the universe has a history. If galaxies are currently moving apart, they must have been closer together in the past. Run the expansion backward, and you eventually reach a point where all matter was concentrated in an incredibly small, dense state. This is the beginning of what will later be called the Big Bang theory, the idea that the universe began in an extremely hot, dense state and has been expanding and cooling ever since. The implications cascade outward. If the universe is expanding and had a beginning, it has an age. You can estimate this age by calculating how long it would take galaxies to reach their current separations given their observed velocities. Your initial estimates suggest an age of a few billion years, which is troublingly young. Geologists already have evidence that Earth is older than that. But the principle is established. The universe isn't eternal and unchanging. It's dynamic and evolving with a definite history. As you stand beneath the stars, you realize you're witnessing something unprecedented in human history. Every previous generation believed the universe was static, unchanging in its large-scale structure. Oh, planets moved and comets appeared and stars occasionally exploded, but the overall universe, its size, its structure, its fundamental nature, was thought to be eternal. You've discovered this assumption is wrong. The universe is not static. It's expanding, cooling, and evolving. It had a beginning and will have a future different from its present state. This discovery comes from technology. The 100-inch telescope, photographic plates sensitive enough to capture faint light, and spectroscopes capable of analysing that light. None of this was available even 50 years ago. Your discovery was always waiting in the sky, visible in principle, but invisible in practice until instruments became sophisticated enough to detect it. How many more discoveries are out there, waiting for better technology? You think about the long chain of observations and insights that led to this moment. Ancient astronomers identifying celestial patterns, Babylonians calculating planetary positions, Greeks creating geometric models, telescopes revealing Jupiter's moons and Saturn's rings. Newton's laws enable orbital calculations. Photography allows long exposures that see deeper into space than eyes alone could. Spectroscopy reveals the physical properties of distant objects, each advance built on previous work, each generation seeing farther and understanding more deeply. And now you've pushed the frontier again. You've measured the universe and found it vaster than anyone thought. You've discovered that it's expanding, that it has a history, that it's not eternal. Future generations will push farther still, answering questions you haven't even thought to ask yet. Will they find the edge of the universe, or is it infinite? What happened in those first moments after the expansion began? Are there other universes beyond ours? You don't know, but you're confident they'll keep looking. The Hooker telescope dome closes for the night. Your photographic plates are secure, ready for detailed analysis tomorrow. The data is recorded, the measurements are made, and the conclusions are becoming inescapable. The universe is larger, stranger, and more wonderful than humanity ever imagined. And that, ultimately, is the most exciting thing you could possibly discover. Not that we understand everything, but there's so much more to explore. You're monitoring a radio telescope in northern England, and the year is 1965. The instrument you're using doesn't look like a traditional telescope. No dome, no eyepiece, just an array of horn-shaped antennas pointed at the sky, connected to sensitive radio receivers. You're not looking at the sky in visible light, but in radio waves, which pass through clouds and work during daytime, opening the heavens to observation 24 hours a day. Your name is irrelevant to this particular night, but the discovery you're about to confirm is not. You've been detecting a persistent background noise in your data, a faint radio signal that appears to come equally from all directions in the sky. At first, you thought it was instrumental error or perhaps radio interference from nearby cities, but extensive checks have ruled out these explanations. The signal is real, it's cosmic in origin, and it's uniform across the entire sky to within 1 part in 10,000. This uniform signal is extraordinary because it shouldn't exist. If it came from stars or galaxies, it would be stronger in some directions than others, concentrated in the Milky Way's plane, for instance, or showing bright spots where galaxies cluster. But this signal is almost perfectly isotropic, the same from every direction. It's like the universe has a temperature, and what you're detecting is thermal radiation from the cosmos itself. The signal's wavelength corresponds to extremely cold thermal radiation, about 3 degrees above absolute zero. This is puzzling until you remember recent theoretical work suggesting that if the universe began in a hot, dense state, the Big Bang, it would have cooled as it expanded. In its earliest moments, the universe would have been hot enough to glow brightly in visible light, even in ultraviolet and X-rays. But as it expanded, this radiation would have stretched to longer wavelengths, shifted by the expansion itself, until today it appears as faint radio waves. You're detecting the afterglow of the Big Bang itself, radiation that has travelled through space for nearly 14 billion years, cooling from temperatures of thousands of degrees to just a few degrees above absolute zero. This cosmic microwave background radiation is direct evidence that the universe had a hot beginning, that it's been expanding and cooling ever since, and that the Big Bang theory is correct. This discovery transforms cosmology from speculation to observational science. Before this, the Big Bang was one theory among several for the universe's origin. Now it's strongly supported by direct evidence, radiation that could only exist if the universe began in a hot, dense state. Alternative theories that proposed an eternal steady-state universe cannot explain this uniform background radiation. The evidence is overwhelming. But the cosmic microwave background isn't just confirmation of the Big Bang. It's a snapshot of the early universe, a window into conditions when the cosmos was just 380,000 years old. Before that time, the universe was too hot for atoms to form. Electrons and protons existed as a plasma, and photons scattered off these charged particles constantly, making the universe opaque. When the universe cooled enough for atoms to form, photons suddenly could travel freely. The radiation you're detecting comes from that moment of recombination when the universe became transparent. By studying this radiation in detail, measuring its temperature in different directions, looking for tiny variations in intensity, astronomers will learn about the universe's structure at that early time. Slightly denser regions in the primordial plasma will appear as slightly warmer spots in the microwave background. These density variations were the seeds that eventually grew into galaxies, clusters of galaxies, and the large-scale structure visible in the universe today. Over the following decades, increasingly sophisticated instruments will map the cosmic microwave background with extraordinary precision. Satellites like COBE, WMAP, and Planck will measure temperature variations as small as 1 part in 100,000, revealing detailed information about the universe's composition, age, and geometry. These measurements will determine that the universe is approximately 13.8 billion years old, that it's geometrically flat, and that it contains not just ordinary matter but also dark matter and dark energy, mysterious substances whose nature remains unknown but whose gravitational effects are undeniable. The cosmic microwave background will also provide evidence for cosmic inflation, a brief period of exponential expansion that occurred in the universe's first fraction of a second. Inflation explains why the universe is so uniform on large scales, why it's geometrically flat, and why certain types of irregularity appear in the density distribution of matter. Without inflation, the universe's observed properties would require extraordinarily fine-tuned initial conditions. With inflation, these properties emerge naturally from well-understood physics. As you examine the data streaming from the radio telescope, you're struck by how much can be learned from such a faint signal. This radiation is incredibly weak. The total energy from the cosmic microwave background hitting a person's body is far less than the energy from distant starlight, which itself is minimal. Yet this faint signal contains information about the universe's age, composition, geometry, and early history. It's as if the cosmos has left its signature written in radiation, waiting billions of years for technology to become sophisticated enough to read it. You think about the long chain of discoveries that led here. Hubble discovered galactic recession, implying the universe expands, extrapolating this expansion backward to a hot, dense beginning. Theoretical physicists are calculating what conditions would be like in the early universe, predicting that thermal radiation from that era should still be detectable. Engineers are developing radio astronomy, creating instruments sensitive enough to detect faint cosmic signals, and now the detection itself, confirming predictions and opening new avenues of research. The cosmic microwave background is also humbling. It shows that the matter we're familiar with, atoms, molecules, everything made of protons, neutrons, and electrons, comprises only about 5% of the universe's total energy content. The rest is dark matter and dark energy, substances whose nature is completely unknown. We've mapped the universe, measured its age, determined its composition, and discovered that we don't understand 95% of what it contains. Yet this ignorance is exciting rather than discouraging. It means astronomy is far from finished. There are fundamental mysteries remaining, questions whose answers will require new physics, new observations, and perhaps revolutionary insights comparable to those that launched quantum mechanics or relativity. The universe is still surprising us, still revealing that reality is stranger and more wonderful than our theories predict. As dawn approaches and your observing shift ends, you prepare your preliminary report. The signal is real, it's cosmic, and it matches predictions for the cooled radiation from the Big Bang. Other observers will confirm it independently. That's already happening, actually, with similar detections reported by other teams. Soon this discovery will be announced publicly, and it will transform humanity's understanding of cosmic history. The stars fade as the sky brightens, but you know they're still there, still shining, their light mixing with the faint microwave glow from the universe's hot beginning. That glow has travelled for nearly 14 billion years to reach your antennas, carrying information about a time when no stars existed, when no galaxies had formed, and when the universe was just a hot, dense plasma beginning its long expansion toward the cool, structured cosmos we inhabit today. Somewhere in that ancient radiation, in its tiny temperature variations and subtle polarization patterns, lie answers to questions humanity hasn't yet learned to ask. Future astronomers will extract those answers, learning things about the universe's origin, structure and fate that you can't even imagine. But tonight, you've contributed your part to that ongoing project, detecting the whisper from the beginning, confirming that the universe has a history, and opening a new window on cosmic time. You're lying on your back in a dark field, and the year is now. No specific year, really. This could be tonight, tomorrow night, or any clear night when you decide to look up rather than down, out rather than in. The grass beneath you is slightly damp with evening dew, the air is cool, and above you the sky blazes with stars. If you're far from cities, you can see the Milky Way, that same river of light that our ancestors saw, though you know now it's actually the combined light of billions of stars in our galaxy's disk, viewed edge-on from Earth's position within it. You can see planets too, though you need to know where to look and when. Venus might be brilliant in the west just after sunset. Jupiter could be high overhead, its moons invisible to your naked eyes, but there nonetheless, exactly as Galileo saw them. Mars might show its distinctive red-orange colour, dust storms in its thin atmosphere reflecting sunlight from 90 million miles away. And you can see stars, thousands of them with naked eyes, millions through modest telescopes and billions through instruments like Hubble or the James Webb Space Telescope. Each one is a sun, many hosting planets, some of those planets potentially harbouring life. The light reaching your eyes left those stars years or decades or centuries ago, making you a time traveller of sorts, seeing the universe not as it is but as it was. You know things those ancient observers couldn't have imagined. You know the stars are powered by nuclear fusion, converting hydrogen to helium in their cores, generating energy through Einstein's famous equation relating mass and energy. You know the universe is approximately 13.8 billion years old, formed in a hot Big Bang and expanding ever since. You know that galaxies cluster into groups and superclusters, forming a cosmic web of structure spanning billions of light years. You know the universe contains dark matter, invisible substance detected only through its gravitational effects, making up roughly 27% of the universe's total energy. You know that dark energy, even more mysterious, comprises about 68%, and it's causing the universe's expansion to accelerate. Distant galaxies are not just moving away, they're moving away faster over time, driven by this mysterious dark energy whose nature is one of physics' greatest unsolved problems. You know that many stars have planets, that exoplanets number in the thousands already discovered, and that more are found constantly. You know some of these worlds are roughly Earth-sized, orbiting their stars at distances where liquid water could exist. You know the chemistry of life, carbon-based molecules, water and energy, is common throughout the universe. You know that if life exists here, it probably exists elsewhere too, though whether it's common or rare, simple or complex, contemporary or extinct, remains unknown. Yet despite all this knowledge, you're lying in a field looking at stars exactly as humans have done for hundreds of thousands of years. The technology has changed dramatically. You might have a telescope beside you, or a smartphone app identifying constellations, or coordinates for satellites passing overhead, but the fundamental activity is unchanged. You're watching the sky, wondering about those lights, continuing a tradition older than civilization itself. The stars you're seeing are the same stars ancient observers saw, give or take a few supernovae and proper motion over millennia. The patterns are almost identical. If an Ice Age hunter or a Babylonian priest or a Polynesian navigator joined you in this field, you'd recognize the same constellations, point to the same bright stars, and share the same sense of wonder at the vastness above. What's different is understanding. You know what those lights are, how far away they are, what they're made of, how they formed, and how they'll die. You know the physics governing their behavior, the chemistry of their atmospheres, and the mechanics of their orbits. You've turned mystery into knowledge, but somehow the wonder remains undiminished. Perhaps it's even greater now, because you understand not just what you're seeing, but what it means. Billions of worlds scattered across incomprehensible distances, all governed by universal laws, all part of one vast interconnected cosmos. This knowledge was hard-won. It required countless observers spending countless nights recording positions, measuring angles, timing events, and noting correlations. It required mathematical genius to create models explaining observations. It required technological innovation to build instruments extending human senses into realms we can't perceive unaided. It required patience, the patience to make observations over lifetimes, to pursue answers across generations, and to accept that some questions wouldn't be answered in any individual lifetime. But mostly it required curiosity, that simple desire to understand, to know what those lights are and what they mean, has driven humanity's astronomical efforts from the beginning. We didn't need to understand the stars to survive. Early humans managed without knowing stellar distances or galactic structures. But we wanted to know anyway, and that wanting was enough to motivate millennia of effort. As you lie there, you might wonder what future observers will know that you don't. What discoveries await better instruments, deeper observations, and more sophisticated theories? Will we find life on other worlds, or evidence that we're alone? Will we understand dark matter and dark energy, or will they remain mysterious? Will we discover the universe's ultimate fate, endless expansion, eventual collapse, or something stranger? Will we develop technologies allowing travel to other stars, or will the distances prove insurmountable? You don't know, and that's wonderful. It means astronomy's story isn't finished. There are still mysteries to solve, discoveries to make, and revolutions in understanding waiting to happen. The universe is vast and strange, and humanity has barely begun exploring it. What we've learned in our brief time as a species is impressive, but what remains to learn is surely greater still. The stars shine on, indifferent to human observation, following physical laws established billions of years ago in the universe's hot beginning. They'll continue shining long after humanity is gone, whether that's thousands, millions, or billions of years from now. But while we're here, while we have the capacity to wonder and observe and understand, we're part of something magnificent, the universe coming to know itself. Because that's what astronomy is ultimately. It's the cosmos developing awareness, asking questions about its own nature, and seeking answers to how and why it exists. We are the universe observing itself, matter and energy arranged in patterns complex enough to contemplate their own origins. When you look at stars and wonder about them, you're participating in something profound, the long patient work of understanding, of transforming mystery into knowledge, of finding humanity's place in the vast cosmic story. So when clear nights come, step outside, look up. You're carrying forward a tradition hundreds of thousands of years old, joining countless observers across time who've shared your curiosity. You're seeing light that travelled across space and time to reach your eyes, photons that began their journeys years or centuries ago from distant suns. You're witnessing a universe of almost incomprehensible scale and beauty, governed by elegant laws we've only partially understood. And in doing so, you're continuing the work those first curious humans began on African grasslands so long ago. The work of looking upward, wondering what those lights might be, and slowly, patiently, figuring it out. The journey isn't finished. The sky holds mysteries still, waiting for observers with new tools and new insights to reveal them. But tonight, you're part of that journey, connected across time to everyone who's ever wondered about the stars. Welcome to that ancient fellowship of star watchers. The universe is vast, beautiful, and comprehensible, and it's been waiting billions of years for minds capable of understanding it. You're one of those minds. Look up, wonder, and know that you're participating in one of humanity's greatest projects. The long, patient effort to understand how the universe works and our place within it. Sweet dreams beneath the stars. Long before laboratories hummed with microscopes and databases clicked through millions of fingerprint matches, detectives solved crimes using nothing more than sharp eyes, patient ears, and detailed notebooks. You're about to discover how these early investigators pieced together mysteries in an era when forensic science barely existed. You stand in a London street on a foggy November morning in 1863. The gas lamps still flicker along the cobblestones even though dawn has arrived. Somewhere in the distance, a church bell marks 7 o'clock. The fog tastes of coal smoke and dampness. You can feel it settling on your coat like a cold, wet blanket. A constable rushes past you. His boots splash through a puddle. He carries a wooden rattle that police officers use to call for help. The sound cuts through the morning quiet. You follow him around the corner to where a small crowd has gathered outside a jewellery shop. The front window has been smashed. Glass fragments catch the dim light like scattered stars on the pavement. This is how detective work begins in the age before fingerprints. Someone notices something wrong, people gather, a constable arrives, and then the real work starts. The constable takes out a small notebook. His pencil moves slowly across the page as he writes down every detail he can see. The broken window, the empty display case, the muddy footprints leading away down the alley. He does not have photographs. He does not have fingerprint powder. He has his eyes and his ability to describe what he sees. You watch him sketch the scene in rough lines. His drawing shows the position of the broken glass. Some pieces fell inside the shop, others scattered onto the street. This tells him something important. The glass broke from outside to inside. The thief stood on the street and struck the window with force. He kneels down to examine the footprints more closely. The mud is fresh. It rained last night and the ground is still soft. He can see the pattern on the sole. It shows a distinctive wear pattern on the left heel. One boot clearly has a crack running across it. He copies this pattern into his notebook with careful attention to every line and curve. This is observation. This is the foundation of all detective work before modern forensics. You learn to look at everything. You learn to see what others miss. You learn that every criminal leaves traces of themselves behind, whether they mean to or not. The constable asks the shopkeeper about what happened. The shopkeeper arrived at his usual time of 6:30 in the morning. He found the window broken and 3 gold watches missing from the display. Nothing else was taken. The till remained untouched in the back room. This strikes the constable as unusual. Most thieves would take whatever they could grab. You follow the constable as he walks the street asking questions. An old woman who lives above the bakery heard glass breaking around 3 in the morning. She looked out her window but saw only shadows moving in the fog. A night watchman patrolled this street at 2 o'clock and saw nothing suspicious. Between 2 and 3 in the morning, someone broke the window and took those watches. The constable writes down every statement in his notebook. He records who said what and at what time. These written records become the backbone of the investigation. Without them, details blur and fade. Memory proves unreliable, but words on paper stay fixed and certain. By mid-morning, the constable has filled several pages with observations and statements. He has sketches of the broken window. He has descriptions of the missing watches. He has the pattern of that distinctive boot print. Now comes the next phase of early detective work. He must take all this information and figure out what it means. You watch as he reviews his notes. The broken glass pattern shows force from outside. The selective theft of only watches suggests someone who knew what they wanted. The timing between the night watchman's rounds and the neighbour's observation gives a narrow window. The boot print provides a physical detail that might identify the thief. In this era, police work relies heavily on local knowledge. The constable knows the people who live on his beat. He knows which residents work honest jobs and which ones have questionable reputations. He knows where stolen goods typically get sold. He knows the ways of crime in his district. He walks to a nearby public house where he knows certain individuals gather. The publican nods when the constable asks about strangers in the area. A man with a noticeable limp came in last night asking about buying pocket watches. He wore muddy boots and seemed nervous. He left before the publican could engage him in much conversation. This information matters. The constable adds it to his growing collection of facts. A man with a limp, muddy boots, interest in pocket watches, looking for buyers. The picture starts to take shape. You accompany the constable to the local pawn shop. The pawnbroker keeps detailed records of everything brought to him. The law requires this. He must write down who pawns what and when. The constable flips through the ledger looking for recent entries involving watches. Nothing from this morning yet. But he asks the pawnbroker to send word if anyone tries to sell 3 gold watches matching the stolen descriptions. This network of informants and cooperating businesses forms another crucial part of early detective work. Detectives cannot be everywhere at once. They need eyes and ears throughout the community. Shopkeepers, publicans, pawnbrokers, and even reformed criminals sometimes provide valuable information. The constable returns to the station to file his report. You watch him copy his notes into the official record book. Every detail gets preserved. The date, the time, the location, the nature of the crime, the witness statements, the physical evidence, the leads being pursued. Senior detectives review these reports daily. They look for similar info. 3 jewellery shops broken into over the past month. All during the early morning hours, all targeting specific valuable items rather than grabbing everything. This suggests someone with knowledge and planning rather than desperate opportunistic theft. You sit in the detective office as they discuss the cases. The room smells of tobacco smoke and old paper. Files stack up on every available surface. Maps of London cover one entire wall with pins marking crime locations. String connects related incidents. Red for robberies, blue for burglaries, yellow for assaults. One detective notices something interesting. The 3 jewellery shop break-ins all happened within a mile of each other. They all occurred between 2 and 4 in the morning, they all involved broken front windows, and in each case witnesses mentioned seeing a figure with an unusual gait moving away from the scene. This is pattern recognition. Before computers could analyse crime statistics, detectives had to spot connections themselves. They had to remember details from weeks or months ago. They had to see how separate incidents might actually be the work of one person or one group. The detective decides to stake out the remaining jewellery shops in that area. If the pattern holds, another break-in might happen soon. Several constables volunteer to spend their nights watching and waiting. They position themselves in doorways and alleys where they can observe without being seen. You join one constable on a cold November night. The hours pass slowly. Your feet grow numb from standing in one position. The fog rolls in thick and heavy. Every sound seems amplified in the darkness. A cat yowls somewhere nearby. A drunk staggers past singing off-key. A carriage rattles over distant cobblestones. Nothing happens that first night, or the second night, or the third. This is also part of early detective work. Patience, long hours of watching and waiting, the willingness to endure boredom and discomfort on the chance of catching someone in the act. On the 4th night, you see movement near the jewellery shop at the end of the street. A figure approaches from the east. The person walks with a distinctive limp favouring the left leg. They pause at the shop window and look around nervously. Then they pull something from their coat. In the dim lamplight you can see it is a short iron bar. The constable steps out from his hiding place before the window breaks. The suspect tries to run, but the limp slows them down. Within moments, the constable has them in custody. The iron bar clatters to the ground. And there on the suspect's left boot, visible even in the poor light, runs a distinctive crack across the sole. This is how detective work succeeds before fingerprints. Careful observation, detailed records, patient surveillance, pattern recognition, and sometimes a bit of luck combined with persistent effort. The suspect gets brought to the station. Now comes another crucial aspect of early detective work: the interview, the interrogation, the careful questioning designed to extract truth from evasion. You sit in the interview room. It contains only a wooden table and 2 chairs. A single oil lamp provides light. The detective sits across from the suspect and opens his notebook. He does not shout or threaten. He speaks calmly and asks simple questions. Where were you on the night of November 8th? The suspect claims to have been home sleeping. The detective writes this down. He then produces the statement from the publican about a limping man asking about pocket watches that same night. The suspect shifts uncomfortably. The detective points out the crack in the boot sole. He shows his drawing of the boot print from the crime scene. They match exactly. The suspect begins to sweat despite the cool temperature in the room. This technique relies on accumulating evidence and presenting it piece by piece. Each fact chips away at the story the suspect wants to tell. Each contradiction makes denial harder to maintain. The detective remains patient. He has all night. He can wait. Eventually, after hours of careful questioning, the suspect admits to the break-ins. He reveals where he hid the stolen watches. He explains that he needed money to pay gambling debts. The limp came from an old injury that never healed properly. He thought it would not matter. He did not realize how distinctive his walk appeared, or how easily someone could identify his boot prints. The watches get recovered. The suspect faces charges. The case closes, all without a single fingerprint analysis or DNA test. Just observation, documentation, interviews, and persistent detective work. But this represents only one type of crime in one city at one moment in history. Early detective work took many different forms depending on the location and the era. You need to understand how these techniques developed over time. Travel backwards several centuries to Renaissance Italy. You walk through Florence in the year 1520. The city buzzes with art and commerce. Markets fill the piazzas with merchants selling everything from silk to spices. But crime thrives here too. Thieves pick pockets in crowded spaces. Counterfeiters produce fake coins. Merchants cheat customers with false weights and measures. The authorities rely on informants to catch criminals. They recruit people from the criminal underworld itself. Former thieves know how thieves think and operate. They know the hiding spots and the secret signals. They know who sells stolen goods and who can be bribed for information. These informants work for reduced sentences or for payment. They move through the criminal world gathering intelligence. Then they report back to the authorities. This system has obvious flaws. Informants sometimes lie to settle personal scores. They might fabricate information to earn their fee. But without modern investigative tools, authorities depend on human sources for most of their information. You observe a magistrate questioning a merchant accused of selling underweight bread. The magistrate has no scientific instruments to test the claim. Instead, he calls witnesses. Other merchants testify about the accused's reputation. Customers describe being cheated. The baker's own apprentice, promised immunity, reveals how his master hollowed out the loaves to use less flour. The magistrate weighs all these testimonies against each other. He considers the character of each witness. Are they known to be honest? Do they have reasons to lie? Do their stories align with each other? This process of evaluating human testimony forms a crucial skill for early investigators. Written records also play an increasingly important role as societies become more literate. Merchants keep ledgers. Ships maintain logs. Governments record births, deaths, marriages, and property transfers. All these documents can provide evidence in criminal cases. You watch a merchant try to prove he was in Venice when a crime occurred in Florence. He produces receipts from Venetian merchants. He shows the log from the ship that carried him. The dates and signatures all confirm his alibi. Without these written proofs, he would have only his word against his accusers. The concept of using documents as evidence might seem obvious now, but it represents a significant development in detective work. It means investigators can check stories against objective records. They can verify claims independently. They can catch people in lies when the written evidence contradicts their statements. Move forward in time to 17th century England. You stand in a courtroom watching a handwriting expert testify. He holds 2 documents side by side. One is a will leaving a large estate to a distant cousin. The other is a known sample of the deceased person's writing. The expert points out differences in letter formation, pen pressure, and spacing. This represents an early form of forensic document analysis. Experts learn to recognize individual characteristics in handwriting. They study how people form their letters. They notice habits like crossing T's high or low, dotting I's to the left or right, connecting letters in distinctive ways. The expert testifies that the will appears to be a forgery. The handwriting shows attempts to mimic the deceased's style, but fails in subtle ways. The forger made S's differently. The baseline slant does not match. Several letter combinations reveal hesitation marks where the forger paused to think about how to form them. The jury finds the will fraudulent based largely on this handwriting analysis. The distant cousin faces charges of forgery and attempted fraud, all because someone developed the skill to examine handwriting as evidence. You begin to see how detective work gradually incorporates more specialized knowledge. It is no longer just about asking questions and following suspects. It starts to involve expertise in specific areas: handwriting analysis, document examination, even early chemistry for detecting poisons. Travel to Paris in the early 19th century. You enter the office of Eugène-François Vidocq, the first director of the French Criminal Investigation Department. Vidocq himself was once a criminal. He escaped from prison multiple times. He lived among thieves and knew their methods intimately. Then he switched sides and brought that knowledge to police work. His office contains filing cabinets filled with detailed records on known criminals. Each file includes physical descriptions, known associates, typical methods, and past crimes. Vidocq recognizes that information is power. The more details you collect about criminals, the easier they become to catch. He introduces the concept of undercover work. His agents dress as criminals and infiltrate gangs. They gather evidence from the inside. They learn about planned crimes before they happen. They identify criminal networks that previously operated in the shadows. You accompany one of his agents into a tavern frequented by thieves. The agent drinks and jokes with the regulars. He never asks direct questions, he just listens. Criminals talk. They brag. They share information. The skilled agent absorbs it all while maintaining his cover. Later, back at headquarters, the agent writes a detailed report. He names the people he met. He describes the crimes they discussed. He maps out relationships within the criminal network. This intelligence allows Vidocq to plan raids and arrests strategically. Vidocq also pioneers the use of plaster cast for preserving evidence. When investigators find a boot print at a crime scene, they pour plaster into it. Once the plaster hardens, they have a permanent copy of the print. They can compare it to suspects' boots. They can store it for future reference. You watch technicians carefully pour plaster into a print left in soft earth near a murder scene. They work slowly to avoid creating air bubbles. Once set, they lift the cast gently. It captures every detail of the boot sole, including a distinctive nail pattern and a worn heel. Later, when police arrest a suspect, they compare his boots to the cast. The match is exact. This physical evidence proves the suspect was at the crime scene. Combined with other evidence, it helps secure a conviction. These advances might seem simple compared to modern forensics, but they represent important steps forward. Investigators learn to preserve evidence. They learn to document it systematically. They learn to present it in court in ways that juries can understand. You move forward to the middle of the 19th century. The Industrial Revolution has transformed cities. Populations explode. Crime increases. Police forces struggle to keep up. Detectives need better methods. In London, the Metropolitan Police establish a detective branch. These plainclothes officers focus on investigating crimes rather than just patrolling streets. They develop techniques for shadowing suspects, conducting surveillance, and gathering intelligence. You follow a detective as he tracks a suspected murderer through London streets. The detective stays far enough behind to avoid detection, but close enough to see where the suspect goes. He notes every stop, every person the suspect talks to, every building the suspect enters. This kind of patient surveillance requires enormous skill. The detective must blend into crowds. He must change his appearance when necessary. He must anticipate where the suspect might go. If the suspect spots him, the entire operation fails. The detective follows his target for 3 days. He learns the suspect's routine: morning coffee at a specific cafe, visits to a boarding house in the afternoon, evening drinks at a public house near the docks. The detective writes all of this down in his notebook. On the 4th day, the suspect meets a woman at the boarding house. The detective cannot hear their conversation, but he sees money change hands. The woman leaves looking frightened. The detective follows her instead. She leads him to a small shop where she works. The detective approaches her carefully. He identifies himself and asks about the meeting. At first she refuses to talk. Then, when he assures her of protection, she reveals that the suspect has been blackmailing her. She witnessed him near the scene of a murder. He threatened to harm her family if she told anyone. This testimony provides the link investigators needed. The woman's presence near the crime scene places the suspect there too. Combined with other evidence, it builds a case strong enough to arrest him. This illustrates another key aspect of early detective work: building relationships with witnesses, earning trust, protecting those who come forward with information. Without the detective's patient approach, the woman might never have spoken. You observe how detectives in this era develop informal networks of contacts. Street vendors who notice unusual activity, landlords who know their tenants' habits, cab drivers who remember where they took passengers. All these people potentially hold pieces of information that might solve crimes. Smart detectives cultivate these contacts over years. They help people when they can. They show respect. They keep confidences. Then, when they need information, people willingly provide it. Consider the case of a missing child in Victorian London. A detective begins by talking to everyone in the neighbourhood. He asks gentle questions. Did you see the child yesterday? Did you notice any strangers? Did you hear anything unusual? Most people have nothing useful to report, but one old man mentioned seeing a carriage stopped on the corner around the time the child disappeared. He didn't think much of it at the time. Carriages stop on corners regularly, but something about this one seemed odd. The driver looked nervous. He kept glancing around. The detective asks for a description. The old man remembers the carriage was black with a distinctive brass lamp. The horse had white markings on its face. The driver wore a brown coat and a wide-brimmed hat. The detective takes this information to the cab companies and livery stables. He asks about carriages matching that description. Most companies keep records of which drivers took which vehicles on which days. After checking several businesses, he finds a match. The company produces the driver. The detective questions him carefully. Where did he go that afternoon? The driver claims to remember nothing unusual, just regular fares around the city. But the detective persists. He describes the corner. He mentions the old man who saw the carriage stop there. The driver's story begins to shift. Maybe he did stop there briefly. Maybe someone asked him for directions. He cannot quite recall. The detective notes these inconsistencies. An innocent person usually remembers clearly or admits they do not remember. Changing stories suggests something hidden. The detective obtains permission to search the driver's lodgings. There, hidden under the floorboards, he finds the child's torn dress. Confronted with this evidence, the driver confesses. He took the child intending to demand ransom, but the child became ill and died. Panicking, he disposed of the body in the river and kept the dress, meaning to burn it later. This tragic case demonstrates how detectives combine multiple techniques: careful questioning of witnesses, following up on small details, checking written records, patient interrogation, physical searches. Each step builds on the previous one until the truth emerges. You witness how detectives also learn to read people. They study facial expressions, they notice nervous gestures, they hear the tremor in someone's voice when they lie. These skills develop over years of experience interviewing countless witnesses and suspects. Some detectives become legendary for their ability to spot deception. They claim to see guilt written on a person's face. Of course, this is not magic. It comes from observing tiny behavioural cues most people miss. A person who lies might touch their face more often. Their eye contact figure might change. They might speak more quickly or more slowly than usual. These observations are not scientific. They can be mistaken. An innocent person might act nervous for many reasons. But combined with other evidence, behavioural cues sometimes point investigators in the right direction. Travel to America in the mid-1800s. You observe the Pinkerton National Detective Agency at work. Alan Pinkerton builds the first private detective agency in the United States. His agency takes on cases that local police cannot or will not handle. The Pinkertons develop extensive files on criminals. They collect photographs when possible. They record physical descriptions in minute detail: height, weight, hair colour, eye colour, distinguishing marks, scars, tattoos. Every detail gets documented and filed. When a new crime occurs, investigators consult these files. Does the method match anyone's known routine? Does the physical description fit any known criminals in the area? This systematic approach to criminal records improves detective efficiency enormously. You watch Pinkerton agents investigate a train robbery. They interview everyone who was on the train. They examine the scene where the robbery occurred. They follow the tracks the robbers left heading into the wilderness. The agents are skilled trackers. They can read signs in the landscape. Broken branches show where someone pushed through brush. Disturbed soil reveals where someone knelt. Scattered ashes mark where someone made camp. Following these traces, the agents track the robbers to a remote cabin. They do not rush in immediately. Instead, they watch and wait. They want to identify everyone involved. They want to catch the whole gang, not just one or two members who might be at the cabin while others remain free. After 2 days of surveillance, they see all the suspects together. Then they move in quickly. They move in. The element of surprise prevents resistance. The agents recover the stolen money. The entire gang faces arrest and prosecution. This case shows the value of patience and planning. Less experienced investigators might have rushed in and caught only some of the criminals. The Pinkertons waited until they could capture everyone and recover the evidence. You observe how detective work varies depending on the type of crime. A murder investigation differs from a robbery case. A fraud scheme requires different techniques than a kidnapping. Good detectives learn to adapt their methods to the specific circumstances. For financial crimes, detectives must understand business records. They need to trace money moving between accounts. They need to spot irregularities in ledgers. They need to recognize when numbers have been altered or fabricated. You watch an investigator examine a merchant's account books. The numbers look correct at first glance, but the investigator notices something odd. Several entries use slightly different ink. The handwriting looks similar but not quite identical. Closer examination reveals erasures under some numbers. The investigator compares these suspicious entries to corresponding receipts and invoices. The numbers do not match. Someone altered the books after the fact. The investigator traces the pattern. It shows money being siphoned off gradually over months. The merchant's bookkeeper stands accused of embezzlement. This case required no dramatic chases or confrontations. Just careful examination of documents, just attention to detail, just the patience to compare hundreds of entries looking for discrepancies. For murder cases, detectives must reconstruct what happened. They examine the body, they study the crime scene, they establish timelines, they identify who had means, motive and opportunity. You accompany a detective examining a murder scene in a wealthy home. The victim was found in his study with a fatal blow to the head. The room appears ransacked. Drawers hang open, papers scatter across the floor. It looks like a robbery gone wrong. But the detective notices details that seem wrong. The ransacking appears theatrical. Valuable items sit in plain view but were not taken. The papers on the floor are arranged too neatly for genuine chaos. Someone staged this scene to look like a robbery. The detective examines the wound more carefully. The angle suggests someone of similar height struck the blow. The victim was tall. Most household staff were considerably shorter. This narrows the suspects. The detective interviews the household. Everyone claims to have been elsewhere when the murder occurred. But the detective asks about the victim's schedule. Who knew he would be in his study at that time? Who had access to that part of the house? Who stood to gain from his death? One name keeps appearing in the answers: the victim's nephew. He was supposed to inherit a large sum. He had argued with his uncle recently about money. He was in the house that evening despite claiming to have left earlier. Confronted with these facts, the nephew's alibi falls apart. He admits to the argument but denies the murder. The detective presses harder. He describes the staged robbery. He explains how the evidence contradicts a random burglar scenario. Finally, the nephew breaks. He confesses. The argument turned violent. He struck his uncle in anger. Then, panicking, he tried to make it look like a robbery. He never expected anyone to see through the deception. This case illustrates how detectives use logic and reasoning to see past obvious interpretations. They question appearances. They look for what does not fit. They build their case on inconsistencies and impossibilities. You see how the best detectives develop almost encyclopedic knowledge of crime patterns. They know how burglars typically operate. They know how poisoners usually act. They know the habits of forgers and fraudsters and violent criminals. This knowledge lets them recognize when something does not match the expected pattern. By the late 1800s, detective work begins to incorporate more scientific approaches. A French police officer named Alphonse Bertillon develops a system he calls anthropometry. He proposes that if you measure enough parts of a person's body, you can create a unique identification. You watch Bertillon's assistants measure a suspect. They record the length of the head from front to back, the width of the head side to side, the length of the left foot, the length of the left forearm, the length of fingers, the distance between outstretched arms, 11 measurements in total. Bertillon argues that the odds of two people having exactly the same measurements for all 11 dimensions are astronomically small. Each measurement gets recorded on a card along with a photograph and physical description. These cards get filed systematically so investigators can search them. This system gains widespread adoption in France and then in other countries. For the first time, police have a supposedly scientific method for identifying repeat offenders. When someone gets arrested, their measurements can be compared to existing records to see if they have been arrested before under a different name. You observe the process of searching the files. A clerk takes the new measurements and uses them to narrow down the cards to check. Cards are organised by ranges of measurements. If the head length is 180 millimeters, you only check cards in that range. Then you narrow further by head width, and so on. The system works reasonably well for several years. Police identify repeat offenders who had been using false names. They solve cases by linking crimes through suspect identification. Bertillon becomes famous. His method spreads worldwide. But the system has significant flaws. Measurements depend on the skill of the person taking them. Small errors accumulate. People's measurements change slightly over time. The cards become increasingly difficult to search as files grow larger, and most fundamentally, the system cannot handle two people with very similar measurements. You witness the critical failure that undermines Bertillon's system. In 1903, a man named Will West arrives at Leavenworth Prison in Kansas. His measurements get taken. The records clerk searches the files and finds a card for William West with nearly identical measurements and a very similar appearance. The two men even have the same name, but they are not the same person. William West is already in prison serving a life sentence. Will West is a new arrival. The two men are not related. They just happen to have remarkably similar measurements and appearances. Bertillon's system cannot reliably distinguish between them. This discovery reveals the fundamental weakness of anthropometry. No matter how many measurements you take, coincidental matches can occur. The system is not as unique as Bertillon claimed. Meanwhile, another approach to identification has been developing quietly. Fingerprints. For centuries, people noticed that the ridge on fingertips varied between individuals, but no one had systematically studied whether these layouts were truly unique or whether they could be used for identification. You observe early fingerprint research in British India. A colonial administrator named William Herschel uses fingerprints on contracts to prevent fraud. He notices that fingerprints do not change over time. The same person always has the same ridge layout. In Argentina, a police official named Juan Vucetich develops a classification system for fingerprints. He identifies basic pattern types and creates a method for filing and searching fingerprint records. In 1892, a bloody fingerprint left at a murder scene provides the evidence to convict the killer. This represents one of the first times fingerprint evidence successfully solves a major crime. Back in Britain, Francis Galton publishes detailed studies of fingerprints. He calculates the mathematical probability of two people having identical fingerprints. The number is so large it essentially proves fingerprints are unique. He develops methods for comparing prints and identifying matching points. You watch as these different threads come together. By the early 1900s, police forces begin adopting fingerprint systems. The technology is simple. You press someone's finger onto an ink pad and then onto paper. The resulting print shows all the ridge details. These prints can be filed and searched. Scotland Yard establishes a fingerprint bureau. Detectives learn to dust crime scenes for latent prints. They use fine powder that adheres to the oils and sweat left by fingers touching surfaces. Brushes reveal the same layout. Photography preserves them. You observe detectives processing a burglary scene. They dust the windowsill where the burglar entered. Several clear prints appear. They photograph these prints carefully. Back at the bureau, an expert compares them to prints in the files. The expert examines the ridge layout point by point. He identifies specific features: a ridge ending here, a bifurcation there, an island, a spur. Each feature gets marked and counted. When he finds 12 matching points between the crime scene print and a file card, He declares a positive identification. The fingerprint belongs to a known burglar named Thomas Anderson. Detectives arrest Anderson. He denies involvement until confronted with the fingerprint evidence. The scientific certainty overwhelms his protests. He cannot explain how his fingerprints appeared at the scene if he was not there. This represents a revolution in detective work. For the first time, investigators have physical evidence that can definitively link a specific person to a specific crime scene. Witnesses can be mistaken, confessions can be coerced or false, but fingerprints do not lie. You see how this changes the nature of investigation. Detectives still use all the traditional methods. They still interview witnesses. They still build timelines and check alibis. They still cultivate informants and follow suspects. But now they have an additional powerful tool that can provide conclusive proof. The transition from Bertillon's measurements to fingerprints happens gradually. Some police forces resist change. They have invested heavily in anthropometry equipment and training. They are reluctant to abandon it. But the Will and William West case makes the superiority of fingerprints undeniable. By 1910, fingerprinting has largely replaced anthropometry in most developed countries. Police bureaus maintain massive fingerprint files. Every arrest results in fingerprints being taken and filed. Crime scenes get examined for latent prints as a matter of routine. You observe how this affects detective work in practice. A series of burglaries plague a neighbourhood. Traditional investigation yields few leads. No witnesses saw anything useful. The stolen items have not appeared at any known fences. The burglar seems to strike randomly with no clear pattern, but at each scene, investigators find fingerprints. The same prints appear at multiple burglaries. This tells detectives that one person is responsible for all of them. They can now focus their investigation instead of treating each burglary as a separate incident. They search the fingerprint files. The prints do not match anyone in the system. This tells them the burglar has no prior arrests. They are dealing with either a first-time criminal or someone who has always avoided capture. The detectives increase surveillance in the area. They wait for the next burglary. When it occurs, they process the scene immediately and find the same fingerprints. But they also find something new. A partial palm print on a window frame. Palm prints work the same way as fingerprints. The ridge layout on palms are unique. By checking the palm print against suspects, they can potentially identify the burglar. The detectives begin checking everyone in the area who fits the general description from the few witness sightings. Young male, average height, dark coat. They ask people to volunteer their palm prints for elimination purposes. Most people cooperate. They want the burglaries to stop. One by one, their palm prints are checked and ruled out. But one young man refuses. He says he does not trust the police. He claims it violates his rights. He becomes defensive and hostile. The detectives cannot force him to provide palm prints without cause, but his refusal arouses suspicion. They watch him carefully. They ask neighbours about him. They learn he has been spending money freely lately despite having no obvious job. Eventually, they obtain enough evidence for a warrant. They search his room and find some of the stolen items. With this evidence, they arrest him and take his fingerprints and palm prints. They match perfectly to the prints from the burglary scenes. This case shows how fingerprints complement traditional detective work. The prints proved that one person committed all the burglaries. The prints eventually identified that person. But between those 2 points, detectives still needed to use observation, interviews, surveillance, and logical deduction. You reflect on how far detective work has come. From the constable with his notebook sketching boot prints in the mud to experts analysing fingerprint minutiae under magnifying glasses. The fundamental skills remain important. Observation, documentation, interviewing, building networks of informants, patient surveillance, logical reasoning. But science adds new dimensions. Fingerprints provide certainty where before there was only probability. Photographs preserve crime scenes better than sketches. Chemical analysis can detect poisons that produce no obvious symptoms. Microscopes reveal details invisible to the naked eye. You consider what has been lost in this transition. The romantic image of the brilliant detective who solves crimes through pure deductive reasoning becomes less realistic. Sherlock Holmes could examine a crime scene and announce the solution through logical inference. Real detectives increasingly rely on scientific laboratories and technical experts. But something important has been gained too. Justice becomes more reliable. Innocent people are less likely to be convicted based on mistaken witness identifications or forced confessions. Guilty people are harder to escape punishment when physical evidence links them to crimes. The early decades of the 20th century see continued refinement of detective techniques. Fingerprint classification systems improve, filing methods become more efficient, photography advances allow better crime scene documentation, ballistics experts learn to match bullets to specific guns, blood typing can sometimes exclude or include suspects. You watch detectives in the 1920s working a murder case. They photograph the scene from multiple angles. They dust for fingerprints on every surface. They collect the bullets for ballistics analysis. They take blood samples for typing. They interview witnesses and write detailed reports. They build a comprehensive case file that includes scientific evidence, witness testimony, and logical deduction. This represents the synthesis of old and new methods. The detectives still use the fundamental techniques developed over centuries, but they enhance those techniques with modern science. The combination proves more powerful than either approach alone. The transition from pre-fingerprint detective work to modern forensics happens gradually across decades. Different jurisdictions adopt new methods at different rates. Rural areas lag behind cities. Some countries lead while others follow, but the overall direction remains clear. Detective work becomes increasingly scientific and systematic, yet the human element never disappears entirely. Machines cannot interview witnesses. Laboratories cannot cultivate informants. Computers cannot earn a community's trust. The best detectives combine technical knowledge with interpersonal skills. They understand both science and human nature. You stand again in that foggy London street where this journey began. But now you see it differently. You understand that the constable with his notebook was not primitive or backwards. He was using the best methods available to him. He was building a foundation that would support all future developments in detective work. His careful observations taught later generations the importance of documenting everything. His patient interviews demonstrated the value of listening. His cultivation of local knowledge showed the power of community connections. His willingness to stake out cold alleys night after night exemplified the dedication required. Fingerprints made detective work more scientific, but they did not make it automatic. Detectives still need to know where to look for prints. They still need to interpret what the evidence means. They still need to connect physical traces to human behaviour. As you prepare for sleep, you can appreciate how mystery solving evolved. Each generation of detectives built on the work of those who came before. Each new technique supplemented rather than replaced older methods. The progression from bootprints in mud to fingerprints and databases took decades of patient development. The detectives who worked before fingerprints were not less intelligent than modern investigators. They simply had fewer tools available. Within those limitations, they developed remarkable skills. They learned to read people and situations. They learned to see the same thing where others saw only chaos. They learned to persist when leads went cold and cases seemed hopeless. Their legacy continues in modern detective work. The notebooks are now digital. The surveillance happens through cameras and electronic tracking. The informant networks extend across computer systems. But the fundamental principles remain. Observe carefully. Document thoroughly. Interview skillfully. Think logically. Never give up. You close your eyes and imagine that foggy London morning one last time. The constable writes in his notebook. His pencil moves steadily across the page. Each word captures a detail that might solve the crime. Each observation might be the key that unlocks the mystery. He works patiently and thoroughly because he knows that justice depends on getting the details right. In the darkness, you feel the connection across centuries. Every detective who ever tried to solve a mystery, every investigator who ever pursued truth through careful observation and patient effort, they form an unbroken chain linking that constable in 1863 to investigators working today. The methods changed, the tools improved, but the dedication remained constant. The commitment to finding truth, the willingness to work long hours on difficult cases, the satisfaction of finally solving what seemed impossible. These things connect all detectives across all eras. You drift towards sleep with these thoughts. The fog rolls through your mind like that London morning. Questions dissolve into dreams. Mysteries blur into peaceful darkness. And somewhere in that transition between waking and sleeping, you understand something profound about human persistence and ingenuity. We solve problems with whatever tools we have available. We build on what came before. We gradually improve our methods through experience and innovation. And we never stop trying to find better ways to uncover truth. The detective story never ends. It just evolves. From bootprints to fingerprints to DNA analysis to digital forensics. Each era brings new challenges and develops new solutions. but the fundamental human desire to solve mysteries remains unchanged. You rest now in the knowledge that human cleverness has always found ways to pursue justice. Before Fingerprints, detectives relied on sharp eyes and patient effort. After Fingerprints, they combined scientific tools with those same fundamental skills. The future will bring changes we cannot yet imagine, but the dedication to uncovering truth will persist. Before sleep arrives completely, you revisit other remarkable cases from the era before Fingerprints. Each one teaches something about the ingenuity and persistence of early detectives. Consider the case of the missing diamonds in Amsterdam in 1878. A wealthy merchant reported that a fortune in gems had vanished from his safe. The safe showed no signs of forced entry. Only 3 people knew the combination: the merchant himself, his business partner, and his most trusted clerk. The investigating detective interviewed all 3 separately. Each claimed innocence. Each had an alibi for the time when the theft likely occurred. The merchant was at his club with witnesses. The partner was visiting family in Rotterdam. The clerk was at church for evening services. The detective could have stopped there. No evidence pointed to any suspect, but something bothered him about the clerk's demeanour. The young man seemed too calm. Most people faced with accusations of major theft show some emotional reaction even when innocent. This clerk remained perfectly composed. The detective decided to verify the church alibi thoroughly. He visited the church and spoke to the pastor. Yes, the clerk attended services that evening. The pastor remembered seeing him. But when pressed for details, the pastor admitted he only saw the clerk at the beginning of the service. The church was crowded. He could not say with certainty that the clerk remained for the entire time. This opened a possibility. The clerk could have arrived at church to be seen, slipped out during the service, committed the theft, and returned before the service ended. The church sat only a few blocks from the merchant's office. The timing could work. The detective then investigated how the clerk might have learned the safe combination. He spoke to the merchant's wife. She mentioned that her husband often worked late at the office with the clerk present. Could the clerk have observed the merchant opening the safe? The detective examined the office layout. The safe sat in a corner behind the merchant's desk. From the clerk's usual position at his own desk, he could not see the safe dial directly. But a large mirror hung on the wall across from the safe. The merchant probably never noticed that this mirror reflected his movements at the safe perfectly visible from the clerk's position. The detective tested this theory. He stood where the clerk usually sat and asked someone to open the safe. Sure enough, he could clearly see the entire combination dialed in the mirror's reflection. Over months of working late evenings together, the clerk had ample opportunity to memorize those numbers. But proving this theory required more than speculation. The detective needed evidence. He obtained a warrant to search the clerk's lodgings. In a locked trunk hidden under the floorboards, he found the missing diamonds. Confronted with this discovery, the clerk confessed. He had indeed memorized the combination from the mirror reflection. He slipped out of church during a lengthy sermon. He went to the office, opened the safe, took the diamonds, and returned to church before anyone missed him. He planned to sell the gems gradually and emigrate to America. This case demonstrates how detectives had to think about sightlines and reflections, and all the ways someone might secretly observe information. They had to question alibis not by disproving them entirely, but by finding gaps and possibilities within them. They had to trust their instincts about human behaviour while backing those instincts with solid evidence. You travel to New York City in 1885. A series of arsenic poisonings has the city frightened. 3 people have died over the past 6 months. All were wealthy. All died after sudden mysterious illnesses. All showed symptoms consistent with arsenic poisoning. The detective assigned to the case faces a difficult challenge. Arsenic was commonly available. It was sold openly for killing rats. Anyone could purchase it. The victims had no obvious connections to each other. They lived in different neighbourhoods. They moved in different social circles. They had different occupations. The detective begins by studying the victims' final days in detail. What did they eat? Who did they see? Where did they go? He interviews family members, servants, doctors, and friends. He fills notebook after notebook with information. A pattern gradually emerges. Each victim had received a gift of expensive chocolates shortly before falling ill. The chocolates came in elegant boxes with cards expressing admiration. The cards were unsigned. The victims assumed they came from secret admirers and ate them without suspicion. The detective now has a crucial lead. Someone is sending poisoned chocolates to wealthy victims. But who? And why these particular people? He investigates the chocolate shops. None of the victims purchased such chocolates themselves. The boxes must have been bought by the killer. The detective shows descriptions of the boxes to every confectioner in the city. Most recognise the style. It comes from a particular high-end shop on Fifth Avenue. The shop owner remembers selling several such boxes over the past year. He describes the customer as a well-dressed middle-aged woman wearing a veil. She always paid cash. She never gave her name. She seemed nervous and hurried. This description helps but does not identify anyone specific. Thousands of women in New York fit that general description. The detective needs more information. He returns to studying the victims. What connected them? He digs into their pasts. He examines their business dealings and family histories. He looks for any intersection in their lives, no matter how distant. Finally, he finds it. 20 years earlier, all 3 victims served on a jury together. They convicted a man of murder. The man was hanged. He left behind a wife and young daughter. The detective locates the widow. She died years ago. But the daughter is still alive. She's now a middle-aged woman who matches the confectioner's description. She lives modestly despite inheriting a small amount of money from her mother. The detective investigates her movements. She'd been seen near each victim's home shortly before the poisoned chocolates were delivered. She'd used different names to rent rooms in those neighbourhoods. She had purchased rat poison from several different shops. With this evidence, the detective obtains a warrant. He searches her home and finds the same elegant chocolate boxes. He finds receipts from the confectioner. He finds a list of other jury members who convicted her father. She admits everything. She spent 20 years planning revenge against everyone responsible for her father's death. She believed him innocent. She wanted them to suffer as her family had suffered. The detective has stopped her before she could poison the remaining jury members. This case shows how detectives must look beyond the obvious. The victims seemed random. Only by researching their histories could the connection be found. The investigation required patience and meticulous record-keeping. Without notebooks full of details about each victim's past, the link to that long-ago trial might never have been discovered. You observe a counterfeiting investigation in Paris in 1890. Fake bank notes have appeared throughout the city. They are excellent forgeries. Most shopkeepers and bank tellers cannot distinguish them from genuine currency. The forgeries threaten to undermine confidence in French money. The detective examining the fake notes uses a magnifying glass to study every detail. The paper quality is nearly perfect. The printing is excellent. The watermarks look correct. But under close examination, tiny differences appear. The genuine notes use a particular shade of blue ink that contains ultramarine pigment. This pigment produces a specific colour under certain lighting conditions. The forged notes use a similar but slightly different blue. The difference is almost imperceptible to the naked eye, but the detective learns to spot it. He also notices that the serial numbers on the fake notes follow a pattern. They all fall within specific ranges. This suggests the forger produced them in batches. By tracking which fake notes appear where, the detective can map the distribution network. Most forgeries turn up in shops and markets on the left bank. The detective stations observers at key locations. They watch for anyone spending unusual amounts of money with different vendors. They note descriptions and follow suspects. One man appears repeatedly. He visits multiple shops each day making small purchases with large bills. He always receives change in genuine currency. He seems to have an endless supply of bills to spend. The detective follows this man to a warehouse near the river. Over several days of surveillance, he observes people entering with bags and leaving empty-handed. Something is being distributed from this location. The detective organises a raid. Inside the warehouse, authorities find printing presses, engraving tools, special paper and inks. They find thousands of counterfeit notes ready for distribution. They arrest a dozen people, including the master engraver who created the plates. The engraver had worked for the official mint years earlier. He knew exactly how genuine currency was produced. He had acquired the skills and knowledge to replicate the process. Only the most careful examination could detect his forgeries. This case demonstrates how detective work sometimes requires specialized knowledge. The detective needed to understand printing techniques, paper quality, and ink composition. He needed to recognize similarities in serial numbers. He needed to organize surveillance and coordinate raids. Multiple skills combined to solve a complex crime. You move to a rural English village in 1895. A farmer has been found dead in his field. At first, it appears to be a tragic accident. Perhaps his heart failed while working. But the local constable notices details that seem wrong. The body lies face down in freshly ploughed earth, but the farmer's hands are clean. If he'd been working, his hands would be dirty. His boots show no mud despite the wet field. His plough stands unused at the field's edge. The horse is still hitched to it, looking restless. The constable examines the body more carefully. He finds a wound on the back of the head hidden by the farmer's hat. This was no accident. Someone struck the farmer from behind. The constable questions everyone who knew the farmer. Most villagers liked him. He had few enemies. He owed no debts. He had no known disputes with neighbours. Why would anyone want him dead? The constable learns that the farmer recently discovered something on his land. He had been digging a drainage ditch and unearthed an old metal box. Inside were gold coins from the previous century. The farmer told several people about his discovery. He planned to report it to authorities as the law required. But not everyone thought the treasure should go to the government. One neighbour believed the gold should belong to whoever found it. This neighbour had argued with the farmer about it. The argument ended badly with the neighbour threatening to take what he felt was rightfully his. The constable questions this neighbour. The man claims he was home all morning. His wife confirms this. But the constable notices mud on the man's boots that matches the field where the farmer died. The man's knuckles show fresh bruising consistent with striking someone. The constable searches the neighbour's property and finds the box of gold coins hidden in the barn. Confronted with this evidence, the neighbour confesses. He killed the farmer intending to steal the treasure. He tried to make it look like the farmer simply collapsed while working. This case shows how even small details matter. Clean hands in a dirty field, mud on boots, bruised knuckles, each observation added to the picture. The constable's knowledge of his community helped him identify who might have motive. His careful examination of the scene revealed the truth. You witness a kidnapping case in Chicago in 1900. A wealthy industrialist's young son vanishes while walking home from school. A ransom note arrives demanding $50,000. The note warns against involving police. The family contacts authorities anyway. The detective assigned to the case examines the ransom note carefully. The handwriting appears deliberately disguised. Letters are formed awkwardly as if written with the wrong hand. But some habits reveal themselves despite the disguise. The writer consistently crosses T's slightly to the left. The letter S always curves more at the bottom than the top. These might help identify the writer if investigators can compare the note to samples from suspects. The note itself provides clues about the writer. The paper is common stock available at any stationer, but the envelope shows a partial postmark from a specific postal station on the north side of the city. This narrows the search area. The detective also analyses the language in the note. Certain phrases suggest the writer has education. The grammar is correct. The vocabulary is sophisticated. This is not a desperate criminal from the slums. This is someone with schooling and perhaps social standing. The detective investigates who knew about the boy's routine, who knew which route he took home from school. The list is surprisingly small. The family employed few servants. The boy had few friends outside his immediate social circle. One name appears that seems unlikely but cannot be eliminated: the boy's tutor. A young man hired to teach Latin and mathematics. He was well educated but always seemed to need money. He gambled frequently and had debts. The detective obtained samples of the tutor's handwriting from lesson plans and correspondence. Despite the disguise in the ransom note, those characteristic T-crosses and S-curves appear in the tutor's writing. That means there's a match. The detective arrests the tutor and searches his rooms. He finds the boy unharmed but locked in a closet. The tutor had convinced the boy that this was a game they were playing. He planned to collect the ransom and flee to Europe. This case shows how analysing handwriting can identify criminals even when they try to disguise their writing. It shows how knowledge of a victim's routine helps identify who had opportunity. It shows how detectives must consider even unlikely suspects when the evidence points in that direction. You observe a case of art theft in Rome in 1905. A valuable Renaissance painting disappears from a private collection. The owner's palazzo has extensive security. Guards patrol the grounds. Doors remain locked. Windows have bars. Yet somehow the painting vanished without any signs of forced entry. The detective examines the empty frame still hanging on the wall. The painting was cut from it with a sharp blade. This was done carefully to avoid damaging the canvas. The thief knew how to handle valuable art properly. The detective studies the room's layout. The windows are indeed barred. The door locks from inside. The only other entrance is through the owner's private chambers. Examining the room more carefully, the detective notices the fireplace is large and ornate. He looks up the chimney and sees that it connects to an old shaft that once served as a servant's passage between floors. The detective explores the cellar and finds evidence that someone recently opened the sealed passage. Fresh scrape marks show where a wooden panel was pried loose. Following these traces leads to a coal chute that provides access from outside. He questions the oldest servants. One elderly man remembers the passage from his youth. He mentions that he showed it once to his nephew, who was curious about the palazzo's history. That nephew works as a restorer of old paintings. The detective investigates the nephew and discovers he recently paid off large gambling debts. A search of his workshop reveals tools and materials consistent with the theft. Under questioning, the nephew admits everything. He used his knowledge of the palazzo's architecture to steal the painting. This case demonstrates how detectives must understand architecture and history. They must think about old passages and forgotten routes. They must consider who has specialized knowledge that could enable a particular crime. You travel to San Francisco in 1908. A series of warehouse fires plague the waterfront. Each fire starts in the middle of the night. Each destroys valuable cargo. Insurance companies suspect arson, but cannot prove it. The detective visits each fire scene after the flames die down. At one scene, he finds melted glass and twisted metal showing the fire burned extremely hot in one specific location. This suggests an accelerant was used. He collects samples and sends them to a chemist who reports finding traces of kerosene mixed with other chemicals. The detective investigates who might benefit from these fires. He discovers an interesting pattern. Each warehouse that burned was scheduled to ship cargo to a specific merchant house. That merchant house then had to purchase replacement goods from a competing supplier at higher prices. The detective investigates this supplier's employees. One worker was recently fired from his previous job at the shipping company. That worker was seen near the waterfront late at night before several of the fires. Surveillance leads to the final evidence. The detective observes him meeting with the supplier's owner, discussing plans for the next fire. Police move in to make arrests. The arsonist confesses to setting the fires for payment from the competing supplier who wanted to eliminate business rivals. This case shows how detectives must understand business relationships and economic motives. They must recognize patterns across multiple incidents. They must use scientific analysis when available. These stories from the era before Fingerprints reveal the breadth and depth of early detective work. Investigators developed remarkable skills using the tools available to them. They learned to observe minutely. They learned to question effectively. They learned to think logically about causes and effects. They learned to persist through difficulty. The arrival of fingerprint technology did not replace these skills. It enhanced them. Modern detectives still observe crime scenes carefully. They still interview witnesses and suspects. They still build cases through patient accumulation of evidence. They still use logic and deduction. They simply have additional scientific tools to support their work. You consider one final aspect of early detective work that deserves attention: the psychological understanding that developed through experience. Detectives learned to recognize markings in human behavior that help them anticipate criminal actions and identify deception. A veteran detective in Berlin in 1910 could walk into a room and sense when something was wrong. He had interviewed hundreds of suspects over his career. He knew how innocent people typically reacted to accusations. They showed anger or confusion or fear, but they also showed a quality of genuine bewilderment that was difficult to fake. Guilty people often acted differently. Some became overly calm and controlled. They prepared their stories too carefully. Their answers came too quickly without the hesitation that accompanies genuine memory. Others became defensive in ways that seemed out of proportion to the situation. They protested too much. The skilled detective learned to recognize these. He understood that nervousness alone proved nothing. An innocent person might be terrified of police. A guilty person might appear completely at ease. But over time, subtle differences emerged that trained observers could detect. You watch this veteran detective interview a suspect in a murder case. The suspect maintains perfect composure while denying everything. His alibi sounds rehearsed. Every detail fits together smoothly. Too smoothly, perhaps. The detective asks seemingly random questions. What was the weather like that day? What did you eat for breakfast? What song was playing in the cafe? The suspect answers each question with confidence, but the detective notices that these peripheral details come as quickly as the alibi itself. Most people struggle to remember incidental information from days past. This suspect recalls everything with unusual clarity. The detective changes tactics. He mentions details about the crime that were never made public. He watches the suspect's reaction carefully. Does the suspect show surprise at learning new information? Or does something in his expression suggest he already knew these facts? A tiny flicker crosses the suspect's face when the detective describes the murder weapon. Just a momentary tightening around the eyes. Nothing dramatic. But the detective has spent decades watching people's faces. He knows that flicker. It is recognition. The suspect has seen that weapon before. The detective presses this advantage. He describes the weapon in more detail. He mentions where it was found. The suspect's carefully maintained composure begins to crack. Small signs of stress appear. He touches his face more frequently. His breathing quickens slightly. He shifts in his chair. These observations are not scientific evidence. They would not stand alone in court. But they tell the experienced detective where to focus his investigation. They suggest which lines of questioning might prove productive. They indicate when someone is hiding something worth pursuing. Combined with other evidence and testimony, these behavioural observations help solve the case. The detective's psychological insight guides the investigation toward productive avenues. His ability to read people complements his ability to analyse physical evidence. This psychological dimension of detective work developed naturally through practice. The most successful investigators were often those who combined sharp observational skills with deep understanding of human nature. They could spot a liar. They could recognise when someone was protecting another person. They could sense when a witness held back crucial information out of fear rather than malice. These skills proved especially valuable in the era before fingerprints. Without scientific certainty, detectives relied heavily on their judgment about people. They had to decide which witnesses seemed credible. They had to determine which suspects deserved further investigation. They had to build cases on foundations of human testimony and behavioural observation. The best detectives approached this responsibility with humility. They knew their intuitions could be wrong. They knew that innocent people sometimes acted suspicious, while guilty people sometimes seemed honest. They did not rely on psychological insights alone. They always sought corroborating evidence and multiple sources of confirmation. Yet within these limitations, their psychological understanding proved remarkably effective. Many guilty people confessed when confronted by detectives who clearly understood their motives and methods. Many investigations succeeded because detectives correctly identified who was lying and who was telling the truth. As you drift towards sleep, you reflect on the complete picture of detective work before fingerprints. It was patient observation of physical details. It was careful documentation in notebooks and files. It was skillful interviewing and interrogation. It was cultivation of informant networks. It was understanding of chemistry and handwriting and document analysis. It was surveillance and stakeouts. It was logical deduction from available evidence. And it was psychological insight into human behaviour. All these elements combined to create a profession that solved crimes through intelligence and persistence, rather than through technology. The detectives of that era proved that human cleverness could overcome limited tools. They showed that dedication and skill matter more than equipment. Their legacy continues today. Every modern investigator builds on foundations laid by those early detectives. The notebooks are digital now. The surveillance uses cameras and computers. The scientific tools are sophisticated beyond imagination. But the fundamental approach remains the same. Observe carefully, think clearly, never give up on finding truth. Sleep comes gently now. Your breathing slows. The modern world fades. And in that peaceful space between thought and dream, you carry with you the stories of detectives past, their careful observations, their patient interviews, their detailed records, their persistent efforts to solve mysteries one clue at a time. The foggy London street dissolves. The constable puts away his notebook. The case closes, and you rest. Imagine what the world was like in 774, when Charlemagne was busy becoming the Holy Roman Emperor, and most people thought the earth was the centre of everything. It was a time when the most amazing piece of technology you had was a water mill. The news travelled as fast as a horse, and you learned about the universe from a mix of ancient Greek philosophy, Christian theology, and what your grandfather swore he saw in the sky that one night. You lived in a world where the heavens were as reliable as clockwork, or at least as reliable as a sundial, which was the most accurate timepiece you had. The sun rose, the moon went through its phases, and the stars moved in patterns that people have known about since the beginning of recorded history. In a time when so much of life was uncertain, this celestial reliability was more than just useful, it was very comforting. Hollywood might make you think that people in the Middle Ages were primitive, but they weren't. They were skilled astronomers who could predict when eclipses would happen, figure out when Easter would be years in advance, and find their way by the stars with amazing accuracy. Monastery libraries kept careful records of comets, the movements of planets, and other strange things that happened in the sky for hundreds of years. These people didn't freak out at every shooting star. They were experienced skywatchers who could tell the difference between normal and amazing. In comparison to how complicated things are today, the medieval view of the universe was very simple. Earth was in the middle of everything, and around it were crystal spheres that held the moon, planets and stars in their never-ending dance. The Empyrean was beyond the sphere of fixed stars, and it was where God lived in perfect light. It was a universe that made sense, where everything was in the right place and had a reason for being there. People in 774 lived their lives in ways that most people today have forgotten. You woke up with the sun because candles were expensive and firelight was hard to find. The sun's path across the sky, not the clock, told you how long your workday was. Farmers knew that certain crops should be planted when certain stars came up at dawn. And monks split their prayers into different parts based on the canonical hours that followed the sun's movement. Most people stayed in the same place their whole lives, only moving a few miles away. The next valley, the closest market town, and maybe the regional cathedral were the only things that could reach your world. If you were lucky enough to go on a pilgrimage, you could see them. It would have seemed as strange to you that things happening millions of miles away in space could affect your daily life, as the idea that you could one day video chat with someone on the other side of the world. But even in this small world, people were very aware of the sky. The night was really dark because there were no electric lights to wash out the stars. This made celestial events much more visible and dramatic than they are now. Everyone could see a bright comet, not just astronomers with special tools. The Milky Way looked like a cosmic highway across the sky, and meteor showers were events that whole villages would stay up to watch. Everything was affected by religion, and people often saw celestial events through religious lenses. Strange things happening in the sky could be signs of political change, warnings from God about how to act morally, or signs of the end of the world. The line between astronomy and astrology was not clear, and both were seen as valid ways to understand God's will. In 774, most scholars were monks and priests who could read the works of ancient scholars like Ptolemy, Aristotle, and Pliny the Elder. These texts helped people understand how the world worked, but medieval scholars weren't just passive recipients of ancient knowledge. They also made their own observations and sometimes came to different conclusions than classical authorities. People were curious and observant at the time, but only up to a point. Natural philosophers endeavoured to comprehend God's creation through meticulous examination, holding the belief that the natural world disclosed divine truth. It was important to pay attention to strange events not only because they were scientifically interesting, but also because they could have spiritual meaning. Trade networks linked even the most isolated communities to larger cultural exchanges. A strange story seen in one monastery could travel hundreds of miles along pilgrimage routes, merchant paths, and diplomatic channels to reach chroniclers. Information moved slowly but steadily, making a medieval version of an intellectual network that could keep and share important observations. In this carefully planned world of 774, where the stars followed familiar patterns and strange things happened so rarely that they were memorable, something amazing was about to happen. The universe was getting ready to send Earth a cosmic message that would be recorded in tree rings, ice cores, and historical records. It would take humans over 1,000 years to make the scientific tools needed to figure out what it meant, but the people of 774 didn't know they were about to see proof of one of the most powerful events in the history of the universe. They went about their daily lives, taking care of their fields, praying and looking at the stars they knew. They had no idea that invisible radiation was about to fall from space in amounts that wouldn't be seen again for another 1,000 years. Imagine that you're relaxing in your medieval cottage on a normal night in 774, maybe sometime between late winter and early summer. The exact date is lost to history, like so many other details from that time. The sky looks normal, the stars shine as brightly as they always do, and nothing seems out of the ordinary for any other night in your life. But something amazing is happening high above the Earth's atmosphere that people won't fully understand until the 21st century. A huge burst of high-energy particles is hitting Earth's upper atmosphere with a force that has never been seen before. These cosmic rays, which wouldn't be called that for another 1,000 years, are falling from space like an invisible waterfall of radiation, carrying energies that are much bigger than anything human technology can make even today. One of the biggest mysteries of medieval astronomy is where this cosmic bombardment came from. This is partly because the people who were affected couldn't see it directly. This event didn't make any visible light, change the night sky in any big ways, or show any clear signs that something strange was happening, unlike a comet or supernova. It was like being in the middle of the most amazing fireworks show in the history of the universe while wearing a blindfold. What was going on, even though it couldn't be seen, was truly amazing. Protons and other high-energy particles were hitting Earth's atmosphere at almost the speed of light. This caused secondary particles to rain down toward the surface. The intensity was about 20 times higher than normal cosmic ray levels. It was like if the normal gentle spring rain turned into a heavy downpour that lasted for months. These cosmic rays were hitting nitrogen atoms in the upper atmosphere and changing them into carbon-14, the radioactive isotope that archaeologists use to date old things. This process usually happens at a steady, predictable rate, like a cosmic clock that has been ticking steadily for thousands of years. But in 774, that clock suddenly sped up, making carbon-14 at levels that would leave a mark on every living thing on Earth forever. Trees did a great job of recording this event, even though they didn't know they were acting as cosmic historians. They took in extra carbon-14 as they grew in 774 and 775, which scientists would later recognise as one of the most dramatic spikes in the radiocarbon record. Every tree ring from that time held proof of this storm that couldn't be seen. The cosmic rays were also making other isotopic signatures, like beryllium-10 in ice cores and chlorine-36 in rocks. These records of the same event were spread out all over the world, like pieces of a puzzle that wouldn't be put together for more than 1,000 years. The universe was putting invisible tags on Earth that said, something big happened here in 774. But what could have caused such a strong burst of cosmic radiation? Scientists today have come up with a number of possible explanations, each one more dramatic than the last. Maybe two neutron stars, which are city-sized objects with the mass of our sun, crashed into each other in our cosmic neighbourhood, sending out a short but very strong burst of high-energy particles. You can start to understand the energies involved if you picture two atomic nuclei the size of Manhattan crashing into each other at speeds of thousands of miles per second. Another possibility is that a magnetar, which is a neutron star with a magnetic field trillions of times stronger than Earth's, had a huge flare that sent radiation across interstellar space. Magnetars are like crazy cosmic lighthouses that sometimes explode with energy that can be seen from thousands of light years away. If one of these huge stars hiccuped in the right way, Earth would have been in the way of an invisible tsunami of high-energy particles. One of the most interesting possibilities is that Earth saw a gamma-ray burst, which is one of the strongest explosions known to physics, when huge stars collapse into black holes or when strange stellar remnants collide with each other in a way that destroys everything. These events can outshine whole galaxies for a short time. A gamma-ray burst that hit Earth directly could have caused the cosmic ray spike that was seen in 774. The timing of this event is what makes it so interesting. From 774 to 776, medieval records from all over the world talked about strange things that happened, like strange lights in the sky, strange weather patterns, and other things that chroniclers thought were worth noting. These observations may have natural explanations that have nothing to do with cosmic rays, but the connection is interesting enough to make you think about what people who looked at the sky in the Middle Ages might have seen that they couldn't explain. The cosmic ray event of 774 was short by astronomical standards. It probably lasted months instead of years. However, it was strong enough to leave permanent marks in Earth's natural records. It was like getting a cosmic telegram in a language that people wouldn't be able to read for more than 1,000 years, when they had better tools and theories. From a medieval point of view, this storm was completely invisible to any technology or observation method that was available at the time. Cosmic ray events don't leave any visible signs that would alert people, unlike eclipses, comets, or supernovae. The people of 774 were going through one of the most amazing astrophysical events in history, but they had no way of knowing it was happening. But in a way, they were all part of a cosmic experiment, working together without even knowing it to make a time capsule that would help scientists learn more about both medieval history and astrophysics. Every tree that grew, every piece of ice that formed, and every living thing that developed during those important years was quietly leaving behind evidence that would be very useful to researchers 13 centuries later. Even though medieval people couldn't see cosmic rays, the years 774 to 776 were not boring for the people who lived through them. There are records from Europe and Asia that talk about strange things that happened during this time. We can't say for sure that cosmic radiation caused all of them, but the timing is interesting enough to make you wonder what people in the Middle Ages were really seeing. Imagine being a monk in a scriptorium in 775, keeping the chronicle that tells the story of your monastery's most important events. You dip your quill in oak gall ink and write down that the winter has been unusually harsh and that strange colours have appeared in the northern sky a few times. You don't know that more cosmic radiation could change the chemistry of the atmosphere in small ways, or that high-energy particles could cause strange auroras to appear at lower latitudes than usual. The Anglo-Saxon Chronicle, which is one of the most reliable sources from the Middle Ages, says that a red crucifix appeared in the sky after sunset around this time. Medieval chroniclers were skilled at watching the sky and could tell the difference between normal and strange events. So when they took the time to write down strange celestial events, they were probably seeing something that was really strange. Between 774 and 776, Chinese astronomical records from the Tang dynasty, which kept some of the most advanced celestial observations in the world, noted a number of strange events. Chinese astronomers were especially good at keeping track of comets, novae, and other short-lived events. Their records talk about guest stars and strange atmospheric events that don't match up with any known astronomical events that can be seen from Earth. The Annals of Ulster say that there were strange lights and weather patterns in Ireland during this time. Irish monasteries were places where people could learn and keep detailed records of events on Earth and in the sky. Their chronicles often give us information about things that other sources might miss. The fact that different independent chronicle traditions all record strange things happening at the same time suggests that something strange was really going on. But this is where the story gets really interesting from a human point of view. People in the Middle Ages who saw these things had to make sense of them using what they already knew. This meant that they mostly understood strange things through religious and philosophical lenses instead of scientific ones. A strange light in the northern sky could mean that the government is about to change, that God is unhappy with how people are acting, or that the end of the world is near. People probably thought of the Red Cross in the Anglo-Saxon Chronicle as a Christian vision, maybe showing God's judgment or mercy. These interpretations weren't simple or stupid. They were smart tries to make sense of strange events with the best tools available at the time. It also looks like the weather in the Middle Ages was strange from 774 to 776, with different records talking about harsh winters, strange storms, and other weather events that were out of the ordinary. Cosmic rays don't directly control the weather, but they can change the chemistry of the atmosphere in ways that might change how clouds form and how much rain falls. Medieval people would have thought it was magic that invisible particles from space could change the weather on Earth. However, modern research shows that these connections are possible in theory. Some agricultural records from this time, when they still exist, talk about strange crop yields or growing conditions. Farmers in 774 were very aware of small changes in the environment that could have an effect on their crops. They would have noticed if plants were acting differently than they should have. Theoretically, increased cosmic radiation could impact plant growth and development in ways that seasoned farmers might notice, even if they couldn't articulate their observations. Monks may have noticed small changes in how plants grew or flowered in monastery gardens, which were well-kept places. Medieval monasteries kept very detailed records of farming, and some of these records suggest that the weather was strange during the mid-700s and 70s. It is impossible to say for sure if these changes were caused by cosmic radiation or just normal changes in farming, but the timing is interesting. Even if the cosmic ray event itself couldn't be seen, it probably had a big effect on the minds of people living in medieval times. Even though no one could say for sure what was going on, strange lights in the sky, strange weather patterns and strange natural events would have made people feel like something big was happening. People in the Middle Ages lived much closer to the natural rhythms of the world than we do now. This made them more aware of small changes in the environment that people who live in cities today might not notice at all. A farmer who slept outside every night would notice if the aurora appeared at latitudes that were lower than usual. Similarly, a monk who prayed at regular times would notice if the colours of dawn or dusk looked different than usual. When strange things happened in medieval communities, people usually turned to religion more, asked learned people for advice, and paid close attention to other signs that might help them understand what was going on. Communities might set up special prayers, processions, or other religious activities to respond to divine messages that are hidden in natural events. It is especially sad that people in the Middle Ages saw the aftermath of one of the most powerful astrophysical events in history, but they had no way to understand what it really meant or how important it was. They were like people who were trying to understand a symphony but could only hear a few notes here and there, or who were trying to enjoy a painting but could only see random brushstrokes. But their careful observations and detailed records, which are still kept in monastery chronicles and royal annals on several continents, give modern scientists important information about both the cosmic ray event and its possible effects on Earth. Medieval chroniclers, writing by candlelight in stone scriptoriums, made records that would be very useful to astrophysicists 13 centuries later. People living between 774 and 776 experienced mystery in its purest form, things that were clearly important, but couldn't be explained by what they already knew. They used the tools they had: careful observation, keeping detailed records, and thinking about what they saw using religious and philosophical traditions that had helped people understand things for a long time. Picture yourself as a detective trying to figure out a mystery that happened more than 1200 years ago. The only clues you have are scattered across royal archives, monastery libraries, and the hidden records written in tree rings and ice cores. When modern scientists first found proof of the 774 cosmic ray event, they had to put together medieval chronicles and the most advanced astrophysics to figure it out. In the early 2000s, researchers looking at tree ring data saw something amazing that led to the big discovery. The amount of carbon-14 in wood samples from 774 to 775 went up a lot, which hasn't happened in the last few thousand years. It was like nature had suddenly switched pens to write the same story, making a signature so unique that it could be seen in trees from Japan to Germany to North America. But what makes this discovery so interesting is that the same strange thing happened at the same time in many different records all over the world. Ice cores from Antarctica and Greenland had higher levels of beryllium-10 and other isotopes that are made when cosmic rays hit other particles. Coral growth rings from tropical oceans showed signs of the same event in their chemical makeup. It was like seeing the same fingerprint at crime scenes on different continents. Medieval chroniclers, who wrote by candlelight with quill pens, unknowingly recorded pieces of this cosmic puzzle in their careful notes about strange events. It was no longer just a strange medieval superstition that the Anglo-Saxon Chronicle mentioned a red crucifix in the sky. It could be useful scientific information about how cosmic radiation affects the atmosphere. Chinese astronomical records were especially useful because astronomers in the Tang dynasty kept very detailed records of celestial events. Their records of guest stars, strange lights, and atmospheric anomalies from 774 to 776 helped us understand how experienced skywatchers might have seen such an event with the tools they had at the time. To connect medieval chronicles to modern astrophysics, you had to think about things in a way that was like going back in time. Researchers needed to comprehend not only the observations made by medieval individuals, but also how these observations would have been interpreted and documented within their cultural and scientific contexts. Medieval chroniclers would have used the language of omens, wonders, and divine signs to write about something that we could describe in terms of particle physics and atmospheric chemistry. The result of this cross-disciplinary detective work was a picture of an event that was both dramatic and invisible. No medieval technology could have detected the cosmic ray bombardment itself, but careful observers might have been able to see its secondary effects, such as strange auroras, atmospheric phenomena, and maybe even small changes in weather patterns. The timing of events recorded in medieval chronicles roughly matches the time when cosmic ray levels were high. This suggests that some of the strange things that medieval writers wrote about may have been caused by the invisible radiation storm. It's like finding out that puzzle pieces that seemed unrelated actually fit together to make a whole picture when you look at them from the right angle. Islamic astronomical records from Baghdad and Cordoba also talk about strange things that happened during this time. Medieval Islamic astronomers were some of the best at observing celestial events in the world. Their records often add to and clarify what European and Chinese sources have said. The worldwide nature of these records suggests that what was happening was truly global, not just in one area. Modern researchers have a hard time figuring out which cosmic ray effects are real, and which are just the normal background of strange events that medieval chroniclers wrote about all the time. People in the Middle Ages lived in a world where comets, eclipses, strange weather, and many other events were always happening and being seen as important. To figure out which anomalies might be linked to the cosmic ray event, you need to carefully look at the timing, global distribution, and the specific nature of the reported phenomena. One of the most interesting things about medieval records is how consistent they are across different cultures. When Irish monks, Chinese court astronomers, and Islamic scholars in Spain all write about strange things happening in the sky at the same time, it means they were seeing something that was really strange, and not just what people in their cultures thought were signs of bad luck or good luck. This cosmic mystery shows how modern science works best when people work together. Astrophysicists offered theoretical frameworks for comprehending cosmic ray phenomena and their possible impacts. Historians and archaeologists helped by sharing their knowledge of medieval sources and the historical context. Geochemists and climatologists studied tree rings, ice cores, and other natural records that keep chemical traces of events from long ago. The 774 event is especially useful for science because it can be used as a kind of cosmic calibration tool. Scientists can better understand similar but smaller events in the geological and historical record by studying how this intense cosmic ray event changed Earth's atmosphere and biosphere. It's like having a Rosetta Stone to help you figure out what cosmic ray signatures mean in natural archives. The medieval chroniclers who wrote about strange events in 774 to 776 were part of a scientific collaboration that they could never have imagined. Their meticulous observations, documented in manuscripts dispersed throughout monastery libraries and royal archives, yielded essential evidence for comprehending one of the most consequential astrophysical occurrences in recorded history. Scientists can now read the cosmic signatures hidden in tree rings and ice cores thanks to modern technology. However, medieval people who saw the event gave scientists the context they needed to understand how it might have looked to people who lived through it. The combination of high-tech analysis and careful historical research has uncovered a story that neither method could have found on its own. The people who saw the 774 cosmic ray event had no idea they were witnessing astronomical history, but their careful record-keeping and detailed observations made a time capsule that would be very useful to researchers more than 1,000 years later. It's a reminder that observations that seem unrelated can sometimes show their true importance only when looked at from the point of view of later scientific knowledge. Imagine waking up on a normal morning in 775 when the year before had brought news of strange events from all over the world. You get up with the sun because that's when life starts in a time before electric lights. When you step outside your home, whether it's a peasant's cottage, a monastery cell, or a merchant's house, you might look up at the sky and realise that something strange has been happening up there. The cosmic ray event that peaked in 774 was making small changes in your environment that you couldn't see, but the strange things that chroniclers and travellers wrote about were adding a sense of wonder and uncertainty to everyday life. People in the Middle Ages were used to living with mystery. They knew that a lot of things about the natural world were beyond human understanding, but the fact that there were so many strange reports during this time made them feel like big changes might be happening in the cosmic order. No matter if you were a devout monk following the canonical hours or a farmer giving thanks for another day of life, your morning routine would always start with prayers. But prayers from the Middle Ages often asked for protection from all kinds of natural and supernatural threats. The reports of strange lights and unusual weather might have made these requests seem more important than usual. You lived in a time when the line between natural and supernatural explanations was not very clear. Strange things could be seen as either divine messages or bad omens. Most people in 775 were farmers, so they had to pay close attention to natural signs and seasonal patterns all the time. To be successful in farming in the Middle Ages, you had to be able to read subtle signs in the environment, like when to plant based on the temperature and moisture of the soil, how to tell when the weather would change based on the clouds and wind patterns, and how to tell when it was time to harvest. People whose survival depended on being able to read nature's signals would notice any strange changes in the environment right away. The higher levels of cosmic radiation that were falling on Earth at this time could have had an effect on plant growth that experienced farmers might have noticed. Medieval farmers were very sensitive to changes in how crops grew and developed, even though the effects would be small compared to more obvious factors like weather and soil quality. If a farmer worked the same fields for years, they would notice if the plants were acting even a little bit differently than they were used to. Monastery gardens, in particular, were carefully controlled spaces where small changes might be easier to see. Monks who took care of herb gardens and medicinal plants were trained to be very observant and pay close attention to how plants grew and how healthy they were. Because they knew so much about how plants normally behave, they might have been able to spot things that less experienced observers would have missed. The psychological climate of daily life during this era was likely affected by the proliferation of anomalous reports from various regions and sources. Medieval communication networks, which were based on trade routes, pilgrimage routes, and diplomatic contacts, moved information slowly but steadily. Strange stories from faraway places would slowly make their way into local communities, making people feel like the normal order of things was changing in some way. People in the Middle Ages knew that big events often made themselves known through natural signs and omens. Medieval people strongly believed that strange events could happen before big changes in politics, society, or religion. People who lived at the time would have thought that something important was going on, when several sources reported strange events happening at the same time, even if they didn't know exactly what it was. People might have talked about strange weather, strange lights, and other strange things that travellers and chroniclers had seen more often during this time. Because medieval communities were small, interesting news spread quickly. The collection of strange reports would have given people interesting things to talk about at communal meals, market days, and other social events. People who worked outside would have had more chances to see strange weather patterns that people who worked inside might not have seen. Blacksmiths, carpenters, and other craftsmen who worked outside would have been in a good position to notice changes in the colours of the sky, strange cloud shapes, or other atmospheric oddities that could be related to the invisible cosmic ray bombardment that is hitting the upper atmosphere of Earth. During this time, people might have spent more time watching the sky at night, because they were more aware of the possibility of strange celestial events. People in the Middle Ages were already good at looking at the stars. The night sky was much clearer without light pollution, and looking at the stars was important for keeping track of time and finding your way. But reports of strange lights and atmospheric anomalies would have made them even more careful about what they saw at night. During 775, religious observances may have encompassed specific prayers or rituals intended to appropriately address the enigmatic signs that appeared with notable frequency. Medieval Christianity offered frameworks for interpreting natural phenomena as divine communications, and communities may have organised supplementary religious activities to ensure appropriate responses to perceived celestial messages. Life in the Middle Ages was still governed by the seasons, even though strange things were happening in the background. No matter how many cosmic rays were in the air or how many strange lights were in the sky, spring planting, summer cultivation, autumn harvest and winter preservation activities all followed their old patterns. But there may have been more talks about what current events mean and what they could mean for the future while the work was going on. Merchants and travellers, who had the most information about different parts of the world in medieval times, were very important in spreading news about strange events to different areas. A merchant who travelled between cities a lot could act as an unofficial clearinghouse for stories about strange things that happened, letting people compare what happened in their own area with what happened in other places. The cumulative effect of living through a time when strange things happened more often than usual was probably a stronger feeling of living in important times. People in the Middle Ages knew that they were part of ongoing historical stories, like the history of their kingdoms, the history of the Bible, and the story of Christendom. They thought that strange natural events might mean that important parts of these bigger stories were being written. What makes this especially sad is that the people of 775 were going through a very important event in the universe, even though they had no idea what it really was. One of the strongest cosmic ray bombardments ever recorded was happening, but people at the time couldn't see it. It left permanent marks in tree rings and ice cores. They were making records that would be very useful to scientists 1,000 years later, but they didn't know it at the time. The story of how modern scientists figured out what happened during the 774 cosmic ray event is like a detective novel for smart people, with clues hidden in Japanese cedar trees, Greenlandic ice sheets, and the margins of medieval manuscripts. It's a story that shows how the most advanced science of the 21st century can sometimes rely on the careful notes of monks from the 8th century who were just trying to write down what they saw in the world around them. As is often the case with scientific breakthroughs, the discovery started when someone noticed that the data didn't look quite right. Researchers studying radiocarbon levels in tree rings in the early 2000s were creating detailed timelines of past weather conditions when they found something that had never been seen before. A huge rise in carbon-14 levels that happened all over the world in trees between 774 and 775. Imagine the moment when these scientists first understood what they were seeing. Radiocarbon dating works because cosmic rays change nitrogen in the air into carbon-14 at rates that are fairly predictable. For thousands of years, this process has been running like a clock in space, making a baseline that archaeologists and climate researchers use to date old things. But in 774, that steady clock in space suddenly sped up. The spike was huge, about 20 times higher than normal levels of cosmic rays, and it happened all over the place at the same time. During their 774 to 775 growth rings, trees in Japan, Germany, North America, and other parts of the world all showed the same huge rise in carbon-14 incorporation. It was like finding out that every clock in the world had run fast for a short time in the same year over 1200 years ago. At first, scientists didn't know what could have caused such a big and sudden event around the world. Testing nuclear weapons in the 1960s had caused fake radiocarbon spikes, but the natural historical record didn't have anything like what they were seeing in 774. In theory, solar flares could cause more cosmic rays, but the 774 event was so big that it was bigger than any known solar storm. The big step forward happened when scientists started looking for other natural records that keep cosmic ray signatures that could back up their findings. Antarctic ice cores, which trap gases and particles from the atmosphere in layers that look like pages in a frozen book, showed higher levels of beryllium-10 and other isotopes made by cosmic ray interactions during the same time period. Coral growth rings from tropical oceans had other chemical signs of the same event. Scientists were sure they were looking at something truly new in the historical record, because evidence from many different sources, tree rings, ice cores, and coral reefs, all pointed to the same amazing event that happened in 774 to 775. But figuring out what happened was just the first step in understanding it. What might have caused such a strong burst of cosmic radiation? This is where medieval chronicles became an unexpectedly important part of the scientific equation. Scientists figured out that if cosmic ray levels had gone up a lot between 774 and 775, there might be indirect proof of what happened in historical records from that time. Chroniclers from the Middle Ages were skilled at noticing strange things in the sky and the air, and they may have seen things that could be linked to higher levels of cosmic radiation. Researchers had to think like both scientists and historians in order to link medieval observations to modern astrophysics. They had to know not only what people in the Middle Ages might have seen, but also how those observations would have been understood and recorded in the 8th century's ways of knowing and believing. A phenomenon that contemporary scientists would characterize through the lens of particle physics may be depicted in medieval chronicles as an omen, miracle, or divine sign. The interdisciplinary investigation yielded evidence that medieval observers discerned unusual phenomena during the years 774 to 776. The Anglo-Saxon chronicles mention of a red crucifix in the sky, Chinese records of guest stars and atmospheric anomalies, and other chronological accounts of strange lights and weather patterns from this time suddenly became more important as possible proof of cosmic ray effects. The scientific teamwork needed to solve this mystery is an example of how modern research works best. Astrophysicists came up with theoretical models of what could cause such strong cosmic ray bursts. Scientists who study the atmosphere talked about how high-energy particles could change the chemistry of the upper atmosphere. Historians and archaeologists offered their knowledge of medieval sources and timelines. Geochemists created ways to get cosmic ray signatures from natural archives. Each piece of evidence backed up and made the others clearer. The tree ring data gave very accurate measurements of when and how big things were. The analysis of ice cores confirmed that the event affected the whole world. Medieval chronicles provided perspectives on the potential perceptions of the event's secondary effects by human observers. Theoretical astrophysics proposed potential origins for such a profound cosmic ray burst. The most likely explanation is that Earth was hit by radiation from either a gamma ray burst, which is one of the strongest explosions known in the universe, or a huge stellar flare from a magnetar, which is a neutron star with very strong magnetic fields. Either of these events could have caused the high-energy particle bombardment that made the isotopic signatures found in natural archives from 774 to 775. This discovery is especially important because it is one of the most powerful astrophysical events that has ever been recorded. Gamma-ray bursts are so powerful that they can briefly outshine whole galaxies. If one happened close enough to Earth to cause the 774 cosmic ray spike, it would be a very rare astronomical event. We're talking about things that happen maybe once every few thousand years in our part of the universe. The effects go beyond just figuring out what happened in one strange event. The 774 cosmic ray spike is a good way to figure out how these kinds of events affect the atmosphere and biosphere of Earth. Scientists can better understand similar but less dramatic cosmic ray changes throughout geological history by looking at the isotopic signatures left behind by this well-known event. Modern technology has made it possible for scientists to read chemical signatures in natural archives with amazing accuracy. However, medieval chroniclers gave us the human context we need to understand how people living through these events might have seen them. The combination of high-tech analysis and careful historical research found a story that neither method could have found on its own. Those who lived through the 774 cosmic ray event could never have guessed that their careful observations would one day help scientists learn more about neutron stars, gamma-ray bursts, and cosmic ray physics. But their detailed records, which are still kept in monastery libraries and royal archives, were very important for solving one of the biggest astrophysical mysteries in history. As you get more comfortable in your reading spot, maybe while you finish your evening tea, let's think about how a cosmic event that lasted only a few months in 774 has changed how we think about the universe for more than 1,000 years. It's a story about how things we can't see can leave permanent marks on the world, and how those marks can wait hundreds of years for someone to learn how to read them. Scientists now call the cosmic ray event of 774 the most dramatic radiocarbon spike in recorded history. Its effects go far beyond just being an interesting data point for astrophysicists. This event fundamentally changed how we think about the relationship between cosmic phenomena and terrestrial life, showing that even systems on Earth that seem stable can be drastically changed by rare but powerful events happening millions of miles away in space. The tree rings that recorded this cosmic bombardment are still around today, preserved in old wooden buildings, archaeological sites, and forests around the world. Every piece of wood that grew between 774 and 775 has a chemical signature of that amazing year in its cells, like a molecular autograph written by the universe itself. This invisible timestamp links medieval cathedrals, ancient temples, and archaeological artifacts from this time period to one of the most important astrophysical events in human history. The 774 event has changed the way we do modern radiocarbon dating. Before this discovery, scientists thought that levels of carbon-14 in the atmosphere had stayed pretty stable over time, with only small changes caused by solar activity and other things that could be predicted. The sudden rise in 774 showed that assumption was wrong, which led to more advanced calibration methods that take into account sudden cosmic ray events. The 774 event has helped make archaeological dating more accurate. Thanks to this unique cosmic signature, we can now date artifacts from the late 8th century with more accuracy than ever before. It's like having a universal timestamp that shows up in organic materials from all over the world. This lets archaeologists line up their timelines with amazing accuracy. The effects on our understanding of medieval history have been just as big. The 774 cosmic ray event serves as a stable chronological reference, aiding historians in correlating events across diverse cultural traditions and geographical areas. When Chinese chronicles, European monasteries and Middle Eastern sources all write about strange things happening at the same time, it makes sense that these events could be connected to the same cosmic event. Climate science has also gained insights from comprehending the influence of cosmic rays on Earth's atmospheric chemistry. The 774 event was too short to change the climate in the long term, but it did show that cosmic radiation can affect atmospheric processes in ways that climate models need to take into account. Contemporary researchers examining historical climate variations are increasingly focusing on cosmic ray fluctuations as a potential influence on atmospheric chemistry alterations. Researchers are now actively looking for similar events in the geological record. Scientists are now looking for more cosmic ray spikes that are hidden in tree rings, ice cores, and other natural records. They want to find more times when Earth was hit by strong radiation from space. Every new piece of information helps us understand how often these things happen and what they might do. The 774 event has changed how we study space weather. Cosmic rays can damage modern satellites and electronic systems, and knowing how extreme events have happened in the past can help engineers make technology that can survive them. The 774 spike is a good example of the kinds of cosmic ray intensities that Earth's technology might need to be able to handle during rare but powerful astrophysical events. The need for scientists and historians to work together to understand the 774 event has led to new models for how these two fields can work together. Astrophysicists now often ask medieval historians for help, and climatologists and archaeologists work together to learn more about how the environment has changed over time. Researchers are realizing that to fully understand complex phenomena, they need to look at them from many different angles. This has made the lines between different academic fields less clear. The discovery of 774 has changed the way both history and science are taught in schools. The story shows how modern scientific tools can get information from old materials that people in the past couldn't get to, while also showing how important it is to carefully observe history in order to understand scientific data. Students learn that to understand the past, they often need to use the best technology and the best research. The 774 event has also changed the way we think about how people see natural events. Medieval chroniclers who wrote about strange weather events in 774 to 776 were doing scientific research that they could never have imagined, and the information they gathered would be useful 1,000 years later. Their careful observations remind us that even records that seem unimportant might have information that future generations will find very useful. The 774 story has helped people understand astronomy better because it shows how Earth is part of a changing and sometimes violent cosmic environment. The 774 event had a direct effect on our planet. Unlike black holes or galaxies that are far away, we can still see the effects today. It makes the universe seem more real and important to everyday life. The discovery has also made us think about how these cosmic ray events might have changed human history in ways we don't yet know about. If strong cosmic radiation can change the chemistry of the atmosphere and possibly change the weather, climate, or even biological processes, then rare but powerful cosmic events may have had an impact on historical events that we don't know about. Understanding events like the 774 cosmic ray spike has helped shape modern talks about existential risks and planetary defense. Cosmic ray bursts don't directly threaten Earth as much as asteroid impacts or supervolcanic eruptions do, but they do show that Earth is in a cosmic environment where rare but powerful events can have global effects. When making plans for the long-term survival of humanity, we need to think about all the cosmic events that could have an effect on our planet. The 774 event has become a touchstone for talks about how scientific discovery and historical understanding are related. It shows how the most advanced modern technology can sometimes show that ancient observers were more accurate than people thought, and how careful historical research can help us understand scientific data better. The cosmic ray event of 774 is a reminder that the universe is full of things we don't fully understand yet. There may be signs of cosmic events in every tree ring, every layer of ice core, and every well-preserved medieval chronicle that we haven't yet figured out how to find or understand. The storm that hit Earth in 774 was invisible, and waited more than 12 centuries for people to learn how to figure out what had happened. The legacy of the 774 event keeps changing as new ways of doing research and new ways of thinking about things come up. Scientists in the future will surely find more proof and come up with new ways to explain what happened that year. As people learn more and technology gets better, the cosmic ray spike that people in the Middle Ages didn't understand will keep giving up its secrets. What started as an invisible bombardment of high-energy particles has turned into a link between medieval chroniclers and modern astrophysicists, ancient trees and modern climate science, and human observation and cosmic events. It shows that the universe is always writing its own story in the natural world around us, using languages that we're still learning how to read. As we come to the end of our journey through this cosmic mystery, it's a good idea to think about what the 774 event teaches us about how we fit into the larger universe. This astrophysical event was so strong that it left permanent marks on every living thing on Earth, but the people who were there couldn't see it at all. It's a humbling reminder that we are part of cosmic systems whose workings we're only starting to understand. In 774, radiation came down from space and connected Earth to events happening at distances and scales that are hard to imagine. The high-energy particles that hit our atmosphere came from colliding neutron stars, exploding magnetars, or gamma-ray bursts from dying stars. They had to travel across interstellar space to get to us. The trees that recorded this event in their growth rings were, in a very real way, recording the death throes of stars that had lived and died millions of years before humans were around. This cosmic link goes against the medieval view that the Earth was at the centre of a small, understandable universe. The people of 774 lived in a universe that seemed to be in order. The stars were in a celestial sphere, with Earth at the centre and divine purpose as the main idea. The real universe that sent them cosmic radiation was so big that people in the Middle Ages couldn't even imagine it. It was full of things that could affect Earth over distances so great that light itself took years to cross them. The medieval view of how everything in the universe is connected wasn't completely wrong, though. Medieval thinkers thought that events in the sky could affect things on Earth. Even though their ideas about how this worked were wrong, the idea that Earth is part of larger cosmic systems that can affect local conditions was very smart. The cosmic ray event of 774 showed that explosions of stars that happen light years away can have effects on things that happen on Earth. The fact that the 774 event was invisible also shows how limited our senses are, and how important it is to make tools that help us see more clearly. People in the Middle Ages were very good at watching the sky. They could accurately predict eclipses, follow the movements of planets, and spot strange celestial events. But in the 8th century, there was no way to see cosmic ray bombardment at all. Because of this technological limitation, people who were witnessing one of the most dramatic astrophysical events in recorded history had no direct way to find out what was going on. It was like trying to understand a symphony while only hearing a few notes here and there, or trying to enjoy a huge landscape while only seeing small details through a small window. The creation of scientific tools that can find cosmic ray signatures in natural materials is a big step forward for human senses. We can see things that we couldn't see directly by looking at tree rings, ice core chemistry, and isotopic dating. We've learned how to read cosmic messages written in the molecular structure of old wooden ice. This lets us get information that no other generation of humans could get. This growth in perceptual ability has shown that Earth keeps detailed records of cosmic events that have happened over time. There are chemical traces of past cosmic ray changes in every old tree, every ice sheet, and every coral reef. The Earth is like a huge library of astronomical events, just waiting for people to make the tools they need to read it. The 774 discovery also shows that scientists often need to look at things over very different timescales to understand them. The cosmic ray event itself may have lasted for months, but its effects can still be seen in things that are over 1200 years old. Chroniclers from the Middle Ages wrote down what they saw within years or decades of the event. Modern scientists, on the other hand, only found the cosmic ray spike after developing analytical methods that took hundreds of years to perfect. To understand the 774 event, people from different academic fields and historical periods had to work together. Medieval monks who kept careful records of the stars were unknowingly taking part in research that wouldn't be finished until the 21st century. Their patient observations, which have been kept in monastery libraries for over 1,000 years, gave scientists the information they needed to solve a cosmic mystery they could never have imagined. This temporary partnership makes me think about what information we might be recording today that will be useful to researchers hundreds of years from now. Our extensive records of weather, climate, and cosmic ray changes could one day help scientists figure out astronomical events that we can't see or understand right now. We might be unwitting subjects in scientific studies that will not conclude until well after our departure. The 774 event also shows that rare but powerful events can have effects that last long after they're over. The bombardment of cosmic rays may have lasted for months, but it left behind permanent marks that have changed our understanding of radiocarbon dating, archaeological chronologies, and how Earth and space interact for more than 1,000 years. Short events can have effects that last for hundreds of years. The 774 cosmic ray event makes us think about our place in systems that work on scales that are bigger than what we can see and feel. We live in galactic neighbourhoods where stars can explode and change the chemistry of the atmosphere on planets that are light years away. Every day we live our lives against the backdrop of cosmic processes that follow physical laws we are still learning about. The human response to cosmic mystery, exemplified by the meticulous observation, comprehensive documentation, and profound interpretation exhibited by medieval chroniclers, signifies a distinctively valuable aspect of the universe. To the best of our knowledge, Earth is the sole location where conscious entities are systematically observing, documenting, and analysing cosmic events in an effort to comprehend their significance and consequences. The people of 774 were exposed to cosmic radiation without knowing where it came from or what it meant. They were curious and careful and made detailed records that would be very helpful to future generations. Their reaction to the unknown, neither panicking nor ignoring strange events, but instead carefully observing and recording, shows the best of human scientific instinct. Researchers today who are looking into the 774 event are following in the footsteps of medieval chroniclers by carefully observing and thoughtfully interpreting what they see. They use tools that medieval chroniclers could never have imagined, but they still use the same basic methods of systematic data collection and collaborative analysis. The enduring human curiosity regarding cosmic phenomena links us through the ages to individuals who also marvelled at the universe's operations. As you get ready to end this story and maybe go to sleep, think about how you're a part of this ongoing human project to understand cosmic events. The stars you might see through your window are in the same part of the galaxy that sent cosmic radiation to Earth in 774. The universe that made that old mystery is still telling its story in tree rings, ice cores, and things that people see that future generations will be able to figure out. The cosmic ray event of 774 is a reminder that there are many things in the universe that we haven't yet learned to see or understand. Every night sky has signs of things that might be happening on Earth that we can't see yet. The invisible storm that hit Earth over 12 centuries ago is just one example of the cosmic dramas that are always happening around us. Most of them are still waiting for humans to get the tools and knowledge they need to understand how important they are. Sweet dreams. I hope you dream of medieval monks carefully writing down strange things by candlelight, not knowing that they were making data for astrophysicists 13 centuries in the future. This is a reminder that every careful observation, every preserved record, and every moment of wonder about the cosmos might one day help us solve mysteries we haven't even thought to ask about yet. As you fall asleep, wrapped in the warmth of your modern blanket in a world lit by electric lights that would have seemed magical to people in 774, take a moment to think about the amazing story we've shared. Over 1200 years ago, an invisible cosmic storm hit Earth. It left its mark on every tree that grew, every piece of ice that formed, and every living thing that was alive during those important months. People in the Middle Ages who lived through this event, farmers tending their fields, monks copying manuscripts by candlelight, and scholars tracking the movement of planets, had no way to see the high-energy particles falling from space. But they reacted to the strange things they could see with the same careful observation and thorough record-keeping that is typical of the best scientific instinct in humans. Their detailed records, which were kept in monasteries and royal archives all over the world, eventually gave modern scientists important information about one of the most powerful astrophysical events in history. People in the Middle Ages who wrote with quill pens unknowingly helped researchers in the 21st century, who used particle accelerators and mass spectrometers. As our analytical tools get better and our theoretical understanding of stellar phenomena grows, the cosmic ray event of 774 keeps giving us new information. There is no doubt that future generations will find more proof and come up with new ways to understand what happened that amazing year. The invisible storm that people in the Middle Ages felt but didn't understand will keep teaching us about how the universe works for many years or even centuries to come. But maybe the most important thing we can learn from this cosmic mystery is that the universe is always making new things that we haven't yet figured out how to see or understand. There may be signs of cosmic events in every tree ring, every layer of ice core, and every careful historical observation that we don't yet know how to look for. The natural world keeps detailed records of astronomical events in chemical languages that we're still learning to read. As you get ready for bed tonight, cosmic rays are softly falling on Earth from faraway parts of the galaxy. This has been happening every night for billions of years. Most of this radiation is too weak to leave any traces, but stars in our cosmic neighbourhood are living and dying in ways that could one day send more powerful bursts of high-energy particles toward Earth. Future observers, maybe even your own descendants, might look back at this time and wonder what cosmic events we went through without knowing. They could find signs of stellar events in materials from our time, signs that our current technology isn't advanced enough to find or understand. The universe might be sending us messages in our modern world that we won't be able to understand until we come up with new tools and ways of thinking. People in 774 were part of cosmic history without even knowing it. They made records that would be very useful to researchers 1,000 years later. We might also be unknowingly taking part in astronomical studies that won't be finished until long after we're gone. Our careful observations and thorough record-keeping may one day help us figure out cosmic mysteries that we can't even begin to imagine. The invisible cosmic storm of 774 connects medieval wonder to modern understanding, ancient observations to modern astrophysics, and human curiosity to the huge processes that shape our universe. It reminds us that we live in systems that are much bigger than what we can see and feel right now, but we have the unique ability to observe, record, and slowly understand these cosmic events. As you fall asleep, you are part of a story that has been going on for a long time. From medieval chroniclers to modern scientists, from observations made long ago to discoveries that will happen in the future. The same universe that sent cosmic radiation to Earth in 774 surrounds you tonight. It is full of things that future generations will study and understand in ways we can't even imagine right now. The mystery of 774 shows us that with time, careful record-keeping, and working together to figure things out, we can find out things that seem impossible to know. Writing by candlelight in the Middle Ages and studying isotopic signatures today are both parts of the same big human project, figuring out where we fit in the universe. Sleep well, knowing that you're part of this ongoing story of cosmic discovery. The universe around you is full of amazing things that future generations of curious people will discover, understand, and appreciate. These people will share our wonder about how the world works beyond what we can see. The invisible storm of 774 shows us that the most important events in cosmic history might happen right next to us, without us even knowing it, leaving clues for future observers to find and figure out. Every night, the universe gets new cosmic radiation, new stellar events, and new chances to write its own history in the natural records that are all around us. Think of the dreams of medieval chroniclers and modern scientists, cosmic rays and ancient trees, invisible storms and careful observation. Think about the ongoing human project of figuring out the universe and your place in a story that connects careful observers across centuries of cosmic mystery and discovery.